Help, yeah? All right, cool. Can you guys hear me good? Awesome. Good morning, everybody. I hope you guys are having a great time at Devcon. I don't know about you guys, but this just has been a great week. I've seen such cool talks, and the Build Guild is here in full representation, and we're here to support you on Scaffold ETH and building on Ethereum. So we're going to be focusing today on Scaffold ETH. We're going to explain a little bit about Scaffold ETH, just to kind of feel for the room. Who here has actually used Scaffold ETH before? Anybody? Or is it kind of new? Okay, cool, couple hands. Who here is a software developer? Who here is an aspiring software developer? Okay, so we got some new people. We got some people that probably have some experience coding. So I'm going to try to keep this kind of a slow pace. A lot of the workshops that we had here this week have been a little bit quick, hard to follow. So I do want to make it kind of paced at a pace where you guys can follow along, especially being new in building on Ethereum can be a little daunting. Who here attended another Scaffold ETH workshop this week? Anybody? A few? Okay, cool. We had a lot. So who here is hacking at the hackathon? A few of you? Okay, cool. Thank you for the hands. I know you guys are probably like, oh my God. But, okay, cool. So I appreciate you guys' time. My quick intro about myself. My name is Kevin Jones. I work as a developer relations engineer for the Graph protocol, but I also am a core member of the Build Guild supporting Scaffold ETH, onboarding and education in Ethereum. And it's actually how I got my start into Ethereum, so it's very appropriate. I continue to be very active in the community. Scaffold ETH is a tool that has come out of the Build Guild, or the Biddle Giddle. The Biddle Giddle, just real quickly, is basically a DAO that is basically focused on education and tools for the Ethereum ecosystem. So if anyone wants to get involved with the Build Guild, you can totally do that, and I highly recommend that, especially if you're getting into software development in the Ethereum ecosystem. You can go to the Build Guild app, but really the meat and potatoes for getting into the Build Guild is through a tool called Speedrun Ethereum. So Speedrun Ethereum is this kind of it's like a challenge kind of gamification on writing and developing smart contracts on Ethereum. And so you go through this kind of process where you go through and build different projects. So you start by building a very simple NFT. You eventually learn to build a staking application and understand the concepts of staking on a smart contract. Then you build a token vendor, and then you do a dice game and you learn about randomness on the Ethereum blockchain. And then eventually you get a little bit more difficult and you can build a DEX. Once you finish that, you actually become a member of the Build Guild, so anyone can do that. So highly recommend after today, go to speedrunethereum.com and test your skills, right? Because it's a great learning experience too, because you really have to think about what smart contracts are and how they work. At any point today, if you have questions in the app, there's a questions and answer. I'm going to try to keep an eye on it when I'm here so I can see, but also feel free to raise your hand, okay? I want this to be interactive. I don't want you guys to I don't want to lose anybody. If you have a question about something, please let's get it addressed, okay? So we're going to talk about Scaffold ETH. We're actually going to use it. We're going to walk through how you use it, and the idea is by the end of today, we're just going to deploy a smart contract, probably to a test net, maybe like Base. I don't know. We'll see. But if you want to get started on Scaffold ETH, everyone should go to scaffoldeth.io. Okay, there's two ways you can install Scaffold ETH. You can clone the repository and install the dependencies using the Git repo, or you can use the npx script method, the package, the create ETH package. It's the easiest. It says beta here. I've been trying to get that to go away, but we need to remove that. It's fully functional, and it's really probably how you should install it, especially if you want to use Foundry. If you use the Git clone method, it comes with hard hat. If you want to use Foundry, you want to use this method. So all you need to do, but let's just look at the GitHub repo real quick. The main benefits to Scaffold ETH, and I'm going to show it off, but is that it is kind of like complete with everything you need to like build a dApp, really. It's great for hackathons. It's great for prototyping. It's great for like local first development. So you can like build locally and you don't have to like, deploy to a testnet. You can use just the local chain and the local front end that you have, and it's just got all this stuff working for you. It runs with some requirements, so you need Node.js on your machine. You need a Yarn package manager, and you need Git. So just one little bullet on Yarn is make sure you have the newest version of Yarn. Make sure you install that, because if you have an old version of Yarn, you might have some issues. And if you have problems with Node versions, just try 18 or 20. Those are kind of the most compatible versions. If you're running Windows, I would use WSL, so the Linux installation for Ubuntu, and because it's going to make it a lot easier. I don't think it's really easy to use just like native Windows. Okay, so let's get started. So let's do exactly that. Let's go to npx create eth at latest, right? So if you have a terminal, open it up, go ahead and type that in. So this is going to ask you, if once you first do that, it's going to ask you if you want to install that package. So that will just take, a little bit of time to install that, and then it wants to know what you want to name your package. Can you guys see that okay? Yeah? Anyone have? Make it a little bigger. Okay, so we're going to name this one Devcon app. Sure. It's going to ask you what kind of chain you want to use. So we support both Hardhat and Foundry. Personally, if you're new, I would recommend Hardhat. If you're more familiar with TypeScript or JavaScript, I would use Hardhat. If you're more like into the solidity aspects of Ethereum and blockchains and stuff like that, then Foundry might be a better option. Foundry is a little faster. You can write your smart contrast tests and your deployment scripts in Solidity, so it's a little bit less of a learning curve if you don't know TypeScript. But personally, I think Hardhat has been around a little bit longer, so I use that. You can also do no chain if you wanted to just use it as a front end. A lot of people do that for different reasons, but so it's going to go through and install the packages. Okay, so this takes a little bit of time depending on your internet connection and your machine. So we'll just let that sit for a second. Another thing about Scaffold ETH is, again, I mentioned it's a local first, right, kind of tool. So you're running a chain on your machine, and you're running a front end on your machine, and then you're using another kind of terminal to do deploys. So you need a few windows open, okay? So you can just open multiple terminals, that's fine. What I use is a tool called tmux, which lets me kind of split my screen up. So I can do like this, and I can split my screen into kind of a few different ways, and then I can go into this Devcon app folder in these other folders. But you can just do this in like 3 windows. So just open a new terminal, go into the same directory on each window. So it's still installing the packages, so we'll give it 1 second. Let's go just really quick and go back to scaffoldeth.io. The next thing you're going to want to always do if you're just getting started on Scaffold ETH is take a look at the docs. The docs are super good, super simple, but they have exactly what you need to know. If you go to the quick start section, it gives you the how to install all the requirements. It tells you how to set up your environment. So it talks about how you bring up your blockchain, and we're going to go through this, where your configuration for Hardhat and Foundry is, how to do a deploy. And then the components section is super awesome, because these are packages that come with Scaffold ETH that give you some really cool added functionality out of the box that you don't. So especially if you're not a front-end developer, it's very difficult when you first start writing smart contracts and hooking that stuff up to your smart contract. So an example would be like if you want to get an address and you want to get the balance of the address, or just do like ENS resolution, there's a component for that, so you can use that. We're not going to be focusing a lot on the front end stuff, but tomorrow Edda is doing a workshop, and if you are struggling with that aspect, I highly recommend you do that, because she's going to focus on some of the front end stuff. We're going to pretty much just do smart contract stuff today. There's also a balance component, which is cool, so you can see what the balance of an address is. There's an address input that you can type in an ENS, and it will resolve it to an address for you. A lot of cool stuff. Ether input, so it'll figure out what the dollar amounts are at the current time based on the input. And then the last part I just want to show real quick before we get started is the interacting with your smart contract. So there's also hooks in Scaffold ETH for reading from your smart contract or writing. So if you want to read some data from a contract in a specific function, you can do that. You can pass in arguments. If you want to write a transaction to the blockchain from your front end, there's a write function for that, and that is also available in here. So like this is an example of a button that will basically call a function called greeting, set greeting with a value passed as an argument and maybe value as like a transaction, like maybe you want to pay in some value in the transaction, and then does some error checking, and it's a really nice component, really easy to do. Okay, so again, this is not a front-end course, but I just want to mention that if you're first getting started, that's a great place to go. Okay, is it done? Yes. Okay, cool. Bought myself some time. All right, so we have the package now set up. It's kind of ready to go. So we're going to go into our Devcon folder in this one, and we're going to run yarn chain. So all this does is scaffold ETH is a mono repo. So what that means is it has like multiple packages in one. And it has this package JSON file that has a bunch of scripts that you can kind of just type really easily using the yarn command. So yarn chain runs whatever local chain you want to use. So in this case, we chose hardhat. So what it does is it spins up the blockchain on the local machine, local host, and then it gives you these private keys and public keys that you can test with, right? And then, so if you wanted to, you could inject those into like your MetaMask if you wanted to or something. But we're just going to use something else, which is really cool about scaffold ETH that I'll show in a second. And then this other window, we're going to open up our front end. So you always have your chain open, and then you always have your front end open, okay? I'm having a bad typing day today. Okay, I'm going to warm up my fingers. All right, so we now have our chain running, and we also have React running. So scaffold ETH also comes with React with Next.js, and it is the app router implementation of that. I'll show it off in a little bit here, but it's up and running. It's ready to go. It's on port 3000. Let's go ahead and just open up scaffold ETH over here on port 3000. Everyone following along? Yeah? Cool. Anyone having yarn errors? Hopefully you're not. A few? Okay. So just make sure you're using the newest version of yarn. And also, yeah, I'm trying to think what else. That's pretty much the main thing. Make sure you're using a new version of yarn. And if you have to change the version of Node as well, sometimes there's like issues with different versions of Node. You can use NVM, which is Node Version Manager, to swap Node versions. 100% recommend that too. Okay. So scaffold ETH is up, right? We have it up and running. If we firstly scaffold ETH here, it's very basic, but it gives us this our connected address. It's kind of like a hello world page. It tells us how to get started editing our application. It also tells us where our smart contract is that comes with scaffold ETH. But it's also, what's the really cool thing is this debug contracts tab. So right up here, it's debug contracts tab. This is kind of the magic sauce of scaffold ETH, because one of the hardest parts of understanding, writing a smart contract and then interacting with your front end is every time you create a smart contract and you compile it down into bytecode, it also generates an ABI. Okay, so the ABI is this kind of like treasure map, or like how you actually can navigate all the functions and the variables in your smart contract. Now what scaffold ETH does is when we deploy our contract, so we come down here and we do yarn deploy, and come back, it's going to give us some output here. It's going to say, okay, cool, the contract was deployed successfully. This is how much gas it took. This is some output that we get from our deployment script. And then we see some terminal output here with console log, so we see what's going on. And we see that our front end also refreshed. So if we go back there, we get everything that's in our smart contract inside of the front end, okay? So that's really powerful because you don't need to go in there and write, front end code. It's just ready to test. So we can kind of look at this and know exactly what our smart contract looks like. It's got some greeting function or greeting variable. It's got an owner variable, which is an address. It's got a premium, which is a Boolean, and it's got a counter, which is an unsigned integer. And it's got a read function, and it's got two write functions, right? So it's got this greeting that I could change the greeting. So I could say hello world or something like that. Or actually, let's do hello Devcon. Okay, like this. And if I try to hit send, it's going to tell me I don't have any gas. So the next thing you'll learn about scaffold ETH is you get this burner wallet as well. So you don't need to connect to MetaMask. You can just start transacting. There's a faucet button. You grab some funds from Hardhat or Foundry, then you can go ahead and interact with your smart contract. So I just paid some gas, I got a transaction receipt, which has all the details of the transaction, and I updated the state of the greeting variable. So very simple. So if we go into our application and we look at that, we can see that's exactly what our smart contract does. So let's do that. So here it is. I use VS Code. Zoom in a little bit. So again, Scaffold uses the mono repo. So we have this hard hat folder, okay? And inside there, we have this contracts folder. And then we have the your contract. So this is a very basic contract. It has the hard hat console. So this gives us our console logging output that we see on the left terminal that I have. We have a basic contract called your contract. It has an owner address variable. It has the string right here. So if I come in here and say building cool apps, save that, redeploy, and then I come back to Scaffold ETH, we will see that my greeting will change here in just a second. There it goes. So now it's reflected my changes. So a lot of the life cycle of using Scaffold ETH is that you just come in here, make a change to your smart contract, deploy your contract change, and then test your changes, right? It's a way for you to like test your assumptions, as Austin Griffiths likes to say. So, okay, cool. So we have this very basic contract. It has a Boolean, it has a counter, it has a mapping, which is cool. So it keeps track of like how many greetings a particular address has done. We'll use that when we build our smart contract. And then we have like some events, which events are like logs on Ethereum. Who here would say they're new to writing Solidity? Just a few newbies. So when you're writing Solidity, everything is very simple. If you've written any other program language, it's very simple to get started on Solidity. If you don't already know about Solidity by example, it is the most probably important website you'll probably be using over the next year. It's going to have every single example of every single functionality inside of Solidity, and I highly recommend that you guys come here and kind of start using Solidity by example to test different functionality. So there's like a hello world, there's a first application which does like a counter, and it allows you to like see how you increment the counter. And this is just a great resource. So if you're coming in here, we kind of have this kind of basic contract that's a hello world contract. It has this event, which is like logging. It has a constructor. The constructor is basically like at the time of deployment, you might want to set some values. So in this case, we set an owner at the time of the deployment. So we pass this into the deployment script, which we'll go through and show off. There's a modifier. So what I want to do actually is I just want to kind of like gut out this contract. I want to show you that you can kind of just start from scratch and go from there. So you should come into this contract and let's just get rid of some stuff so it's easy to see. I still want to use hard hat console, right? So I'm going to keep that. I want to get rid of all of these variables. I also want to get rid of this. I want to get rid of this event. I need a constructor, but I want to get rid of the stuff that I'm passing in the constructor. And I don't want this modifier anymore. I don't want this function anymore. I want this function because this is an important one. There's two important functions here that I want to keep. One is a withdraw function. Did I break something here? Oh yeah, okay. There's this one function that is a withdraw function, which allows me to withdraw all the funds from the contract. And then there's another one that allows the contract to receive ETH, even though there's no receive function, so it gives you that ability. We also took away the modifier, which we'll get rid of that. We also don't have this owner variable anymore because we deleted that. So we actually want to use message.sender. So let me kind of show you what I did. Ooh. Okay, so what I did is I just took everything out. I kept the constructor. I kept the name of the contract, which is we want to use this year contract because we also have a deploy script that's down here, but I'll get to that. And we just emptied out the constructor, so there's nothing being passed at the time that it actually gets deployed. But we keep this because we want people to be able to come in here and withdraw the funds from the contract, especially if it's mainnet. This might get some funds, and we don't want them locked in the contract forever. So what this does is it allows people a user to make a withdraw function or call, and anyone who does that who is the sender can do a .call and get the value, which is the balance of the contract. So we can basically rug pull this contract, and then we can basically pass a success, okay? Or require, which in Solidity, a require statement is something has to happen, otherwise the transaction will be reverted. And then this last one, like I said, is just so that if someone tries to send ETH to this address, we still want it to be able to receive ETH. So it just allows that receiving. So it's like a payable function, okay? So yeah, so we basically wiped it out. Let's save that, and let's try to deploy. So if you guys do that, you're going to get an error. You're going to get a couple errors, actually. So we could look at the errors in real time. Let's do it. So this one's saying, well, I expected 0 arguments, but I actually got 1 argument when I was doing the deploy. So if we go into that deploy script right below, so again, we're using hard hat in this version, we are using TypeScript to deploy the contract. Let me get rid of some of these comments so you guys can see what's going on. But what we're doing is we are getting we're getting the list of hard hat accounts that are available to us by doing this calling .get named accounts. And we take the very first one and we use that to deploy the contract. So we use that private key, the hard hat private key. And then we call the .deployments to do that, to do the deploy. And then we create a deployment right here by using the await. So an await is like, hey, you need to wait until everything is done before you continue in this code. And we deploy the contract. Now, we say who the transaction is from, right? Who sent the transaction, and what were the arguments that need to happen in that transaction. So this is where the constructor arguments are. So as we mentioned earlier, we took away the constructor arguments. So we also need to take away the arguments here, okay? And we also have logging enabled, and we have like auto mine true. You can take those off if you wanted to. We'll just keep those there. And then if we save that and then now try to deploy, we'll get a new error. But this is what you do in software development, right? You work through errors. So then you're going to see, well, we got a type error in our deployment. Inside of our deploy contract, we got this your contract.greeting is not a function. So let's go back. So another thing you'll notice is we get an instance of the contract right below here. So we say, okay, if you have deployed your contract successfully, take that and get a contract by using get contract from Hard Hat Ethers. So Hard Hat Ethers is an Ethers implementation for Hard Hat that allows you to query the blockchain basically to get the instance. And we query it by calling the name, which is here, and we query it by calling the owner, or who it's from, is the deployer. And then once we have that contract, we can call any functions inside of it, which is really cool. So we can actually do some transactions here inside of the deploy script. Or we can, so in this case, what we're doing is we're doing a console log, and we're logging your contract.greeting. But this doesn't exist anymore because I deleted it, right? So we also need to get rid of this, okay? So if we save that and then deploy again, we should be in the good. There we go. Cool, successful. Okay, let me zoom back in. No more errors. So hopefully you guys have been able to get to that point. So you should come in here, you should wipe out the contract. You don't really need this withdraw function. You could get rid of it too. You could get rid of this if you want. We just want to start from scratch. So what I want to do now, and then you need to come in here, make sure you remove the arguments from the args, make sure you remove this console log that you were doing here and right below that, and then you'll be kind of where I am. I want to pause a second for questions because I know there probably some people might have questions, so let's just give like a couple minutes to answer questions. Put your hand up if you have a question, and I'll check the app real quick. Any questions? No? Yep.
I was more focused on following up with the code. I didn't really get why did we do these changes.
I'm going to build out a new smart contract right now. We're going to create an ERC20 from scratch. So we want to, it's kind of just when you're first using Scaffold ETH, it comes with this stuff to test and see how it looks, but you probably want to just start from scratch. So I wanted to show you guys how if you're doing a hackathon, you can get rid of all the stuff you need and just kind of start at a new base.
And why these specifically? Like why the argument and the other line below?
I'll show you, but that's a good question. The question was basically, yeah, like why are we removing the arguments? Well, this contract comes with a what's called an ownable pattern, or like an ownership pattern, where that owner address is kind of like the access control for withdrawing funds from the contract. We're actually going to use Open Zeppelin to do that, and so I'm going to show you why in a little bit. There was a couple questions in here. Let me just read them real quick. So, can you share the main difference between Scaffold ETH hooks and WAGMI? We use WAGMI for some stuff like getting the account, but the hooks, they're just kind of custom, and they were kind of imported from the previous implementation of Scaffold ETH. So they were kind of rewritten to be more optimized. I think they just are designed for Scaffold ETH, so that's kind of why that's how they're different. Can you navigate a conflict? That's a silly question. What VS Code extension do you recommend? Definitely the Solidity and TypeScript highlight syntaxing. I actually recommend Cursor. I don't know if everyone used Cursor yet. If you're not using Cursor, at least like a couple days of the week, try it out, and you will really, really, really start to develop a little quicker. Okay, those are good questions. Any more questions in the room? Yeah, over here.
I'm getting an address and use problem for when I run yarn chain after running it before and closing it out.
That's interesting. It sounds to me like it's still running somewhere, so maybe you have it in another terminal that you didn't notice. Double check. Maybe just do like a PS and see if you can find the binary. Are you running a Mac, yeah? Or it's Windows? Windows? Linux. Yeah, just do a PS like AUX, like this. Grep, I don't know, what is it, Foundry? Oh, you were using Foundry, right? Something like that. And see if you can find the process ID. And then try to kill. So do like a kill-9 process ID. I'm teaching you guys Linux too. Okay, cool. Yeah, try to just kill the process. That should get rid of it. Okay, let's keep going. I think we answered a couple questions. If you have a question, ask it in the app, and the next time I stop, we'll go. Okay, so we have our chain running. We have our front end running. Let's start writing a contract. We've wiped out the contract to at least a very base kind of spot. The name of this workshop is about smart contracts. So let's try to write one. Just let's hope I don't mess it up, but let's see. Okay, so what I want to do is I want to create an ERC20, but first I want to start by having access of this contract in a way that is probably the standard, okay? So we were using this kind of like, we don't want to use Open Zeppelin, we want to use Ownable. Let's see if that works. Actually, let me grab it from here because I forgot what it is. There it is. Okay, so we're going to use Ownable. Now, the beginning contract for Scaffold ETH comes with this kind of access control pattern where you have an owner of a contract, and only that owner can do certain things, right? But the standard way to do it, the easiest way to do it, is just to use Open Zeppelin Ownable. So we're going to do that. We're going to import Ownable, which is an access control contract that allows me to just take everything that's in this contract and import it by doing your contract is ownable, like this. And what that's going to do is it's going to allow me to deploy at the time of my deployment. Okay, so it wants something passed in the constructor, which I think, let's see if we can do that. I forget how we need to do it. No arguments passed. So I think it wants the owner passed here. So we can set the owner. So what I want to do is I want to use my contract address from the contract burner wallet that I have. So inside my burner wallet, so now that I've done my deployment, the script, or the smart contract's pretty much empty. I want to use this address here in the burner wallet as my owner. Okay, so I'm going to copy that, and I'm going to pass that into the arguments, which I think is what I need to do. Let's see. What is this? That should work now. Let's try to do the deploy. Let's see. Oh. Address, constructor address, initialize owner. Yeah, that should be it. Oh, I need to call. So what's interesting, I think I need to do your contract deploy. And is it ownable? frick, I'm trying to think what I need to do. It's in the constructor. Oh, yeah, you're right. Thank you very much. So it's not here, actually. It is here. Like this, right? Ah, thank you. So we do it. So like this? Oh, I got you. Okay. So owner like this? Can I do it like that?
I would say that.
Yeah.
You can take the arguments from the deployment if you want. No, it's fine.
Okay. Well, all right. That's okay. Let's actually not do the ownable stuff. Let's just focus on the actual smart contract for the ERC20. I don't want to like hold this up. Let me just redeploy those changes real quick. Okay. So the basic functionality of a token is that you have like a name for the token, you have a symbol for the token, you have a total supply of how much tokens that you want to have, and then you want to like mint that token to a particular address. And then you might want to like sell that token on a exchange or something like that. So let's try to actually do that. Let's just try to make a token. So what we'll do is we'll do a string public name, and we'll call it, I don't know. Everyone's talking about these frogs, so I'll do frogs. How many frogs do you guys have? Okay, so, and then we'll also do string public symbol equal frog, sure. And then we can also do a total supply. Let's do, 1, 1, 2, 3, 1, 2, 3, 1 million times 10 to the 18th power. So in Solidity, or I should say on Ethereum, you have this concept of decimals, right? Sorry, I spelled this wrong. What am I doing wrong here? Oh, thank you. Gosh, I'm like failing today. Okay, so you have this concept of basically decimals. So if we want to have 1 million tokens, but we also want to have the the full amount of decibels available, we want to multiply this by 10 to the 18th power. So we want to set the total supply to 1 million tokens, and then that way it can be converted down. So we have this kind of like total supply. And so we can save that and then do our deploy and kind of show what that looks like. So we do the deploy. And then when we come here, we can see that we have the variables are showing up, we have the name, we have the decimals, we have the total supply, and then we have this cool functionality here where we can like convert, sorry, it's a little hard to see, but Scaffold ETH can convert it from the standard Ether values all the way down to what it would be in 10 to the 18th power. And so we can see what the total amount of Wei is that this token is worth. But we don't have any way to, well, first of all, we haven't minted that. We have the supply, but we haven't actually transferred the value of that. And so the way that we do that with Ethereum or Solidity is we create a mapping. So we say, we want to keep track of the balances of any address that interacts with the smart contract and has some kind of like balance, transfer of balance. So we use what's called mapping. So mapping takes one variable and essentially maps it to another variable. And so in this case, we want to take in an address, so any particular address that has a balance, and we want to exactly tell how much that balance is. And we want this to be publicly available so that a user could query what their balance is. And when you do this with Solidity, you get a get function, so you can actually see what this balance is. So if we query that, so let me just save that, and then in here, we can set the balance of a particular address at the time that the contract deploys to anyone we want. So we don't want to actually send it to message.sender. I want to send it to my burner wallet, so it's here. So I'm going to come in here, copy the address, and then I'm just going to paste that in here. Cool, so let's hit send. There we go. So now we can deploy our contract. Cool. So our contract is deployed, and we can see that how much gas it took. And then if we go to Scaffold ETH now, we should see that we have this new read function, right? So we can grab this balance of this address, paste it in here, and do a read. So you can see how you just paste in the thing. It gives you this like little blocky dude, and then you can do a read. So this is how much actually tokens that we have. We can convert it by seeing exactly what that is in ETH, and then we can go back and forth. but now we don't have any way to actually like transfer the tokens around. So we probably want a way to transfer. That's the next thing that comes in a standard token. So then what we can do is write a new function. So we will do a function. Oh, gotta love AI. It just kind of does everything for you. So what this is saying that is we need to write a function that transfers by taking in a to address and an amount that we want to transfer. This should be publicly available. And then at the time that someone calls this function, you want to do a check, basically to make sure that they have enough tokens to send to another user, because otherwise they'd be double spending, right? So we just do a little, like a require statement. And then after that, we just update the balances. So we say, okay, well, the balance of the person who is calling the function. So in Solidity, you have these kind of like global variables, which message.sender is the person that is sending the transaction. So that's the user, their public key, basically. And if someone's calling the transfer function, we want to remove the amount that they're going to send. And then we want to, whoever they're actually sending it to, we update that mapping to with the amount. So here we subtract, here we increase, okay? So now we can hit save, and we can do deploy. Cool. So now we can go back to Scaffold ETH, and we can see that we have this contract. And you'll notice that every time we do a deploy, we can force a deploy by doing a yarn deploy -- reset. And you'll see the contract address up here in the top. It will change, and you'll constantly get a new contract. And so that's why we're kind of like starting over from scratch every time, because the nonce is changing on the deployment. So now we have this contract. We have a very basic ERC20. It's called Frog. The name is Frog, so it's got a total supply. I have a balance of whatever, 1 million tokens right here. So if I want to transfer some tokens now, I can say let's transfer to Vitalik.eth, and let's send him some Frog tokens, sure. 777. Now, again, we need to transact in Way. So Scaffold ETH has this really cool tool that you just click the little button, and it will multiply whatever value is in the input by 10 to the 18th power. So I click that, and that will tell me exactly how much Way that I need to call in the transaction, and then I can go ahead and hit send. And as you can see, it did this nice ENS resolution, and we can see Vitalik's photo. I'm really sad Vitalik changed his little rainbow cat, because that was a really cool one, but now it's his face. So there we go. We have send, and then here's the receipt, so we know that it was successful. And now we can come up here and query against Vitalik's address. So Vitalik.eth, and do a read. It resolved, and then now we can see that he has a balance of 777 tokens. So we've created this kind of like very basic implementation of a ERC20. So I want to show you how to do the other method. So let's actually do let's take a look at Open Zeppelin. Let's see, Open Zeppelin ERC20. Let's see if I can find it here. So you probably don't want to reinvent the wheel. Again, like we're going to try to use the, okay, this is going to tell me how I can fix the ownable thing as well. We want to probably just go ahead and use Open Zeppelin, right? So you probably want to reserve the time that you're working on your smart contract to do something new and innovative. Since ERC20 is a very, very good standard, we can just use Open Zeppelins, okay? So we can grab this here, and we can come back here, and let's just kind of like take away all this stuff we did and show how much easier it's going to be if we just use Open Zeppelin. So we'll do this, and we'll go here. So we can say your contract is ERC20, and then what we need to do is we need to pass the stuff inside of the constructor. So this is what I was not able to figure out earlier, that I don't know why I wasn't thinking about that. But with ERC20, it has a constructor, so it has its own constructor. So when you're deploying an instance of another contract, you also might have to call its constructor. So this is how we do that. We call this here. And so in this case, we wanted to do frogs and frog like this. And then here we can do _mint. So there's already a function that's available to mint tokens, okay? So instead of us writing that function or that line of code to actually like create the tokens, we can just call this mint function. Okay, so what this will do is it will do 1, 1, 2, 3, 1, 2, 3. So it's 1 million tokens times 10 to the 18th. I think we can do it like that. Let's see if that works. Yeah, there we go. Okay, now let's try to deploy again. So, and we can also probably add ownable now, I think, as well. So if we do, well, let's try to do that afterwards. Okay, so we have the ERC20. Let's deploy it. We already did. It's successful. Now if we come to Scaffold ETH, what you'll notice is we have a complete token with just a couple lines of code, as opposed before we had to like write all this different code. So we have this token that has a decimals of 18. It has a name of frogs, symbol of frogs. It's got its total supply. But what's cool is it's going to give you all the functions that come in the other contract. Okay, so since we're importing ERC20 standard, we get the allowance read function. We get the balance of that we had to write manually last time. We get the approve pattern for an ERC20, where you have to like approve the spending of your tokens before they're able to be spent. And we also get the transfer function, and we get transfer from, where we can transfer from another address to another address if we have the approval. So it's a little bit more complete, and it's a little easier to implement. So you should always look and see if there's like a standard that you can use. I always like to go to cookbook.dev. I don't know if anyone's heard of cookbook.dev, but cookbook.dev is a really good spot to find contracts that you might be thinking about creating, and so you don't have to reinvent the wheel. So if I come in here and like, let's say I want to look at ERC 721, we can do a search, and we can find different implementations. So here's a soulbound NFT, right? So if we want to do a soulbound NFT, we could come here and it's going to give us an example of what the contract should look like. Also, what's cool about here is you can download it with Scaffold ETH as well. So you can click this little icon right here, which is Scaffold, and it will basically download the entire package for you. And it's basically an entire installation of Scaffold ETH. And you can just spin up your environment with that exact contract inside of Scaffold ETH. So it's super powerful. Okay, so okay, we have this token that we've created. We used ERC20 standard. Let's just, I want to show you guys how you add another contract. So you might want to add another contract at some point because, you know, you might have a more complex application. So in this case, we have, it's called your contract. So we also might want to do like new file, and we might want to call it another contract like this, and then we can grab this entire thing, paste it in here. But let's just get rid of some of this stuff, and I don't know, this will just say like, get rid of the constructor, it's not an ERC20. We'll just do, I don't know, we'll do something like string hello equal hello world. There, I'm not sure. Okay, so we have this other contract that we want to deploy, but how do we deploy it? So we can, if you're using Hard Hat, you can come in here and create another deployment script. So what I'm going to do is take this contract and make another deploy script. So all you need to do is do a new file and do 01 underscore deploy underscore your, or I should say deploy another contract. So it's going to go in order of the leading zeros. So this one would be deploy first, this one would be deployed second. We can paste that in. We also need to update, instead of deploy your contract, we want to replace everything with another contract. So what we'll do is we'll find anything that says your contract, and we will replace with another contract. Let's see if that works. Cool. Boom. So now we're doing the exact same deploy on this contract. So now we have a new contract here that just says hello, and we have another deploy script for it that's here. It's called another contract. So we took this, copied everything, replaced everything that says your contract with another contract. Oh, I'm missing one here. There we go. Okay, now let's try to deploy that. So that should give us two contracts now. What did I do wrong? Oh, is it? Did I not do it completely? Here? Oh, thank you. Thank you. This is the best audience ever. You guys are helping me. Okay, cool. There we go. So now that should work. So basically, we have a second contract. Now what's cool about Scaffold ETH is it will show you the other contract here at the top. So we have this contract, which is our ERC20, the frog token. And then over here, we have another contract, which just has this kind of like, oh, that's weird. Where's the variable for it? Oh, it's not public. So it's private. So defaults to private. So we need to make that public. Redeploy our changes. And now we'll see this kind of like string that shows up here. There we go. Cool. So you probably are going to make a way cooler smart contract, right? You'll probably do some more interesting things. If you want to get some ideas of like smart contract stuff, I would just, like I said, look through Cookbook Dev to see what kind of other contracts are available for you to use. If you're trying to like create a new contract, it just takes time to kind of like innovate and do stuff like that. If you're new to Solidity, again, you should go through Solidity by example and just understand how things work. There's also, I don't think I talked about it, but there's a great set of YouTube videos. I personally like to learn by videos. So if you go to the Smart Contract Programmers YouTube, which is this guy, there's a bunch of playlists that are available for different things. And there's one just for Solidity 0.5 examples, and then there's another playlist here for Solidity 0.8. So definitely recommend watching both of those. I think most of the time that they might be embedded in here sometimes. No, so you kind of have to look them up. I think he needs to like put links so it's easier for people, but yeah, for the most part, you can find for all of these examples that are on the left, you can find related videos that explain in like detail of what each line of code does and why. He's a really good teacher. Okay, so let's pretend that we kind of have this contract. First of all, I'll stop for a second and see if anyone has questions, and then if not, what we'll do is we'll try to deploy this contract, okay, to a testnet. So show of hands if anyone's stuck or has a question so far. Anybody? Good? Bueller? Okay. Let's do this. All right, let me just make sure there's no questions here on this thing. And then what we'll do is we're going to try to deploy this contract to a public testnet, okay? So, no questions. Looks good. Okay, so the first thing is that we don't want to use the private keys that are stored inside of the different chains. So we have Hardhat or we have Foundry. They come with private keys and public keys. You don't want to use that when you move into a testnet. So the first thing that we actually need to do is take our implementation and we need to generate a private key, okay, our own private key. So Scaffold ETH actually has a function for that. So you can do yarn generate. So depending on which chain you're using, if you're using Hardhat, it's going to just create a .env file with your private key inside of that file. That's what you should keep secret, obviously. And then it's going to give you your public key here, okay? You can also do yarn account. And what this is going to do is it's going to give you a QR code that you could scan to basically fund that account. So I'm going to go ahead and do that. I'm going to use my Punk wallet to send some Sepolia ETH here. We'll deploy the Sepolia. So I can, I have Scaffold ETH was also used to build punkwallet.io. So if you guys haven't seen that, it's really cool. You can have this burner wallet inside your browser and you can fund it and it's stored in storage, like the private key. So it's not good for public stuff. I wouldn't recommend it, but it's good for like test nets. So we have this ability to scan the QR code with the camera. And then I can just send some ETH to this deployer account. So I'll send in 0.1 ETH, sure. Okay, so I just sent that ETH. We'll give it a second. So now if I do yarn account, oh, is there a question? Sorry. I'm going to use Sepolia. Yeah, just because Sepolia is easy. Also, base Sepolia is pretty easy. I mean, shoot, you can deploy to base these days pretty cheap. So, but yeah, let's see. It might take a second for the thing to go through. It takes maybe like 10 seconds. Let's see. So if you do yarn account, it goes out and checks the balances. Did it actually go? I hope it did. That's weird. I'm me just make sure that I got the address right. I don't think it got, yeah, that's the right address. Let me just try sending a little bit more. Okay, your own account. Okay, let's look at this. Let's look at the scan. Sepolia, Etherscan, and we'll put in this address and let's see if it has a balance. It could be that the Yarn account is not showing us the balance, but it actually has one. Yeah, so it has some ETH. It has 0.2 ETH. So I funded it from my phone, send it over. So now what I'm going to do is I have a deployer key now, private key. So what I can do is deploy my contract. So there's a couple ways you can deploy your contract. With Hardhat, you go into the Hardhat directory, and there's a Hardhat config. And inside of here, we have a configuration of what deployment we want to use. So in this case, the default network is currently set to localhost. So we've been like doing everything locally, but now we want to put it on Sepolia. So we're going to replace this with Sepolia, like that, hit save. And then now we're going to go ahead and do a deploy using Sepolia. So we could also, if we didn't want to update the config, we could also do -- network, and you can just type Sepolia as well. So it's either or, right? So let's just go ahead and do a deploy. So what this is going to do is it's going to take the contracts, try to compile it, which it didn't need to, and now it's going to propose a transaction and then try to basically do a contract creation. So it's a little slower, obviously. So we got it deploying right now. What did I do? Insufficient funds. Okay, Sepolia is expensive right now. Okay, let's try to send some more funds, let's say. It's probably because of the ERC20 contract. Let's do 0.25, sure. It's Sepolia ETH. We have lots of it, so. Yarn accounts. Let's try. Okay, let's try now. Yarn deploy. Oh, no. Insufficient funds. Oh my gosh, it's so expensive. All right, I'm just going to send a lot of ETH. I'm just going to YOLO like 1 ETH. Let's do it. Oh, I don't have that much ETH on here. Okay, I got to get it from somewhere else. Let's do right here. Let's do here. Let's grab the address. Sorry. Where's the address at? Boom. I'm just going to send some ETH from this other wallet that I have, which has a lot more. Okay. Okay, so we do send, paste in that address, and let's send, I don't know, ETH. We want to send, should send like 2, sure. What? How do I not have that many funds? Oh, thank you. That wouldn't have been good. Yeah, where's Sepolia at?
First one.
Did I go by it? Where's Sepolia?
It's in the bottom. Show test
Oh, yeah,
window.
thank you. It's so weird because I have like some test nets in the top. There we go, and that's a lot more. Okay, let's try sending that to there. Okay.
In the log is showing balance 0. Are you sure you passed the accounts in the Sepolia network config? The balance is shown 0. I think it's
Oh,
a wrong
yeah.
account.
Huh.
Because 0.2 is way more enough to deploy
Yeah,
a
that's
simple contract.
That's weird. Then maybe it's
I
something.
mean, in the hard hat config file.
Oh, in the hard drive config, yeah.
So Sepolia accounts. Sepolia config.
Sepolia config.
Default network Sepolia. Yeah, networks. What's the private key?
Yeah, it should be using deployer private key. That should be right.
I think accounts you have to pass -- network Sepolia and see what's the price. When you did Yarn account, I guess.
Yeah. Let me just double check our account. You said this. Yeah.
Doesn't look like it. Yeah.
What's that? Oh, you think? Oh, you think I'm doing? I need to do dash dash network flag here, like that? Oh, yeah, but yeah. But I just looked on Etherscan. I just looked on Etherscan and I thought it said that I do though. Right? If we go here. I have
nice.
balance. Yeah, so it seems like it's checking. Let me just try this. Let me see if this will work. Something weird's going on.
Oh, can you just import the private key into MetaMask and confirm the wallet address? I think it's two different accounts.
Yeah.
The .nl, you have the private key there, right?
Yeah.
Yeah.
What is it? Let's see, packages, hardhat.env, I think.
No. Accounts.
Yeah, accounts, thank you. All right, let's see, add accounts, import accounts, private key, boom. So that works.
Okay.
Yeah, it's weird, yeah, it's not.
Oh, it's weird, yeah.
Yeah, I don't know, it's something weird's going on. Unless it's something with the RPC provider. It might be that, actually.
Yeah.
Because I'm using the public RPC, but. Okay. Well, okay. Yeah, I'm not sure what's going on. It's very weird. Let me just double check the config real quick. Default network Sepolia. Default. I don't need to change anything here, right? For the deployer now. Should work. This is for named accounts, so that should be like what it's using for local stuff, but for Sepolia.
Maybe you can try OP Sepolia.
Do what?
OP Sepolia.
Oh, like another network? I don't think that's what it is. Because he's right, it does say 0 here, balance 0. So it's almost like it's not pointing at the right network, or it's the RPC endpoint is wrong and it's just defaulting here. Like maybe this needs to change to Alchemy. Let me try just doing that real quick. So alchemy.com, let's see. Did I spell it right? No. There we
Or you can take another RPC from chain list.
go. Yeah. Let me just try this real quick. The demo gods do not like me today. Okay. Come on. There we go. Okay, apps. Let's use this test one. Sepolia. I wonder if this will work if I just use this one. Now I'm just curious more than anything.
Oh, can you go to the packages directly and try manually deploying it, like packages/hardhats?
Yeah, I'd prefer not to though.
It's using toolbox, so the deploy
Yeah.
function is there.
Hmm. Oh, this is mainnet, but where's the pulley at? There we go. Let's try this. Sorry guys, sorry we're having issues. This is unexpected. The good thing is there's like a billion videos of deploying. Oh yeah, yeah, well, let's just try to deploy. Let's see if it works. There it goes. So it's the RPC provider, man. We got to fix that in Scaffold ETH. We just changed the RPC provider, and because we were having issues with Alchemy blacklisting our API key. Cool, it's working now. All right. Woo, that's fun. All right, cool. So we're going to deploy our contract now. As you can see, it deployed successfully. It tells us how much gas we got. We have the TypeScript definitions were created. Now, what we want to do is change our front end. So let's get rid of this. We want to change our front end to also point to Sepolia now. We're still using Hardhat. So we're going to go into the contracts folder. Or sorry, the Next.js folder. We haven't really touched Next.js. We didn't do any front-end stuff, but there's one config that you're probably going to want to know, and that is the scaffold config.ts. So this has the chains directory, the target network variable, and we can do chains.sepolia. All these are going to be available because it's obviously TypeScript, but we're going to do Sepolia. We can also change the polling interval. We can get rid of like a 0. And we could also put in an API key for Alchemy if we wanted here as well. If you have your own API key, you should put it in. Okay, now let's go ahead and load up Scaffold ETH again. Now you'll notice we got kicked out of the wallet. So first of all, let's take a look at the contracts. These are both going to be unverified. I think I need to actually update the RPC provider too. I think the RPC is completely messed. So let me put my API key in and see if that works, because it's already freaking out. Okay, let's go to API. Let's copy the key, and let's also put that in here. Save it, and then you might need to restart Next.js if you do that. Let's try it again. Okay, so now we're on Sepolia. We have our contract deployed on Sepolia here, so we can see that. We can also see that we got kicked out of the burner wallet. So we don't want to use burner wallets on a test net because they're stored in local storage, so it's not really the most secure way. So we now need to use MetaMask, right? So we're going to connect to MetaMask, hit next, confirm. It wants us to switch networks. We did. And now we're on Sepolia. I have a balance in my address. I have another contract, which is just the hello world, and then I have this year contract, which is an ERC20, and it should have a minted supply of my burner wallet, but, oh, you know what, I don't know who I minted it to. Let's see. Let's take a look at the deploy script. What did I do? Your contract, deploy your contract. Sorry, where's the contract at? Your contract. Oh, I sent it to the hard hat address. That's okay. Either way, we're not going to actually do a test anyways, but I just want to show that we've deployed successfully here, and we have this kind of like read functionality. So now we should be able to see who deployed the contract. So if we come here, we can click on the address, and we can see that here was when the transaction was done 3 minutes ago from this contract creation, which is here. And yeah, we can also see that it's not verified. So the next thing you probably want to do is verify your contract. So what we can do is come over here and this is going to be fun. Let's see if it works. Yarn verify -- network Sepolia. So that's going to take the contracts and basically like figure out what the bytecode should look like based on what's on on chain versus sending the ABI to Etherscan, I think is what it does, and it's going to verify it. So there we go. Now it's verified. I think because I put my API key in, it's good. So it's going to be good, yeah. So there we go. That one's verified. This one should be verified now as well. So now if we come back to Etherscan, we can hit refresh, and that contract will have a green check mark, okay? So that's definitely a cool feature of Scaffolded ETH because you want to verify your contract, especially if you want to like use the graph or some other tool that needs the ABI. That way the ABI will be publicly available. Okay, cool. So now we have our contract that was deployed. It's successful. We could basically try to like interact with it. Let's just see if we can do that. See, where's it at? Here we go. So we can do like balance of vitalik.eth. It's going to be empty. Yeah, cool. But yeah, we can see that both the contracts are deployed. So cool. All right, what else do we want to show off? We also might want to deploy this somewhere for like testing with like other users, like you want to actually send the URL to someone. So the next thing is you probably want to ship this front end. There's a command for that with Vercel. So we can easily ship the application by doing a yarn Vercel colon YOLO -- prod, which is the most awesome yarn command ever. But what's going to do is it's going to ask you to sign into Vercel. So you can sign in with GitHub, or you can sign in with like basically like an OAuth hook to Vercel. And then it's going to ask you if you want to set up and deploy. We say yes. It's going to ask you if you want to use an existing scope of projects or what your project scope is. So in mine, it's Kevin Jones Creates. It found our project. I want to create a new one. So I'm going to say no. And then I'm going to not link it to an existing project. I am going to do it to a new one. So I'll just do this, I don't know, Devcon demo. Enter. It asks me where the code is located. I can just hit enter. And now it's going to set up the project. So what it's going to do is like create the config file for Vercel and then build it and make sure it builds properly. Set the ports, all that stuff like that. And then it's going to ask if you want to modify the changes. You say no. And then now you can deploy it. So it's going to push it out here. So if we come to this URL now, it takes a second to deploy. We can come here, paste that in. And oh, I need to be in the right browser session, which is a little annoying. So by default, Vercel will make it private. So you need to authenticate and actually sign in to Vercel. But as you can see here, it's building, so that will take a second. So it's already kind of transferred all the files to Vercel. And now Vercel is running some automation and basically creating a page for me. So at this point, then we'll have this kind of deployed application. We didn't really do any front-end code, but like I said, Edda tomorrow, she will do a much further demo and show you how to use the hooks and the components, reading and writing from your contract, and stuff like that. Okay, cool. I want to talk about one more thing. First of all, let's stop for a second. Sorry about the hiccups. I'm glad that we were actually able to deploy the contract. But are there any questions up until this point that I can answer? Yep. Yeah. Network not supported. Did you do yarn verified -- network?
Yep.
And you typed Sepolia?
No, I use base.
Base, it's base mainnet maybe. So if we go into the hard hat config, so the question was, he was trying to do his verification, but it said network not found. So I think what's going on probably is inside of the hard hat config, we can take a look at what base is called. So I think it's called base, oh, maybe it is called base, yeah.
Base, yeah. So basically, the error message says network with Trinity 8453 not supported. You can specify the URL manually via API URL.
Oh, maybe you can't verify contracts. It's possible that you can't verify contracts for base, possibly. So there might be a manual URL you can pass with the API key using base scan or whatever it's called. So there's probably a way to do it. You need to go to the base block explorer and go to the verification for that contract, and it will tell you how to do it. Cool. Any other questions? Yep. Uh-huh. Let's get you a mic first.
Yes, thank you. I would like to know where to specify the API key for the Block Explorer, because to verify, what I read is that we need the Block Explorer API key. So in the structure of the project, where do we specify this key?
Yeah, that's a good question. So I think there's a, let's see if I can do this, yarn verify -- help maybe. I don't know if that's going to work, but there's a way to do -- API key. So you can say yarn verify -- API key, and you can also specify the URL manually. So yeah, it's using hard hat verify. So if you want to look up the documentation for hard hat verify, that's exactly what it uses. At least what my implementation is. If you're using Foundry, it's going to be different. I'm not sure what they use.
And when you verify, does it verify all the contracts?
Yeah.
Or?
Yes.
Okay.
Yeah, like scaffold ETH is not like multi-chain out of the box, so it's just going to assume that you want to verify all of the contracts in that project. If they're already verified, it will just skip them. Yeah. Another question over here.
So basically, Scaffold is for NFTs and staking apps. Assuming I would like to do like a computation and add it to a smart contract, if I'm using, I don't know, graph computing or something. Is this possible with Scaffold ETH? Or is this more for like staking apps and NFTs?
I mean, you can write any EVM smart contract with Scaffold ETH. So if you want to do that inside of the smart contract, then yeah, you can do whatever you need. Any kind of smart contract logic, anything you can write in Solidity, you could write with Scaffold ETH, right?
But is it made for that, or is it made for the examples made on speedrun Ethereum? Is it made for computation actually, or was it made more for like dApps like staking and so on?
Yeah, it's made more for dApps. It's not really made for like decentralized compute aspect stuff. Like it's not a, I mean, yeah, I'm not sure to answer how to answer it, but basically it's just an Ethereum, tool for building and writing smart contracts. So anything with Solidity, but dApps, yeah, cool. We can talk after if you have more questions. Yep, cool. Any other questions? Sorry, it's hard to see you guys too. I'm like blinded. Okay, cool. I don't think anyone else has questions. No. Cool. All right, now what we're going to do next is, since we have just a little bit more time, I just want to talk about the extension system. Looks like we got like, not sure how long, maybe like 20 minutes, 15 minutes or something. So let's talk about extensions. If you go to the Scaffold ETH website, scaffoldeth.io, and you go to docs, and you come down here, there's a section called extensions. So I talked about this yesterday. You can probably find the talk available later on after they upload them, where I actually show off an extension. I probably don't have time for that, but there's a list of available extensions here. One of the extensions that I would recommend you check out is the subgraph one, because it has the graph implementation. There's also other ones like on-chain kit and different EIPs, as well as Ponder. And then you can also create your own extension. So it's pretty cool if you are a developer and you want to like showcase Scaffold ETH, how it integrates with something. You can build out a extension and add the functionality you want. And then every time you want to create a new project, you can just use that extensions framework to start at that point. So really powerful. And also, if you go to scaffoldeth.io and you scroll down, there is a section that is all about components. And there's an extension guide here. And then we have the check out all the available extensions. So you can do it, like I said before, you can do the -e flag, and you can pass in a URL on GitHub. And then here we can get a list of extensions. So here's the subgraph one, EIP, Ponder, ERC20, on-chain kit. There's a bunch of other third-party ones that have been created. So we'd love to see what you guys build. There's a chain link one. So if there's something you're trying to do with another integration, you should always check here. There's an Fleek extension, which is really cool. You can deploy to Fleek. So if we didn't want to deploy to Vercel, we might want to deploy to Fleek. You can use that. So yeah, check these out. Highly recommend them. And those are going to be a good point to start. And then also, speedrun Ethereum. So I just want to talk about speedrun Ethereum a little bit more. So speedrun Ethereum, when you first come here, you can connect your wallet, and it's going to create a profile for you with your address. It generates this little like punk. And then you can come in here and go to the main speedrun Ethereum page. Oh, let me reconnect. And you can start a quest. So like the very first one is very, very simple. So I guess my recommendation for anyone that's new to Ethereum, try to do this challenge, because all you have to do is do the first part of what I did, set up Scaffold ETH, and it's going to let you create this kind of like NFT tool. It's like just an NFT with these little like kind of fun characters, and it's going to walk you through everything you need to do. So it tells you what you need to install. It tells you how to get the repository, go into the repository, check out a specific branch. So it's a little different than just the standard Scaffold ETH installation, because it is a GitHub repo right here. And so each particular branch is the challenge. So if we go to it, we can show what that looks like here. Let me go. Oh, did I type it in wrong? That's weird. Huh. That's weird. Okay, let me just check the Scaffold ETH website. What's it called? It's SE2 challenges. So we go to repositories, SE2. Huh, they renamed the repository. Okay. There it is. Okay. So this is the challenges repository. If you click here on main, you can see all the challenges here. So 0 through all the way down to 7, SVG NFT. So yeah, you can just choose that repository, and then each one is going to have all of the instructions as well here. So you can do it either way, but when you're ready to actually submit your progress, you come all the way to the bottom, and you hit Submit Challenge. And it's going to ask you where you deployed it. So earlier, I showed you guys how to deploy to Vercel, which we should have done, actually. Let's see if it went through successfully. Oh, shoot, did I lose it? I had it here. I don't know where it went. Anyways, it will give you the URL that I typed in and put in. So you need to put that URL right here. And then you also need to put the contract address that is verified on Etherscan. So basically, it's going to ask you to deploy everything to Sepolia. So you just need to put that Sepolia Etherscan. The contract also needs to be verified, because we do some automation to like verify your contract. So I would recommend everyone try to do at least challenge 0 before the end of the week. It literally will take you like 20 minutes to do. And then that will kind of set you up to start learning a little bit more. And then you can learn, again, how to do like staking. So this will go into like how you stake. You do like a token staking. This is how you do like a token vendor, where you can actually like deposit one asset and get back another. And then again, this talks about randomness, and then eventually you build like a DEX, which is a lot more complicated, but you learn a lot, because then you start to learn about slippage and stuff like that, and understand how a DEX works, decentralized exchange. Cool. Okay, cool. I think we're gonna probably end a little early unless there's questions. Does anyone have questions at all? Yep, question here.
Yes, I would like to know, when you submit your challenge, is it verified by a human being behind the scene, or is it automatic? Do I need, for example, to send a video to show that my contract respects the specification?
Yeah, so it's all automated pretty much. We just, the way we do it is the first few challenges we do automated, so we just get the the Etherscan address, and then we pull down the source code and then test it. So we run like a test. So each challenge has a test. So if the hard hat test passes on your local machine, it's going to pass on the automation, so we verify it. When it gets down to the decks, it's done all manually. So we actually look at the code and make sure that it's good. You don't need to do a video, though. And especially these last few, like the state channel, multi-sig, and SVG, those are also all manual, pretty much. Yeah. What other questions we have? I think I saw another hand, but I don't know where it was. No? No? Cool. Awesome. Thank you guys so much for coming, and I hope you guys learned something and it was useful. Thank you.
10 seconds. Okay, good. Right. First thing, thank you for coming to this workshop. My name is Remy, and today we are going to talk about ZK and identities, and more precisely about ZK and passports. So this workshop is going to be split in two parts. First, I am going to present you open passports, and in the second time, Michael and Theo are going to present you ZK Passport, which is another ZK Passport project. Sweet. So back 1 year ago, we realized that the identity market is really inefficient because it's actually not private nor secure. Right now, if you want to prove your identity online, most of the time you are going to go through the whole KYC process, which is actually not needed. And what's going to happen is you are going to take a picture of your ID documents and send it to the application, maybe do a proof of liveliness, so take a picture of you, maybe move the head a bit around to be sure that it's really you, and send it to the application too. And then you are going to pray. You are going to pray that this information is kept secure and that there will be no data leak. And spoiler, there is, and there is so many. Like a massive one just happened 2 weeks ago in France, for example. Also, it's not even secure from the point of view of the application, because a picture of an ID document or proof of liveliness is proofable so easily using generative AI, which is not good at all. And what's even more stupid is that when you do traditional KYC, you give all your information, which is most of the time not needed. You would like to give some kind of more granular information about yourself, such as proof that you are above a certain age or that you are part of a specific country, without revealing anything else. So what can we do? Fortunately for us, the International Civil Aviation Organization already built a nice tool on which we can piggyback on, which is the electronic passport. It's issued in 172 countries and carry on an electronic chip with inside a bunch of data about you, which is signed by the issuer country. So this logo is the one of the e-passports. If you got this one on yours, it's obviously an electronic one. And these are pretty cool because as the data is signed inside of it, that means that we can verify that inside the ZK proof. And by doing so, we can already target several issues related to identity. The first one is, of course, the Sybil resistance. How to prove that it's a human who's behind an action, a vote, a tweet, or anything else. The second one is the selective disclosure. I talked a bit about this one before. You may want to prove something really specific about yourself without revealing anything else. The last one is the compliance. As you can perform computation inside zero-knowledge circuits, you can actually prove that you are not part of a list of countries or that you are not part of the OFAC list without revealing anything else. So how can we do that, for example? So the OFAC list is the list of the people that US companies are forbidden to deal with, so mostly terrorists. And you can actually parse this OFAC list into a sparse Merkle tree, and then you can do a proof of non-inclusion of your name and surname inside this sparse Merkle tree. Sweet. Also, as you are going to verify a signature, ZK proof of passport are totally unforgeable, which is 1 point for crypto. You can't actually spoof crypto, that's not possible. Sweet. So now let's take a look at the passports. So in the passport, there is different data groups. For example, the DG1 is mostly the information that is contained in the main page of your passport. The DG2 is the image which is signed, which is pretty cool too, because we could imagine to do some kind of ZK machine learning tricks to do the proof of liveliness with the phone. That could be really cool. So these data groups are hashed, concatenated together, and hashed again. And the final result is signed by the issuer country. Or more precisely, it is signed by the document signing certificate, which is an intermediary certificate that can sign up to 100K passports. And this document signing certificate is signed by the country signing certificate authority, which rotates every 3 to 5 years upon the country. And those certificates are actually issued in public registries maintained by the International Civil Aviation Organization. So that's actually why it's so easy to verify passports, because we have access to the public keys. Okay, I kind of lied when I said that it was that easy, because countries didn't agree on one signature algorithm and hash function. So this is all the primitives that are currently available in the passport signatures. There is even another country such as Germany that use 4 different ones, including ECDSA with SHA-1, which is quite kind of surprising. Yeah, okay, so if you want to see if Open Passports currently support your country, you can refer to this map. You can go to map.openpassport.app or scan this QR code. Basically, the countries in dark green are the ones that are currently supported. The one in green are the one issuing e-passports. We should support them soon. And yeah, if you pass the mouse on the country, okay, so that's a static screenshot, but if you go on the screen and you pass the mouse on your country, you will be able to see which kind of signature algorithm and hash function your country is currently using. Sweet. So my guess is that it's time for demo time. Like that, you will have a better idea of what we are doing. All right, so what's going to happen when you need to prove your identity using Open Passports is that you are going to scan the QR code. Scan this QR code. If you don't have the mobile application, it's going to install it. And then the first step will be to scan your passports, or for demos like this one, you can actually generate a mock passport inside the application. So if you don't have the passport on you, that's fine. You can generate one. So let's do this, because obviously I don't want to show my passport in front of everyone. So sweet. That's my new identity. Okay, so next step, when you onboarded the passport, you just have to scan the QR code once again, and that's it. On the phone, there is written, Rainbow Chaser is requesting to prove you own a valid passport, which means that I'm going to generate a ZK proof and not disclose any information besides the fact that I own a valid passport. That's it. So let's do it. Let's generate the ZK proof. There is a WebSocket connection between the front end and the mobile application. For the technical side, we are using Grow16 and SciComm now. We are currently moving to Noir. And the proving time is around 8 seconds with SciComm. So sweet, the proof has been verified. All right, now let's say that you're an application that want to gatekeep the contents to users that are above a certain age. Let's see how you can actually do that technically using Open Passports. So you are going to use a really straightforward flow, because we are in Web 2, we are off-chain, so it's going to be pretty easy. So what you're going to do is first, obviously, generate a proof of passport, and by that I mean verify the integrity of the data, verify the signature of the passports, and disclose the fact that you are older than 18 years old. And along with that, you are going to send the document signing certificate to the application. Like that, the application will be able to verify that these document signing certificates have been signed by one of the country signing certificate authority. So, technically, what you're going to do in the front end is import OpenPassport/core and instantiate OpenPassport verifier class. So what you just have to do is to declare a scope, which is basically just an app ID, and then the mode that you want to use. So in our case, we are off-chain, so let's use proof off-chain. Right. You will also need to set the minimum age to 18 and exclude countries like Germany for absolutely no reason. I'm sorry about that. Okay, so this is the information you can work with using Open Passport right now. We are going to add more of them. Right now you can deal with age, so gatekeep on age. You can use nationality, so gatekeep. So you can require user to be part of a specific country, require them to be not part of a country list, or ask them to disclose their nationality. And you can also ask them to generate a proof that they are not part of the OFAC list. Right, so once the first class instantiated, what you want to do is generating a QR code. And for that, you just have to import Open Passport QR code from Open Passport QR codes. That's a React component, and pass the Open Passport verifier that you just instantiated before inside this component. And that's it. The last thing you want to do is in the onSuccess callback function, you want to write some code to send the attestation to the backend to verify the proof in the backend too. Okay, so we saw that before. Right. So I told you that the connection between the phone and the computer is done using a WebSocket server. By default, you can use the one of Open Passport, but if you want to use your own, we actually provide you a WebSocket repository on GitHub. You just have like to clone it, and to start it, it's pretty easy. For the backend, it's also really easy. You just have to, one more time, instantiate the same Open Passport verifier class with the same scope and the same circuits, which is still proof of chain. And to verify the attestation, you just have to call Open Passport verifier.verify and verify the attestation. And that's it. Like that, you know if the proof is verified. Okay. Now, let's say that you have a DeFi application, so you want to use the same flow, but this time on-chain. It's going to be a little bit different because you can't actually send the document signing certificate to the DApp because a document signing certificate is too big to pass in the call data, right? So now you want to use ZK proof for the Sync and Nest too. So what you're going to do is to send this document signing certificate to a remote prover. We actually need to do that because document signing certificates are most of the time RSA with 4,000 kbits length. So it's actually take too much time on client-side proving, but it's not disclosing any personal information. So you send this to a remote prover, it's going to send you back a DSC proof, and you are going to send to the DApp in the call data the passport proof and the DSC proof. So if you want to run, once again, there is a modal prover that we allow you to use, the Open Passport one. But if you want to run your own, you can. It's pretty easy. You just have like to run to fork the code and to run it. That's it. Right. So this time, what you want to do in the front end, it's pretty much the same actually. The only difference is you want to change off-chain for on-chain. And as we are in DeFi, we want to enable OFAC check because we don't want terrorists to use our application, and exclude some countries such as Iran. There is typing, so if you just type the I letter, it will propose you directly all the countries. Sweet. And for the QR code, it's pretty much the same. All right. Now. It's time for Nico to present you how you can verify this proof on-chain using our smart contract SDK.
Okay. Thank you. Hi, my name is Nico. I'm mostly working for a contract SDK at the Open Passport, and I will explain like how to integrate the Open Passport contract to your smart contract. So like the smart contract, you can do pretty much the same thing what you did on the off-chain. So like you can reveal, like you can generate a proof which reveals like nationalities, like age, and then you can reveal it to the on-chain. So first, how to integrate our contract. So since the passport has like so many like signature algorithms, and we need to have like a different kind of verifiers for each algorithm. So like there is so firstly, like we generate like a verifier, the gross 16 verifiers for each signature algorithm, and then we will like manage in the generic verifier. And like generic verifier is kind of handle like what kind of proof is be like verified on like what kind of smart contract. And also like we also have a open password verifier. Open password verifier is basically doing like data formatting or something. So this blue part is like handled by us, like it's managed by us. Like we're gonna update and we're gonna add more verifiers to it. And what you need to do is like just import open password verifier to your smart contract. And how you do it is like this. So like firstly, like you need to import an interface of our open password verifier. It's easy. You can install. It's already published as an npm package, and like define your like open password verifier instance, and like set your address on the constructor or whatever. Like not only the constructor, but you can set our open password verifier address to your smart contract. All right, and then like after you integrate our smart contract, I will explain how to call the smart contract. So like this is a graph. So like this on the right side, this is like an input. What you need to input to have when you call the smart contract, and the left side is like the function name when you call the smart contract. And I will say at the first, I will explain the blue part. So the currently like our open password circuit is like we're gonna we verified all the DG1 like data, and we're gonna put like some kind of zero mask for like which we don't want to reveal the data. So like only the byte data which want to reveal is coming it can be like a public value, and we also need to format the a byte data into our readable data into string or into uint, and then we need to do those kind of formatting our executions. And anyways, your proof, your hidden data is already hidden, so it's 0 byte. But to reduce the gas cost on the on-chain, I recommend you to choose what kind of data you want to reveal, and you choose you should set the selectors what your attribute you want to reveal. So firstly, you should define the uint 256 array named selectors, and then you just put what you want to reveal. So so those open password attribute selector is already defined. It's also already defined in the library, and you will choose what your data you want to reveal. And then also there is also combined attribute selectors functions, and you call this uint 256 array, and you generate combined selectors. So yeah, after you generate combined selectors, you can actually reveal the data from the passport. And then this is a red part. So after you get the combined selectors, you can call the open password verifier dot verifier and verify and dot and disclose attributes, and you can call the attestation and combine the selectors, and you will get the passport attribute, and you will get for example, if you want to get a nationality, you can call was open passport attributes dot nationality. All right, so
yes, thank you, Nico.
All right.
Now, let's take another example, voting. In this case, you want to target some maximum privacy preserving. You want to have the biggest anonymity sets and have actually no way of linking your nullifier with what action you are going to do and with the proof you want to send. So let me explain that. When you generate a proof of passports, you have to have a nullifier. And this nullifier has to be generated deterministically on your passport data. But for use cases that requires a really, really strong privacy, you need to hide this nullifier because maybe some countries actually keep the passport data, and it means that country could actually reforge that nullifier. So to avoid that, what you can actually do using Open Passports is to use a two-time flow. So first you are going to register to a commitment Merkle tree, and in the second time you are going to reuse these commitments, and this time do a proof of inclusion of your commitment in the commitment Merkle tree. And now you can disclose whatever data that you want, and there is actually no way of linking the final proof with your initial deterministic nullifier. So this flow is the same either you want to do it on-chain or off-chain. So as I said, the first step is send a passport proof. With only a commitment, you don't disclose anything and your initial nullifier. You want also to generate a DSC proof and to verify that inside a commitment Merkle tree. So this commitment Merkle tree can be either on-chain or off-chain. If you want to do it on-chain for doing stuff such as a gated tornado cache, for example, that you could gate on the fact that people are not on the OFAC list, or just to be able to nullify people, you can just use the Open Passport smart contracts library, SDK. And there is this Open Passport Merkle tree reader repository that will allow you to listen the blockchain, listen all the events, and reconstruct the Merkle tree on an AWS instance, for example, of whatever. Sweet. And if you want to do this off-chain, this repository allows you still to run everything off-chain just with TypeScript code. So it can verify the proof, create a Merkle tree, store the value inside, and you will be able to call it to retrieve the whole tree. Sweet. So what we did also for Devcon is the cursive exhibition. And for that, we create a little game which is known as Steal the Flag. So this game is using Open Passport, of course, and it's pretty simple. What you want to do in this game is to steal the flag that is displayed on screen. Right now there is no flag because the game didn't start it, but if one of you scan this QR code and generate a proof of passport, he would be able to replace the background with its country flag. So let's do it. Okay, so now the application tells me that Open Passport, I'm not sharing my screen anymore, but what it's saying is basically just that Open Passport is requiring me to disclose the country of my passport, and that's it. So let's generate this proof. Once again, it's using WebSocket, so yeah, I think there is, okay, that's fine. And that's it. It's also playing your national anthem, and the counter is starting for the Bahamas. And by the end of the con, we will elect the winner of this small experiment. Sweet. So, thanks for your attention. That's the end of this presentation. Here is the QR code that links to the GitHub repository. You can also try by yourself the Open Passport Playground if you want to try the whole flow. As I said before, if you don't have your passport, that's not a big deal because you can generate one inside the application. So try it, give us your feedback because it's so valuable. And yeah, thank you for your time, and I would be happy to answer to your questions. Florence.
All right. Any questions? There's one here, yeah?
Oh, yes, please.
I can also repeat it.
So why, if this is like open source and we have everything available, why aren't all the countries supported already?
Do you mean like why are not all the countries supported in Open Passport right now? Very good question. So there's a lot of different identity systems in different countries, and most of the time when it's a national ID, like an ID card, it only has one signature algorithm. But the thing is that passports are such a wide specification that is used by many different countries that can also have each of them their own security preferences. The specs are kind of vague actually, and so there's many different signature algorithms that many different countries use. So if you go on map.openpassport.app, you'll see a detailed map of all of the different countries, which ones are supported right now, and which signature algorithm each of them uses. So right now we support a lot of them, like most of Europe, the US for instance, because it's the most common signature algorithms. But there are some countries, okay, I won't name them, but maybe Austria, or maybe Germany, or maybe Iran. It's
I think we can name them. Oh, maybe it's display on screen. Oh no, the screen is not showing anymore.
They require a bit more work because they have they used a lot of different signature algorithms, like RSA with multiple exponents. So it's just a bit more work. But I think in less than a few months, we can confidently say that we can basically support the whole world. All right, any questions?
Hello. I had two questions. The first being Open Passport, as I see on the website, is mostly proof of personhood, right? So we have other solutions working like World ID, who are working with the similar solutions like proof of personhood and civil resistance. So the first question would be, how is this a better solution than that? The second part being, so with Open Passport, we are generating ZK proofs of passport, basically the user. So in order to have this a global acceptance, we would need to have government involved in this or not, for the ZK proofs to be used everywhere, the ones that are generated using Open Passport?
So two very good questions. The first one is, how is that different from World ID? So World ID is what World is doing. I guess it was called WorldScan before, now it's World. So I think what the work that World is doing is also quite important because they're trying to tackle civil resistance at the biometric level. The trade-offs here with what we're doing is a bit different because World, there's a, if they can actually make the thing work and ship their hardware all over the world and everybody gets their iris scanned and everything, it could definitely be a very good system because then it does not rely on states. So we don't even have this trust assumption of passports or ID cards. But it's quite hard to execute on. There's a lot of different attack vectors on the hardware, especially now with the new orb that can be managed by anybody even without an operator. And they also have to ship it everywhere. It's not clear if everybody can have access to an orb. So we also chat a lot with them. We support a lot what they're doing. They're also supporting us. But I think the trade-offs here are a bit different. And with this kind of system, just like with what Anandar is working on, and we're planning on integrating Adar 2 in this, we can have we can support a lot more people a lot faster, basically, because people just need their phones. The other question, which was about do we need governments to collaborate with this? The really great part about this is that passports are already deployed, right? And the public keys are already public, unlike international registries. So we don't really need to ask countries, which is kind of great. There are some identity systems, not passports, but others, in which the public keys are not public, and so we need to actually ask the countries. So for instance, Nico worked on Mind-Number cards, which are the identity cards of Japan, and they need to ask for the government for an API key to check that the people's cards are actual cards. They don't have all the public keys available, but we have them. So we don't really need to, we can just bootstrap on what the government's already created. Of course, if we could have better communication with them, we could also have them have better standards, already have selective disclosure directly in passports, but it's very long processes, so we can go faster by doing this.
Okay, that sounds good. The other question that just came in my mind is like how will you handle like the fake passports that people generate? Like we have seen incidents where people have like 5 passports generated that are fake, basically. Does Open Passport has something to handle that situations?
Good question. So what I really like about this is that today most of KYC works on just you send a photo of your passport. Oh yeah, this is really bad. First because of the data is stored, and so if it's leaked, like all of your private data gets leaked, and now people can like have phone numbers or like bank accounts with your data. But also, as you know, generative models like just got way better, and so now it's just possible to easily generate like huge databases of fake people and like KYC on websites. So this is why we like cryptography. Like maybe AI can generate fake images, but I'm not sure AI will like break the discrete logarithm problem for like RSA and the CDSA soon. So that's great. But if your question is more about actual physical fake passports, I think what's like my guess is that today most of the fake passports they look good from the outside, but they don't actually have a chip with a signature because this is really hard to get. You have to actually get the private keys from the countries, and you have to get the right country, right? So it's like actually very like challenging. I would not be surprised if there were like some fake passports that had the whole signature thing and everything. I just think it's probably quite rare, and that's kind of good for us, right? But in this case, yeah, if the whole passport is fake and the government kind of failed, yeah, of course, like you can do a proof there, but I guess that's like the trust assumption.
Testing? Okay. I had a follow-up question to your penultimate response about Japan's public key. So if the public key isn't public and only you have it, then if I'm doing a proof of my identity that I'm a Japan citizen, am I offloading that to you where you have the public key and you're not sharing it with me? Or do you share it with your users?
So good question. Nico would be able to maybe give more background, but my guess is that you have to call an API to check for a Japanese citizen. This is for the Japanese ID card system, not for the passports. For the passports, we can already do what we do. Okay. But for the Japanese ID card system, each time you want to verify, you have to go through an API by the Japanese government. So I guess there's like censorship here. But yeah, is that right?
Yes, if you want to like check the validity of that card, every time you need to check the like a government API, and like you need to like this card is valid or not. Like still the like RSA key inside the card is still available after if the card is revoked. So like it can be used as a kind of wallet, like you can use the operation wallet operation even after the card is revoked. But like for like civil resistance, like for the eKYC, you need to call the government API. Yeah.
Thanks.
So there is also a question from the community. The first one is, can you ensure that Open Passports is not selling user information? Like which apps a user connected to?
Yeah, good question. So the nice thing about everything we're doing is that it's all open source. Like the circuits are open source because it's the SDK part. The contracts are open source. They're going to be on-chain anyway. The whole app is open source, and it's not even just like we open source stuff. It's like we're building in public. Like you can just see on the repo like us committing and doing everything. So you can like yeah, basically see everything that's happening. Again, like when you do an app on stores, there's always like, I mean, you never know if like the code on the GitHub is actually the one that's on the store. It's kind of a general problem with apps. I think that like Apple and Google Play Store are like every time doing kind of verifications, every time there's like an update. But yeah, I guess there's some trust assumption on the fact that the app is not completely compromised. If you don't want to do this trust assumption, you can just build the app yourself on your computer, load it on your phone, and then you know exactly what's running. And then maybe another question, in the case of pornography, on Spain, they want to implement some kind of verification based on the DNI, so I guess national identity system. So does this kind of solution solve this problem better? Our opinion is that yes, because the question is, if you're gonna go on an adult website and have to prove that you're above 18 or above 21, do you really want to send your like passport photo or something that's kind of sensitive? Maybe for banking, it's sensitive, but in another way. I think for adult websites, it's like more sensitive on like your personal life. Like if there's a, you know, if there's a leak, you don't want like people to have this data and like link it to you or something. So I think this is where it's very important. And also, there's not really the compliance requirements that you have with banking, in which you have to check every transaction, do monitoring. For adult websites, it's probably okay, like I can prove that I'm above 18. That's why we're like super excited by use cases for Open Passport for this.
Another question is this Open Passport SDK made with ZK circuits, or what technology is behind it? So that's a good question. Open Passport SDK is mostly used to verify the proof. So it's not, there is no circuits inside of it, in a sense that it's just verifying the proof. So it's actually using ZK in the sense that it's going to verify a ZK proof. But the generation of the proof is only made locally on the phone.
Are there plans to expand information to include financial data? Well, I would say that we like, you can already use Open Passport for like transactions. One thing that we're kind of excited about is what we recently prototyped, the OFAC non-inclusion proofs. So you can, for instance, prove that you're not on the OFAC list. And I think something that's exciting in finance for that is like, you can have a wallet that says every time you do a transaction, it's going to take the passport data that you already loaded inside your phone, and it's going to do a proof that you're not on the OFAC list live. And what is nice about that is that the OFAC list gets updated, right? And so you can do always a live proof every time you do a transaction. You wouldn't necessarily need to scan your passport every time, but you can do it once in a while to, like, we can enforce you to do it once in a while so that we can make sure you didn't like steal a passport or something. And then it could be, for instance, like enshrined in a layer 1 or layer 2, that's like all the transactions have to have this kind of compliance system. Or you could have a DeFi protocol in which you say, okay, like this function, when you call it, there's a modifier on the function, and I want you to like only include this function in a compliant transaction. So those are things we're excited about.
All right, can we scroll a bit on the questions? Yeah, perfect. When do you think it is necessary to do on-chain and off-chain validations? When is it better to use one instead of the other in a practical way? So that's a really good question. The first answer is going to depend on the privacy layer that you want. There is a really clean answer, which would be if the application is a Web2 application, just prove it off-chain, and if it's a dApp, then prove it on-chain. But let's say that you want a maximum of privacy, and you want to use the two-time flow that we talked about before. So first you are going to register and generate a commitment, and in the second time you want to reuse this commitment to then generate a ZKP. So in this way, maybe it's better to actually generate the first proof and verify it on-chain, because like that it could kind of centralize every users and have the biggest anonymity sets. Yeah, so another question.
Do you have an SDK to include it in native mobile applications? Okay, so there's kind of two answers. Right now, if you want to verify proofs in your mobile app, you can already integrate it, but people have to like download the Open Passport mobile app to like do their proof, and then you can verify it in your app. One thing we're like thinking a lot about is making a more general like package or SDK that you can add to do proofs and passport scanning on your own app. So for instance, you want a fully integrated flow. You don't want people to have to download the Open Passport mobile app because it's like some friction. You have to download a new app. And so you would just be able to integrate it directly in your app. And that would be also really nice. Another thing that we're working on is like app clips. So app clips is basically like something that iOS provides. it's like you can easily open like a small version of an app without having to go on the store and click on download and everything. And like we tried the flow, it's like very great. It's coming soon too, so yeah.
Okay, are there examples of some corrupt countries issuing signed e-passports? That's a really good question. I think the answer is quite all of them in a small amount, because most of the time for secret agency, they will need to like create a real passport. So that's part of the game. But they should not cheat that much. And there is probably some specific country, I won't name them, but it's pretty easy to guess which one of them, and that's why you can actually exclude this country when you want user to disclose their nationality.
Yeah, the kind of philosophy we have is that because all of the passport data is there when you scan the passports, as an app developer, you can have the flexibility to choose what you want. So if like one day one country's like certificates get compromised, you can just exclude this country or like this specific certificate, or like go more into the granularity, or like say, okay, this signature algorithm is not secure anymore, and like now people can forge proofs with SHA-1, let's say. So now like we can just exclude like people that have like this specific signature algorithm if they renew their passports, like only support the newer ones. So yeah. All right. I think we're getting close to the end of our side, so we might just welcome ZK Passport to the stage. So ZK Passport is another team working on passport verification, bit of a different stack, different philosophy, and they can tell you more about their approach.
Thanks, Florent. Round of applause for the Open Passport team, everyone. Hi, I'm Michael Elliott. I'm a co-founder of ZK Passport, and this is Theo Madzo, and we're going to go through, I guess some of you may already be familiar with what ZK Passport is, how it works, but today we're going to have a workshop on how to actually plug into it and to be able to leverage these identity proofs for your own projects or dApps. And so we've built out this SDK in TypeScript, which allows you to use this query builder. Yeah, go ahead. And with this query builder, as you can see up here, you can, like, as a high-level overview here of how it works, you just request, you specify which credentials it is that you're interested in, that you'd like the user to prove, and then the rest is sort of handled for you. You get this URL back, which can be displayed as a QR code. They'll scan that, it'll bring up the ZK Passport app on whether it's iOS or Android. And
So the idea is that you can try this out on your site. So I'm going to pull it out this as a QR code so you can scan it from your site. So if you want to join in, oh sorry, it went away. So you can scan this, it's a replit, a REPL, so you can try it out, fork it, try it out on REPL directly, or maybe try to do that locally. But the idea is that you can import our SDK.
Yes, please. Thank you. Just going to bring it full screen.
Oh.
So it's easy to see. Yeah.
Ah, okay. Well, thanks.
Should be a bit easier to see now.
I'm going to keep this out for a few seconds.
Yep, I think it's good to go. Yeah, so the idea here is that we have this replit that we made, so you're able to fork this replit and easily kind of get going by yourselves and test this in the browser.
Yeah. So I'm going to show it out how it looks like. So essentially...
Also, just a heads up, we don't have any fixture data yet, so you will need to use your own passports to be able to actually generate these proofs.
Yeah, you need to have your passport to
Yeah.
test the flow. So you will generate a QR code with this example.
I was
where that's
considering lending mine to people that don't have it, but it may be a bit of a security issue. So
Yes, so you have to have your passport to do the entire flow, but I'm going to show it to you. So this is the deployed replit. So you click on generate new request. It generates the QR code with our SDK. You scan this with any QR code reader. So it pulls it out on my phone, and I'm going to, on this side, wait, if the Wi-Fi is good enough.
did you want to tether?
No, I think it's a more Wi-Fi issue because over the website.
No, tether through my cellular.
Oh yeah. Yeah, go ahead.
To see if it shows up.
Where
Or you could do your own phone.
Yep. Okay. Let me try again. Oh, jeez. Do I have connection? All right. Now it works better. So, oh, sorry. Oh, it disappeared. Why isn't? Oh, there it is. So the request was received. So this is like a little message that will be.
Use the camera. You can show you what's on your phone.
Oh no, I don't want to.
Okay.
Yeah. So generating the proof, I generated the proof on my mobile phone, and now you get back my details, so first name, country, and that you can edit easily in the app by playing around with our different function, disclose function, greater than equal, if you want to make a comparison with the age, the birth date, or the data from the passport. So for example, I'm going to go here on the replit. So what we do here is like disclose nationality, disclose first name, but for example, we could add another disclose of like the, let's say, what should I disclose? My information. Oh, wait. Yeah, last name. Let's go with last name.
So for example, this might be a good proof for social media, where you just want to prove your first and last name, but nothing else. You're already sharing that information publicly anyway on maybe X, Meta, Twitter, and this could be like attached to the profile there, or maybe Warpcast, Farcaster. Could I maybe just get a show of hands of how many people have their own passports with them? Cool, so 5 or 6 people will be able to do this today. We should have maybe given that as a heads up with the passport. But at least you'll be able to see the flow and how it's achievable when you get home and you're able to use your actual passport then, so that's useful.
Yeah, so here I'm going to add another state variable so I can store my last name. I got air completion, that's pretty nice. So I'm going to complete, and here we go. So from the result, so the way the result is structured is I'm going to have the query result with the name of the field and whatever function you require disclose, or like if you do a comparison, it would be equal, greater than, or others, and then you would get the result. So in most cases that would be a Boolean if you do a comparison, but here you directly disclose the data. And you will get, you can actually log the proof. Like the proof would be right here, although I don't think I see the logs here. But anyway. And I can add, oh wait, field for the first to last name. So when I generate the request now, come on. All right. Did I do anything wrong? Jesus. No. Seems to have a trouble issue with the Wi-Fi. Oh, damn. Let me try to reload this. Has any one of you been able to pull out the replit? No? Do you want the QR code again by any chance? Do you want the QR code again? Oh, yes, okay. Yes. You can fork it. You can directly fork the page, and you can create a Replit account. Or I guess you could create like an Next.js, because I just use a Next.js template. So you could create a Next.js boilerplate, like a simple app, and just integrate our SDK. I'm gonna also show a QR code towards the SDK repo, so you can get the link. Great, the connection is not good. I'm going to switch back to the main Wi-Fi. So this is directly the QR code for the repo of the SDK. So it's not on NPM yet, so you can pull out directly the GitHub URL. Oh yeah. Can you just plug?
Also, so we're available on both iOS and Android. However, currently the Android version is only available for internal testers because we kind of like released it too late. But if you're on Android and you wanted to join, please just this is my Telegram handle. Please just reach out to me now and send me your email address, and I can add you to the internal Google Play Store app so that you can get the Android version. Just one sec. Also, you can just message me. I'm ZK Mike. Okay, here's the QR code. So yeah, again, if you're on Android and you want to get access to the Android app, just message me your email address, and I'll add you to the Play Store app. I can give you my phone, just chat through it.
I was using my phone, but that was actually worse.
My cellular might be better though.
It's really better. Let me see if the AI actually works. Oh, yeah,
Just plug this in. If you're having issues still, let me know. You can use my phone to tether. My cellular is better.
Okay, so now it works. After fixing those issues with Wi-Fi. So you got the QR code here, which is essentially embedding nationality, first name and last name request. So one more field compared to before. I'm going to scan it again with my app, ZK Passport app. Pulls out the request on my side. I'm being asked for my last name now. Just waiting for request received. Now I can accept. It's generating the proof. This is all done over WebSocket, end-to-end encrypted, using ECDH to set up the shared secret and ECDSA SEC P256K1 for the encryption. And you can see my last name in addition to my first name now. So this is, you can play around with the disclose function. You also have greater than equal functions, for example, for age, like if you want to prove that you're over 18. And in this case, it would essentially send out Boolean whether that is true or false, and that's the only information you're going to get back from the user. So I'm probably going to try to set up this. So let's say he's over 18. Actually, it's more 18 or plus. Okay. So now I'm also asked for my age, violation age comparison. I'm going to send it back. Oh, is it not showing? Oh, I forgot to. Wait. Oops. All right. Well, result. Was it? Oh wait, let me actually look back into SDK. Define my types. One details regarding this is that the whole SDK is strongly typed in TypeScript, so generally you will have like auto-completion that's pretty intuitive, so you know what to expect and what to put in. Yeah, that's okay. Yeah, it is. It's fine. Where was I? I don't know. Like the edge I'm getting. I guess this is just.
So maybe now we can move on to also just describing the sub-circuit design we have and the reasoning behind why we've designed it this way. So on mobile, you're really constrained by the number of, by the amount of memory that you can actually use. And so we can't have our circuit size blow out too large, too big, or it won't work on mobile. And you want to have client-side proving on mobile because you want to keep privacy. You want to keep your private, passport data local to your device. It's on our t-shirts. Own your identity. The meaning behind that is self-custodial identity, where you own your own data. And also on that topic, after this workshop, there's plenty of t-shirts we have. So just, after we finish, please feel free to go over to the corner here and you can grab your t-shirt. We got a new batch in today because we ran out, so do you want to take it away there?
Yes, so regarding the circuit composition, wait, who in the crowd was in the talk yesterday we gave? Because I made a quick overview, but that was not very deep. I was hoping to go more into details, so actually now I'm going to do it. So yeah, you had that idea of certificate trust chain, which is similar to the SSL certificates, if you know how that works. So essentially, the passport data is signed by the state, but there's two certificates in the chain. There's an intermediate certificate, which is called the document signing certificate, the DSC, which is essentially signing directly the data. That DSC is directly in the chip of the passport, nearly all the time. There was exception. And then you have the root certificate, which is actually the source of trust. So the root of trust, which is like the certificate that signed the intermediate certificate. And that is a kind of certificate you can maybe get from the government websites or a registry provided by the ICAO, the International Civil Aviation Organization, which is the one that set out the standard and managed by the United Nations. Or sometime you may not find it and you have to find other ways to get it. So the idea is that within our circuits, within our zero-knowledge circuits, so in Noir, we do the verification of those two signatures, which allows us to prove that those data were signed by the state and then attest the validity and authenticity of the document. And the way we organize our circuit is that we divide it in sub-circuits. We don't want to have like a single big circuit, because otherwise we would have too many constraints, which would blow up the memory consumption. And memory consumption is very important on mobile, so we need to restrict it. So we have 4 main sub-circuits. One that will verify the signature of the root certificate over the intermediate certificate, which is on the left. One that will verify the signature over the passport data, which is the second one. And then one which will verify the integrity of the data. I will go back to that real quick. And then the final one, which is the disclosure. So if you want to disclose information, so like when you play with the SDK, this is essentially the one that's gonna disclose whatever you ask for. So like disclose field directly, or do a comparison of age, or any kind of like stuff you can build with the SDK. So we're trying to be very, so this approach has 2 advantages. So we split the circuit in smaller circuits that can be executed sequentially. It may take more time to generate the proof, but at least the RAM consumption will be not as much. So we can actually work without making the app crash. And the second one is it makes it quite modular, which is very important in the context of passport, because in this standard, there's a lot of flexibility in the kind of signature algorithm that can be used. So you need to have like a specific circuit that implements a specific signature algorithm verification. So we have different circuits for all those kind of signature algorithm. We're going to add more. We support some of them. We're going to add more over the next few weeks and few months to support all the passports. And the idea is that you can just swap whichever signature algorithm circuit you need. So you're going to have one for RSA of different key size, one for CDSA for different curves, so you can just swap it out. So it's very modular. So those are the 2.
It also means we can add new circuits as new signature algorithms get added by governments.
So yeah, without changing too much. And Noir being like Noir coupled with Honk, and the backend bar Tabung being kind of proving scheme trusted setup every time, so managing new circuits and updating current ones is much easier than using Circom with Graph 16, for example.
Also, if anyone's trying this out with Replit and they're having issues, please just feel free to put your hand up and I can come over and try to help debug.
So more details on regarding the passport integrity check. So this is really core to kind of link the signature to the data that we use to generate the proof. Essentially, the data of the passport that we use is mostly derived from one data group. So they call those data groups. It's like the DG1, data group 1. And this is essentially the data of the MRZ, the machine readable zone. The two bottom lines you can see when you open your passport. Those kind of character with the little angular brackets. That's kind of like the filler characters. So those contain issuing country, country of nationality, birth date, expiry date, document number, gender, name, first name. So you have most of the information that you need from just this single data group. And this data group, among all the others, so there can be up to 16 data groups. Most of the time, there's only about 5 or 6 or 7. Only the two first one are mandatory. So the data group 1, we just talked about, the data group 2, which is the photo, like the one you see on the
It's like a
passport.
JPEG of your face, 20
Like a
kilobytes
full,
or so.
Yeah, like a full JPEG, like generally a couple dozen of kilobytes. And the rest of the other data group, you can have like the fingerprint, the iris. Those two data groups tend to be restricted, so we can't actually read them. We know they're there, but we can't read them. The state need to authorize you specifically to be able to.
This is where like countries would give access to other countries they trust.
Yeah.
Otherwise, you'd be going to airports around the world and they'd just be scanning everything, which is not ideal.
You got a couple of free-form data groups as well, and some other data group, including like an interesting one, the 15, data group 15. That means that when you have this data group, a passport can actually sign stuff. Not all countries support this one, so it's unfortunate. That would be an interesting primitive to have.
It's quite powerful, actually. It essentially makes these passports into a type of hardware wallet, allowing you to sign over data.
Now, for example, my passport doesn't have this data group. It uses another kind of like, it does have a private key inside, but that private key cannot sign deterministic messages, like challenges. It's only like deterministic stuff. Because some countries don't like the idea of being able to sign whatever you want with your passport.
It may give too much power to the citizens, perhaps. Who knows?
So yeah, so that's unfortunate. So all those data groups, all the data of those data groups are hashed using a different kind of signature algorithm per country. Again, that's up to them, but generally it's going to be SHA-256, SHA-384, or SHA-512, like different variant of SHA-2.
Something else is quite interesting. This is all encoded in what's called LDS on the passport, logical data structure, and so that's the current version that's used around the world. But there's also a V2 coming out at some point, LDS2, and so LDS1 supports the ability to read data, but LDS2 supports the ability to write data as well. So you can imagine governments maybe using this, so when you travel around, instead of getting like a physical stamp on your passport with the ink, you'd actually get like a digital stamp that you've traveled somewhere. So that could be cool, and then you'd be able to generate zero-knowledge proofs from that data that a government has attested to the fact that you traveled through their airport, and that could be a cool use case for that. Or a privacy nightmare, depending how you look at it, I suppose.
So all those hashes then group together and hash into a final hash, which is what is actually signed. There's some padding adding to this, but the overall idea is there. So the final hash of all those hashes is signed, and this is what we call the signed attributes. So the content is the gathering of all those hashes, and then the final hash is the signed attributes. And so from those signed attributes, this is, since if you verify the signature over that message, and what we do in our circuits is that we go from the DG1, get all the other hashes that are provided, we group them, we do the whole process, kind of. We verify that indeed the data, after being hashed from DG1, gives back the same message that's being signed, so that way we show that the data we're using is the data that was signed. So that's the data integrity check done here.
And then finally, there's the disclose subcircuit, and this is where you're actually able to generate proofs to reveal selectively information, mostly from DG1, because that's where all the interesting information lives. And so you can just do a simple, so when you're actually specifying what it is that you want to disclose, whether it's the first name, last name, this country, this kind of stuff. Gender is even possible. You create like a byte mask, and that byte mask combined with an actual output DG1, like the reveal DG1, in the circuit, it will reveal wherever there's a 1 bit, or 1 bit, sorry, just like a 0xFF. And so all the characters, the 93 characters of the DG1, you're revealing selectively information in that way. And then there's also other possible circuits that are a bit more dynamic, like a proving that you're over a certain age. So essentially you'd have, as a public input, you'd have the age that you're trying to prove that you're over, and you'd also have the current date as a public input. And then it would, in the circuit, it would be responsible for extracting out the date of birth that's in the DG1, and then doing like a delta check between the current date, that's a public input, and your date of birth, and that must be over the input age, the public age input. And that's the only way you could generate a valid proof for proof over a certain age. And so we can also create new circuits in the future because of this modular design to allow for disclosure.
Yeah, and so the way we kind of make the circuit link to each other, because if you execute them separately without any glue, it doesn't mean too much, because you can easily cheat, like with the data you put in.
You can easily cheat, which is why you need commitment.
So you have like commitment between each circuit. So like the first circuit on the left, which verify the signature of the intermediate certificate, commits to the public key of the intermediate certificate. That commitment is checked into the second circuit that it is indeed, you have the public key of the DSC including that commitment that was generated by the other circuit.
And by commitment, you could just imagine that as like a hash over the data that you're trying to pass to the next circuit, but then also you obscure the values of the hash that are called a pre-image by using this secret, so that no one can like figure out what it was that was being passed between circuits.
Yep. And so you have a commitment that's linking the two others from the second and the third, essentially over the signed attributes. So that way you know that that message that was verified against, the signature the message was verified against, is indeed the same you checking the data integrity checked against. So you're sure that that data integrity checks does match with the signature. And then the final glue is like with the DG1, so like the data group you derive the data from, so you want to make sure that the data integrity check is done over the same DG1 that you're going to disclose. So all this together makes it so that they're all linked together. You cannot cheat. The prover cannot cheat trying to prove wrong data.
Because they're all uncommitted sub-circuit relationships.
Yeah. And then we also have this idea of the nullifier. So from some of the data from the passport, we derive a private nullifier. Well, it's called like secret.
Yes, we're calling it a secret nullifier here, but private nullifier is also possible. And the reason maybe we could change this to private is because the government may know, probably knows the data on that passport. So while it's private and not something you're sharing around publicly, there is an entity that may know. So we call it a private nullifier.
Yeah. And so that information is also added with a salt, a private salt that's generated by the user on his mobile phone. So that allows to add some randomness to it.
And allows for full privacy, so even the government knows the passport data, they can no longer deterministically find the actual nullifier because you've obscured it with this salt, and that's important.
And the actual final nullifier that's revealed to the service is scoped to the domain name of the service, plus another subscope that allows the service, so essentially the service is like the developer that's asking a request of data from the passport of the user. It allows it to essentially restrict to a specific use case. You could have like a subscope named voting, a subscope named
like poll ID 420, and then for the actual service scope itself, we use the domain name. So that's the same domain name that must match on the website you're at, and so in the QR code, that's also encoded, which is why the request comes up so quickly. But your the client-side app is actually also checking that that is indeed the correct domain name. So you can't just spoof some other service's domain name, which is also quite important.
Yeah, so, and essentially that pretty much wrapped it up.
Just to clarify, the reason for the service scope and why this is important, if you just use the same nullifier that was global, it'd be easier, obviously, but it means that if I were to use, service A over here, and I were to vote in some kind of poll, that would be a nullifier that would be used to ensure I don't double vote. And then if I were to go to service B over here and vote there, they could easily compare or maybe it's public even, and see that I actually am the same person that use these two different services. So the server scope allows for privacy between different services. And then again, the subscope, even more privacy that's more granular. Should we open up some questions?
Yeah, I guess I can open up some question. Did anyone? Oh, wait. It didn't. Well, never mind.
Stuff that makes the possible, but productionalizing it is what I think is like happening now that hasn't been happening like before now. So I'm interested about actually the toolkit for Honk and like the client, the either mobile or desktop side proving that like is performant. What are the tools that you're using for that?
For Honk proving on mobile?
Sure.
Yeah,
whatever you're proving.
Yeah, so originally, like Bartenberg didn't work well on mobile, so we worked on some mobile tooling for generating the proof using Honk on mobile. So like, essentially the way it works is that we have bindings to the Bartenberg C++ code base, so the C backend used by Honk, in Rust. And those bindings, we use them into a library that allows us to generate the proof for any kind of targets. Actually, it works on macOS as well, but then we optimize it for iOS and Android. And that Rust code, we bridge it to Swift and Kotlin on iOS and Android respectively, which our own app is in React Native. We then link that to the JavaScript code. So that's a lot of bridging all the way from C++ to JavaScript.
And the iOS library is called SWA, that we built out to use this on mobile. And so it's a portmanteau of Swift and Noir, SWA.
Yeah, the other one is called Noir Android or Noir Droid. Still deciding on the name. I'm not sure which one is better. Maybe you have an opinion. Not sure. But that's the general idea.
Awesome. Thank you.
So we get some question here.
Regarding the age one, I saw about a government using a particular type of age verification. I think this is, just generally speaking, this works really well for age gating adult websites or gambling websites, because essentially you've got a government somewhere attesting to this information about the citizens of the country, and then you can use zero knowledge proofs, so whether it's an e-passport or some other system, you can use zero knowledge proofs here with our system to just prove that you're over 18 and reveal nothing else. So whether it's their system that they use or this, I think it's a wonderful solution. Like, I can't think of a better solution than that.
So I believe the two bottom question are ours, right? The two bottom ones? What was it like? Oh, no. Okay, there's more than I imagine. Okay. Which one? There was a question about the difference between Open Passport and ZK Passport. I'm going to cover this real quick. I think this has been asked in a panel as well, where Michael and Florent were speaking. So yeah, our projects are quite similar. We cover like a similar idea. So they use Circom originally for their circuits. They are mostly supported by PSE from the Ethereum Foundation. We kind of used Noir from the get-go. We did use Circom at some point to get things working, especially for the Devcon integration. At the time, Noir was not stable enough for us. But now it is, so we are fully using Noir, like completely 100%, no more Circom, no more Groth 16 whatsoever, no more Z-key. So the difference is we tend to put a lot of focus on, I would say, UI and UX, and also a bit of DevX, because we want to have like a good SDK and everything. So like right now, what you saw is a TypeScript SDK, strongly typed, but what's coming up in the next few weeks or few months, it will be a React SDK. So the idea of that is that you have a single component, you plug it in, no API key, you set what you want from the passport, and that will be all. We'll take care of all the rest, the QR code generation, the progress with all the UI updates, and a callback with the results. So we really put a lot of focus on that.
Yeah, and I think we're also discussing with them something that makes the most sense to duplicate effort is to actually merge the two projects together.
It does make sense because they want to switch Noir as well. So you're going to have two projects working on with the same stack, same proving scheme, same language. So it makes more sense to merge. That's something we're working on.
There's a question about how can you ensure it's not like forged. You'd have to actually break like RSA encryption for that to be the case. So you can be you can have the assurance that it's genuine, unforged passport proof because of the cryptography involved. Oh, and that's a great question, yeah, about the last one here. Is there anything done to address the I borrowed my friend's passport issue? So the way that we can solve this, we'll be doing this quite soon actually, as a feature we're going to build out, is you can generate a face fingerprint from the photo, the JPEG on the passport that's also been attested to by the government, so you can trust it, and then we'll have the users with their iPhone, they'll scan their face, all local, nothing leaves the device. You scan your face, it'll derive a face fingerprint from that, that's going to be, you have the guarantee of the TE on the iPhone, so it's a trusted execution environment, and we can use the app attest service to ensure that. So in other words, you know it's our code running that derived the face fingerprint and not like a jailbroken iPhone. And then you can compare those two face fingerprints in zero knowledge to prove that you are the same person that's scanning the passport that is also on the passport, which I think is just magic. That's pretty cool to be able to do that to a service, like provide that to a service. Yeah, I did already, yeah.
So we got a question. How will this affect KYC requirements if none of your personal information is passed on to the service provider? So this is often a requirement for AML and CTF in many countries, that you should be able to give out the information in case of a suspicion of fraud and or money laundering or terrorism financing. So yes, it might be a bit of an issue for full KYC if you have full self-custodial identity. But I believe that with blockchain, where we have more of a gray area, we have an opportunity to nudge into a different direction. So, and actually that's probably where we're heading with Obsidian, the wallet we're building on Aztec. So Aztec is a privacy-preserving layer 2 for Ethereum. So using Noir as the smart contract language. And the idea of Obsidian is that, so it's going to be one of the first wallets on Aztec, and it's going to integrate natively ZK Passport. So you're going to have privacy, compliance, and identity at the wallet level natively. So essentially, we're going to be able to provide to dApps an easy way to request proof of identity and compliance proofs. And it's going to be very smooth for the user. It's not even going to realize it. It's going to be self-custodial. Now, we've been kind of entertaining the idea with Circle of a compliant USDC on Aztec using Obsidian. So every time you would make a transaction, you would have a check that would be done. That would include, for example, a local check against OFAC list, another SDN list. So that can cover its moderate risk, not high risk, I would say. So this is a way toward compliance on-chain and compliance with using self-custodial method instead of having to store the data. Now, yeah, you're not going to be able to use ZK Passport for full KYC in the traditional world, but if we nudge in that direction, maybe the minds of regulators can change if they can see applications into this space.
Yeah, and the reason this works really well for a private stablecoin like USDC on Aztec network is because every time you transfer that USDC around, you're generating proofs again. So you're actually checking against the current OFAC SDN list and sanctioned country list. So instead of, it's kind of inverted a little bit. So instead of you giving that to some provider that's checking themselves every day, you yourself are checking just by the fact that you're generating a proof, but all privately. And there's be some other cool checks there as well. You could have you provide this super generous limit of say 100,000 USDC per month that is enough for 99.99% of people, but it's going to really mitigate and prevent a lot of bad actors from using this with hacked funds, that kind of stuff. And that's going to be using the nullifier that you saw before. And that's going to allow you to transfer privately USDC and then off-ramp if you wanted to to Coinbase, Binance, wherever, and not have to worry about getting your account banned because it's a privacy coin.
I think that's it. That's it.
Any other questions that we haven't covered that maybe somebody wants answered? Just feel free to raise your hand and we can. Yeah.
Where can I find the diagram? The slides?
Oh, the slides? We can share them with you if you like. If you just message me on Telegram, I can send you them through. Cool. ZK Mike. Okay. Anything else you want to cover?
I think that's right.
You say you wanted to cover something in the slides that we didn't quite get to? The sub-circuits?
I think the sub-circuit was pretty much covered everything on it. And where's the slides?
we'd also love to hear about any ideas that anyone has. Oh, we've got some questions popping up. Great.
Hey. So there was that question about the KYC requirements. Are you guys aware of any governments that are moving towards accepting a ZK proof of a passport as essentially the same thing as having provided your passport?
Yeah, great question. I think a lot of this is really sort of uncharted territory. And so we have the opportunity to get in front of FinCEN and speak with them. I think that's really a matter of just having those conversations with regulators and showing them, explaining how the tech works. It may take a lot of time and effort, but I think once this new paradigm of zero-knowledge proofs and how it can really unlock these new features, they can see that it's actually working. I think that'll really help to warm the government to these kind of new approaches. And there's also ways that this can work off-chain, but provide way more security than just a photograph of your passport. And that whole model, I think, would be completely broken. It already is broken, but it's going to become more broken with the generative AI, these kind of things, due to the fact that it's unforgeable. And these proofs are one-time use as well. So, you can't replay them easily. And so in the example of needing the data to check it maybe every day against your OVAC SDN list for banks and some financial institutions that need that kind of security, you could simply just have it like off-chain. So you can generate a proof that reveals your full name, date of birth and country, and maybe a passport number if you wanted to. And you might ask, oh, but that's already available, if you send a photograph in. Yeah, but it's a photograph of your passport. If it's a proof, it's unforgeable. So they can take that, they can have it on their server, it's never revealed publicly, and they can do their daily checks against the OFAC SDN sanctions lists, and they have a far increased ability to be sure that it's actually authentic. And I think, it's just going to take time for governments to start realizing that this tech, it's still very new tech, it's just like bleeding edge to kind of warm up to this. Thanks. And I think if anyone has any great ideas about use cases or wants any help, please reach out to us on Telegram, ZK Mike, or even just Twitter. Please just tweet out to us, ZK Passport, and we'd love to reply and brainstorm some new ideas with you guys. If you have anything you're building, also please tweet that out to us, and we'll help just to promote it and share it, and also work with you guys to build out cool use cases. And ultimately, what we're building here is public goods, open source, reputable identity infrastructure for Web3. And so we want as many projects to build on this and be able to unlock these identity primitives to make use of them in really cool, interesting, and novel ways. And so I think that pretty much sums up our workshop for today. So thanks everybody for coming. This has been really fun. I really appreciate it. And if you guys would like some t-shirts, we have the last batch available in the corner here. So please help yourselves.
Okay, and we're live. Welcome, everybody. My name's Andrew. I'm with Xerox PARC, and I'm here to talk to you a little bit about pods. How many here have been using pods this week? I think the answer should be everyone, because you got into the building somehow, and that actually required one. So what are pods? So your Devcon ticket is a pod. The proof of attendance to this talk that you can claim from the Q&A app that's up on the screen there right now, if you're in the room, I don't think this works remotely, that's also a pod. Some of you have been playing Frog Crypto this week. I see some frog hats out there. All those frogs are pods. A pod really can be anything. It can be a secret message. It can be your identity credentials. It could be your driver's license, if we get any governments involved to actually do this. It's cryptographic data of any sort. So what is the pod framework? So pod is a technology, a framework that makes it easy for apps to issue cryptographic data and to make ZK proofs about that data. It's a data format that's optimized for efficient proving. It's a standard of how that data format can be sent around and things can be proven about it. And it's a framework with some developer SDKs. Check out our documentation site. I'll have a link at the end if you want to try it out. It's mostly in TypeScript, but can be used on other platforms as well. We have ports in a few other languages. So I'm hoping some of you will get some use out of it. So one last WTF is zero knowledge proofs. How many people here have used ZK proofs before? Feel like you understand them? Okay, a few. It's kind of obscure technology. That's kind of the point of pods, is to make it easier to use so you don't have to understand how the underlying math works. But in brief, a ZK proof lets you prove the validity of any private data or any computation on your private data without revealing that private data itself. And that proof is trustworthy because there's some math that basically you can only calculate if you did it validly. At Xerox PARC, we think of ZK proofs as a universal cryptographic adapter. Basically, I've got lots of different kinds of private data. By doing computations on that data in a verifiable way, I can present to somebody whatever I want that is validly proven from that data. The example in this diagram, which you'll find in our blog post, is like, what if I could calculate my own credit score from signed data I got from my bank or from the IRS? I don't need to ask a credit reporting company to gather all this stuff together. I can gather it myself, and I can make a provable statement about what my credit score is and apply for a loan. This is part of the vision of something we call the PARCnet. programmable cryptography internet, which we think is going to be much better once programmable cryptography catches on in all of these ways. ZK proofs are a big part of this, but it's only the beginning. See the other talks being given by my colleagues this week. Also, we have a whole day CLS tomorrow about programmable cryptography. But today we're going to be focused on ZK proofs and what pods let you do with them. So this is the pod ecosystem that we envision, right? You need issuers who are issuing this cryptographic data. They're mostly using a private key to sign it. Those takes the form of attestations, which users themselves can hold on to. They hold on to their own private data. They don't need an intermediary. At some point, some consumer asks the user, please prove something about yourself. Your identity, your age, the fact that you went to Devcon, things like that. And then the consumer can generate a ZK proof and the user can send the ZK proof to the consumer who can verify that proof. They do need that third arrow in the diagram, which is a little bit of knowledge about who the attester is. You need at the very least to know that that attester has a public key that you should trust. There might also be things like what is the event ID that represents Devcon on a ticket, things like that. But that kind of completes the diagram. Okay, so why are we doing this? So I work with the team that builds ZooPass. You've all been using that to check into Devcon. And we believe that the best learning on this kind of technology comes from contact with reality. Meaning we want real users to try this. We want to do it at scale. There are 12,000 people at Devcon this week who are stress testing ZooPass for us. Thank you. I'm sorry if the performance has not always been as great, but it seems to be standing up. And we want to use these opportunities to onboard new users by bridging data that is not ZK-friendly into our ZK-friendly world, and take advantage of people who are willing to be early adopters, like the crypto community. So by bridging, what I mean is we're bringing data in the red boxes on this diagram into the green world. Red in my diagrams of this talk and the next one means like non-ZK friendly systems, whereas green means ZK friendly systems. We can bridge it in, we can then issue it like your Devcon ticket, which is loaded from a database that isn't cryptographically signed. And then the verifiers can gate you into another system like Telegram in order to join the Devcon chat group. All that is working today. In order to bring this in front of the most users, we do have to accept some constraints. So we're not using the most cutting edge of ZK technologies. We want everyone to be able to use it, which means we've built a mobile-friendly web app, which means everything we do has to run in a browser on a phone, even an older phone, even on a bad network when the Wi-Fi is overloaded at the conference. So that became a bit of a mantra when I was building some of these technologies. So there's a lot of cool ZK technology out there that is great, but it needs to run on a big back-end server, and I don't have one of those when I'm in a browser on a phone. So we got to use tried and true technologies. For people who are in the know, we use CIRCOM and Groth16. You may not have heard of those, but that's kind of the underlying technology. They've been around for quite a few years, so they're pretty well battle-tested at this point. So I want to talk a little bit about the systems we built along the way. So this is what ZooPass ticketing looked like a year ago at DevConnect when we were in Istanbul. So it's the same triangle that you've seen here. We were pulling data out of pre-ticks and issuing the tickets. We used a format called an EDDSA ticket. That's a signed piece of data, but it's not a pod, which I'll explain a little bit later. And then we had a proving circuit where you could prove your ticket. You could reveal some fields. You can prove that you owned it, et cetera. So what did it take us to build this? Don't pay attention to all the details here, but look at the line counts on these PRs when we wrote these things. It's pretty large. That's quite a few lines of code that it took. And there's, in just the ZK proof, there's about 15,000 lines of code that are still there, that, not including tests and documentation. So it's kind of complicated. So that was the first thing we built. The second thing we built was Frog Crypto, the first version last year, which used a very similar data format. So frogs were issued by the server as what was called an EDDSA frog, very similar format to tickets. And then you could make a proof about it. You could present it to our ZooCat Telegram bot who would let you into the secret frog holders chat. This all happened last year in Istanbul. So what did it take to build that? It turns out it was very similar. There was a lot of duplication of effort. There was a lot of similar patterns, but you couldn't actually reuse the underlying data. So there clearly is a pattern here, right? We want to issue some signed data. We want someone to request a proof and then to be given a proof of that signed data. But it turned out that each time we had to build it, we had to rewrite a whole bunch of code in order to customize it. So I'm an engineer. I don't like this kind of complexity. I'd rather do things once because I'm lazy. So why is this so hard? So the signed data part, the EDDSA PCD that we were using as our underlying data format, uses a fixed size hash. It hashes 16 numbers in an array. And therefore, every new data type that we wanted to put in there, we had to do some custom coding to decide how those numbers in that array go together to make this data type. I would analogize this to imagine you were like processing all your data in a hex editor directly as bytes. It's kind of inconvenient. We have better tools than that now. And on the proof side, ZK circuits are a little bit awkward to program. Like they don't use a normal programming model. You don't write it in a language you're used to. Every variable is what's called a field element. This is a mathematical concept. It's a very big number modulo some big prime number. And you've got to like write equations on those field elements. So it's kind of complicated. And also, once you build a ZK circuit, it's very fixed. In order for the prover and verifier to agree on what's valid, the circuit can't change very much. It's hard to, you have to publish a whole new circuit. So that makes this a bit hard. I would analogize this again to, in the hardware world, this is like an ASIC. It's a chip that does one thing. It might do it very well, but it still only does one thing, and every time you want to do another thing, you got to build a whole new chip. It's kind of inconvenient. So what do we need here? Well, what we'd really like to have is what's called a ZKVM. Basically, if you have an ASIC and you want something more general, why don't you use a CPU? And there is technology out there that lets you basically write code, run it inside of a ZK circuit, and validate that this is the correct output. It's great. Some other people are giving talks about it this week. But unfortunately, for our situation, it's a little bit too much. Like I said, my mantra has to work in a browser on a phone. ZKVMs are pretty big right now. You're not going to be able to do that on an older phone in a few seconds. So we have to do something a little bit more limited than that. But again, I'm an engineer. I like working within constraints and coming up with clever solutions. So here's what we came up with. So on the data side, I'm finally going to explain to you what a pod is at some level. So a pod is just a collection of names and values. Think of it like a JSON object. Except that it's flat. There's no hierarchy of nested objects, just names and values. It can have multiple data types in it for those values. The data is then cryptographically signed in a way that makes it easy to make proofs about it, and I'm going to get into more of that a little bit later. Also, I forgot to mention this at the beginning, we are having a deep dive session after this intro session, so stick around for that if you want lots more detail. But I'll give you what I can in the next 15 minutes. On the proof side, we also can generalize. So we have what we call a general purpose circuit, which means rather than having a fully CPU-like circuit in a ZKVM or having the ASIC fixed circuit, we can do something in between. I would analogize it more to an FPGA. Right? We've got some logic blocks, we call them modules. You can feed in some inputs to your circuit in order to decide how those logic blocks are connected to each other and make a different proof every time using the same circuit. We call this framework GPC for general purpose circuit. And in addition to the circuits individually being configurable, we precompile a set of circuits in what we call a family at different sizes with different sets of modules. So when you want to make a proof, you can pick the circuit in the family that has enough modules for what you want and not any more, because having a bigger circuit means more time to prove, more memory, etc. So you can make the right trade-offs there. So with that, we get the generalized version of the ZK ecosystem, where every issuer is issuing pods. They might contain very different kinds of data. It might be a frog, it might be a driver's license, but it's still a pod. And then when you make proofs about it, you can freely decide what you want to prove and write a configuration to represent that proof. So with that in mind, at this point, what is a pod? So a pod is a data format that makes ZK proofs easy. It's a key value store. It's going to be hashed and signed in a very specific way involving a Merkle tree, which I can explain more of later. And it's optimized for efficient ZK proving. Here's an example of a pod. So we've got some names and values. Most of these are very straightforward, so I'm not going to go through them all in detail. The one that's maybe a little bit interesting is the card holder. So this is meant to look like a driver's license in some, fictional country. The card holder is my semaphore ID. This is what ZooPass uses to identify you. It's really a public-private key pair. So the public key is what's going to go in the pod to say that this is my pod, or in this case, this is my driver's license. What you see on the right is the JSON format for this. It's optimized to be a little bit terse and also human readable. So things that don't need a type annotation, you'll notice, don't have them, because the JSON type itself is enough data for that. Once you get down to actually building the Merkle tree, like everything does have a type, but in this table I call them type hints, because the type is not part of the cryptographic data. Instead, it is guidance to how do I hash this data into a piece of cryptographically verifiable data. More on that later. So the first thing I do to make this into a pod is I build a Merkle tree. I'm not going to go into detail on that, but basically you arrange the elements into a tree, you hash them all together until you get to a root, and that root is what we call a content ID. The content ID is derived from the data, so if you have the same data, you can derive the same content ID regardless of how it was formatted in JSON. One detail that you might notice on the right is that the names have been alphabetized. That's how we make sure that it is deterministic and you always get the same content ID. But everything else is just hashing. And then now, once I've got the content ID, that's the thing that I sign. So if I'm an issuer and I want to issue a pod, first I get the data, I Merkleize it, I get a content ID, and then I just write a signature on that content ID, and that's enough to validate that the entire pod is valid. So we have a ZK-friendly data format. We'd probably like to do some ZK proving on it. So let's talk about the GPC side of this. That is what lets you do that. As I mentioned earlier, GPCs are circuits made of reusable modules, as well as a family of multiple circuits, so you can pick the size that you want. Let's look at what that looks like. So this is an example of a GPC configuration. This is how you say, what do I want to prove? And you're going to present this as this JSON object that says what you want to prove, and the system is going to do the rest, compiling this down to what to do with the circuit. So here's a very minimal proof. I'm going to try and prove that I have a driver's license that says I'm allowed to drive. Right? So my configuration says I have a pod. I'm going to call it ID card. This is actually an arbitrary name that's just part of the configuration to refer to it later. It has some entries, and one of those entries is driver. That is not an arbitrary name. That's a name that was in the pod and is going to be hashed and checked. And what do I want to do with it? Well, I want to reveal it. So isReveal is true means this is a proof. It's going to proof that I have a pod, that it contains this entry, and it's going to reveal that its value is hopefully true because I'm going to try and drive a car. So that's simple enough. There's one detail that wasn't on the previous slide. That's because it's done by default, so I didn't need to include it in the config, but it's important to talk about. What I proved, if I don't think about the signer key, is I just proved that I have a pod containing the word driver with the value true. That doesn't mean it's actually a driver's license. In order to do that, you got to do something cryptographic. So the easiest way to do that is you check that the pod was signed by a public key that is well known. That might be the government of California, which is where I live. Hopefully we'll get them to issue pods eventually. But that is implicit, like the signing key is also always revealed by default. But you can choose to not reveal it if you want to, in which case you can constrain it in other ways. You might constrain it to be equal to some other element without actually revealing it, or constrain it to be a member of a list. Like maybe I have a list of all of the signing keys of the 50 US states, and I just want to prove I have a driver's license from one of them. I don't want to tell you which one. Okay, let's try and get a little bit more complicated. So I've proven that I have a driver's license that says driver equals true. I haven't actually proven that it's my driver's license yet. I could have stolen somebody else's. The thing is that pods, because they're just data, they are transferable. I can copy them. The way we make a pod bound to a single user is by putting that user's public key in it, which I showed earlier when we were looking at the entries. And the way you prove that you are that user is you make a proof that you hold the private key that corresponds to that public key. And the way you say that in the GPC config is this isOwnerID field. You say isOwnerID, and I give the type of public key I'm using, which is semaphore version 4 from our friends at PSE. And that basically means that this proof is going to be configured to check that I have the right private key, which is in my private inputs. And in this case, it's not even going to reveal what my public key is, just that I own this pod, and this pod says I can drive. Okay, let's get to a little bit more ZK and hiding some more data. Instead of proving that I'm a driver, what if I just want to prove I'm over 21? Maybe I want to go buy some alcohol. I don't know what the age is in Thailand, but back home it's 21. So I can just say I have a pod containing an entry called date of birth. That entry is not going to be revealed, but it's going to be in this range, and that's the numeric range for the date that is 21 years ago. We should make this more friendly and let you just pass in a date object, but for now it's a number. So this is a proof that I am over 21 and that I own this pod. I didn't take out that field, but everything else is not revealed, and I'm being very anonymous. One last example, we can make proofs of multiple pods at once if we have a circuit with enough modules. So here's one that I'm proving I'm over 21 and also proving that I have a ticket to an event, that maybe I'm going to go to an after party after Devcon. And in this case, the ticket, I'm proving that its attendee name is the same as the name in my driver's license. I'm proving that I own it, and I'm also proving that the event ID of that ticket is in a valid list. I'm not revealing what I have a ticket to, but it's in maybe a list of like Devcon related events that are happening in Thailand this week. So this is kind of a minimal anonymous way of checking into a party. Of course, if I'm there in person, I'm revealing some more about myself by being there, but you get the idea. Okay, so last piece of this, I've now configured my proof. I've decided what I want to prove. How do I actually make a proof? And all of this is an example of what you can do with the GPC libraries. So the three things I need in order to make a proof, one of them is the proof config that I've already given you some examples of. The second thing is the inputs, that's the actual pods, which I need to have in order to make proofs about them. There are also other inputs like my private key, or like that list of valid event IDs that I want to prove that my event ID is one of. Those are all inputs. The third thing I have to feed in is something called an artifact path. That is, where do we find the binaries that know how to generate this circuit? So when a ZK circuit is compiled, it generates a proving key, a verification key, and also a witness generator. Don't worry about what those are, but there's some like big binary things that the prover and verifier have to agree with. We distribute these via NPM. We also put them on various CDNs so you can download them. So you have to just decide for your app, are you going to download them, put them on disk, give a path to them? Are you going to download them from a URL? There are options. Once you've got these things together, the GPC proof function will generate the proof. Like it puts together that configuration, it picks a circuit that fits that configuration with enough modules, it downloads the corresponding artifacts for that circuit, and it generates the proof. And then the last thing it does, oh, I should have gone to the next slide, here we go. So it needs to compile down all those inputs into circuit signals that can feed into the actual ZK circuit. Which are, mathematical field elements, as I mentioned. And then after it's done and it gets a valid proof, it will decompile some of the outputs and turn them into what's called the revealed claims object. So it comes out of a proof. You've got the actual mathematical proof. That's just opaque numbers that are needed by the verifier. That's the actual ZK part. You've got a bound config, which is exactly like the configuration that you fed in, except that now it contains the identifier of the circuit that was selected so that the verifier knows how to verify it correctly. And then you've got the revealed claims. If I revealed that I am a licensed driver, driver equals true, that would be in this object. If I revealed like my name, etc., that would be here. And that's what the decompiling is for. It's taking the circuit outputs and turning them back into a string or whatever the representative thing is. Okay, so those three things are exactly what I should send to a verifier, whoever I'm going to prove this to. They need those three things. They also need an artifact path to download the corresponding verification key. And then they can verify the proof. They just do very much the same thing. They're going to compile some of those inputs back down into ZK land where there are circuit signals. They're going to verify the proof, and they're going to say yes or no whether it's valid. And gravy. We're at the end, and hopefully everything went right, and I've proven what I wanted to prove to you. So final takeaways, summary of what this was a bit of a speed run through. So pods are data that's designed to be proven about. Any pod is a signed attestation of something, whether it's I have a ticket, whether it's I have a driver's license, etc. GPCs allow you to flexibly make proofs about those pods by using modular circuits, which can be configured using a JSON-like configuration language. And you can the system will auto-select the circuit that you need depending on your configuration. So all your app needs to do is say, please make me a proof of this with these inputs, and everything else is handled for you. And then the last step is the verifier verifies the proof, and then the apps have to decide what things they trust. How do you trust that this is the correct proof? Like I alluded to before, you should check that this ID card was actually signed by the government. You should know the public key, or you should know the event ID for Devcon. You should also check, and I'll say a little more about this in the deep dive, that like the configuration that was sent to you was actually the configuration you asked for. So you don't want the prover to say, oh, I have a proof of something, but not necessarily the thing you asked for. That's something that you should check as well. But once you do all of that, like this end-to-end should be very solid, and you should be getting the information you need. Okay, that's it for the speedrun intro. Please check out our documentation. They're on pod.org that just went live yesterday. And also there's a link that just went by, t.me/zoopass to join the Telegram group. And yeah, let's go do some Q&A. All right, where do you store the semaphore identity secret for users in ZooPass? So that's all client-side. ZooPass stores all of your private data client-side. The ZooPass server is aware of your public key, because that's how it can make sure that you get issued the right Devcon tickets and things like that. But yeah, ZooPass is a client-side cryptographic data manager. To what extent is POD an open data standard? So I consider it open. We haven't published a spec for it. I should work on that. But all of our code is open source, so people can do interoperability with it. The pod format itself is very generic and interoperable. It's the GPC compiler that turns a pod into the specifics of what you need to prove with the specific GPC. So the GPCs are kind of less standard and generic, though they also could be used on multiple platforms. We do have an example of GPC verification on chain that just started working a couple days ago. So all that is possible outside of a browser, but we don't have as many examples there as we do on the pod data. Can we scroll down? Is there anything more? Can you compare pod to verifiable credential? Yes. This is something I looked into. Pod is simpler. It doesn't really have a fixed schema or anything that ties it into a specific standard. You could put JSON LD based verifiable credential data in a pod if you wanted to, but a pod is much more flexible. At the cryptographic level, there is a difference in the kind of Merkle tree we use. The pod uses the lean IMT, which is something that Semaphore created, which is much shallower because pods tend to be relatively small. As opposed to the sparse Merkle tree that is used, at least for the implementation of verifiable credentials that I'm aware of, which is the one from IDEN 3. That is a much deeper Merkle tree, but it can do things like prove absence of an entry, which pods can't do. Okay, what else do we have? How frequent is pod refresh? Very frequent so far, but we're hoping to keep it much more stable after Devcon. I don't have a strong answer to that. What else? How do you convert JSON to a Merkle tree? Please stick around for the deep dive session that's coming up. I'll tell you all about that. What else? Yeah, so in the example prover and verifier, the user's device can generate the proof, and that's why everything has to work in a browser on a phone. Client-side proving is definitely the default in ZooPass. Not every app has to do it. These are libraries. You can call them wherever you want. There's much more difference between verifiers, whether they're doing server-side verification or client-side verification. That depends what your use case is and what you're protecting against. Are the issued credentials signed and the proof that the credential, oops, we scrolled away. We do not use BSS signatures to verify partial properties. That's what we use the Merkle tree for. Again, more details on that coming up. Is it possible to make information in ZooPass portable? I think that pods do make that possible, yes, as long as it's a pod. And there are APIs for getting data out of ZooPass if you want to. That's called the Z API, at which point you can take this to whatever platform you want. We have implementations of pods in Python, C, and Rust for various projects, so it's not too hard to do. How do apps know whether a proof from a verifier is legit? Well, the framework tells you that it is a valid proof, and it will confirm for you that this configuration and these revealed claims and this proof match up and are valid. So the prover couldn't have cheated about that. What they could cheat about is app-level semantics. So if you asked for a proof of a driver's license and I sent you a proof of a frog instead, that's something that the framework can't tell you because it just says that's a valid proof. So you do have to check, is that the config I asked for? Is the signer of this driver's license the government, et cetera? But yeah, that's the kind of level of verification you get. Okay, I think that's it. Can we go back to the slides briefly? Okay, those of you who are collecting frogs, I've got something for you if we can switch back to my slides. Oh yeah. We'll leave that up for a minute or two. I think we've got like 3 minutes before the next session starts anyway, so feel free to frog away. Okay, and as I said, we're going to go straight into a deep dive session, which is going to be 90 minutes. We probably won't use the whole thing, but that's what we're scheduled for. So stick around if you want more details to answer any of those questions. All right. Thank you again, everyone. Thanks for everyone who stuck around for the deep dive session. I know these are being recorded, so anyone who's watching this session online, you may want to go back to that one first. It'll give a more gentle introduction. This session should be a little bit less rushed because we have a bit more time, but it's definitely going to get a little more technical, and I hope I can answer some of the questions that you may have had after the first session. So we're going to cover two things. I'm going to do a deep dive into how pods work, how we build them into a Merkle tree, what makes them provable, and then how that kind of proof compilation step happens that turns things into a circuit. And then my colleague Ahmad over here is going to take over and talk to you a little bit about the actual circuits underneath that, how we make them modular, how we make them these very flexible proofs. Okay, so let's review very briefly. So we're building this pod ecosystem where issuers issue credentials or attestations that may have come from some non-ZK friendly data source outside of our ecosystem, such as like the Pretix database that Devcon tickets come from. You're going to hold them in ZooPass or somewhere else. You can use pods in whatever app you want. ZooPass is optional. But we let users hold their own data. And then that user can, in response to a request, make a proof about that data in order to prove, I'm a licensed driver, I'm over 21, I have a ticket to Devcon, et cetera. So this is what we're trying to enable. So pod is a data format that makes ZK proofs easy. We use Merkleization, or rather we build a Merkle tree. I don't know if Merkleization is actually a word, but I will continue to use it. We do it in a deterministic and repeatable way, and we use this data structure so that individual entries are easy to make proofs about without having to prove every entry of the pod at once. And I'm going to, in this session, go a lot deeper on how that works. The other thing that makes this easily provable is we use ZK-friendly primitives. All of the underlying math is based on the baby jub prime field. That's those like prime numbers that were, or numbers modulo a prime number that I referred to earlier. We use a Poseidon hash and an EDDSA signing. These are two algorithms that can operate over this baby jub prime field. And the proof compiler plays an important role, which is that there are some things that are not ZK friendly to verify, but as long as they are public and can be verified by the verifier directly, they don't have to be in the circuit. And I'll show you a little bit more about how we make that work. So a reminder of what a pod looks like. I've cut this pod down to only 3 entries just so that everything fits on a slide, but it's otherwise the same as the driver's license I showed you before. It's got a name, it's got a date of birth, and it's got the public key of the card holder. So how do I sign this in a ZK-friendly way? Like, right, the normal way you would sign a JSON is you have to just sign it like a string, and you have to be very careful that it's all in the same order, otherwise your signatures is wrong. So we've got a better way in pods that makes it much more provable. So what I'm going to start with is I'm going to take all those entries, and the first thing I'm going to do is I'm going to alphabetize them to make sure that they're always in the same order. Entries actually come from entry names come from a pretty limited character set. They basically match an identifier in most programming languages. It's like ASCII plus numbers and underscores. So there isn't any Unicode question about like what the alphabetical order is. It's pretty clear. So we do that. We put the names and the values adjacent, and then we hash them all. And in this diagram, and in the future diagrams, green is something that is ZK friendly. I can do it inside of a circuit if I want to. Red is something that is not ZK friendly. I can't do it inside of a circuit, at least not efficiently, not in a browser on a phone. There are certainly ways of doing non-ZK friendly things in circuits. They're just really big circuits. So all of the name hashes and any of the string values that I want to hash, I'm using SHA-256. That's not a ZK friendly hash function. So that means that those strings are going to be represented in a circuit only by their hash, not by the actual string, because the circuit can't repeat the hashing. I mean, that wouldn't be very ZK friendly anyway, because strings are variable size, and ZK circuits don't like variable size things. But this is the approach that we've taken. The green P's here, that's the Poseidon hash. So a date is a number, so I can use the Poseidon hash function to make a hash that is ZK friendly. The same is true of the public key. A public key is actually 2 numbers, so the P here is actually a 2-input Poseidon hash rather than a 1-input Poseidon hash. The diagram is lying a little bit, but it's still ZK friendly. It's something that I could verify in a circuit later if I want to. Okay, that's step 1. I haven't built a tree yet. I've just done a bunch of hashing. So let's start building a tree. We're going to hash together the adjacent elements. That means that the name and value that correspond to each other are always hashed together to get a new value. These ABCs at the top, those are just the hash that results in hashing together the previous 2 hashes. Okay, so we're starting to look a little bit like a tree. Let's keep going. Next level up, I'm just going to keep hashing together adjacent elements. This is a pretty standard Merkle tree. There is an open question here of like, what do I do when my tree isn't a multiple of, or a power of 2? The way we do that in the particular version of the Merkle tree we use is we just skip that level. So when we go up to the next level, we just take that value C, we feed it up to the next level unchanged. This is a data structure called a lean IMT, IMT standing for incremental Merkle tree. It was built for Semaphore by the PSE team, and we're just reusing it here. It is a very lightweight Merkle tree and works particularly well for small trees. Most pods right now are less than 16 elements or less than 32 elements. You can go as big as you want, but the circuits just get a little bit bigger with the depth of the tree. So the lean IMT works very well and very efficiently for small trees. Okay, so now that we've gotten to the top, we've done all these hashes, we've got one hash, and that's called the Merkle root. In Merkle trees, that's a thing that you might publish to prove that you're a member of a group, for instance. In the case of pods, we call that Merkle root a content ID. And that's the thing that I mentioned earlier is going to represent this pod. The same content put through this same process will always generate the same content ID. So we make this a first-class concept that what the pod's content is. This is its hash, essentially. Now that we got the content ID, that's when we can actually sign it. And as I mentioned earlier, the content ID is actually the thing that's signed. You're not feeding in the names and values directly to any signature algorithm. You're just doing this Merkleization and then feeding the content ID into the signature algorithm. You're also going to feed in your private key if you're the issuer, and you're going to get out a signature. EDDSA signing, you notice that that's kind of a gradient between green and red. It is a ZK-friendly signature scheme, but it turns out that there's a key generation phase in the signing step that isn't ZK-friendly. So from your private key, it's actually hard to generate a signature in a ZK circuit. That's not usually a problem for us, because all you need to do is verify it. Like if you ever wanted to do the ZK circuit equivalent of signing, you would just sign outside and then stick the signature in and verify it in the circuit, and you're good anyway. But I'm trying to be correct about my color coding here, because I'm that kind of pedantic. Okay, so we've got this thing that represents the entire pod. How do I prove one entry of that pod? That's the thing I most often want to do in one of my ZK circuits. So this is what Merkle trees are for, if you've seen them before. This is called a technique called a Merkle membership proof, that if I want to prove that I have this entry called date of birth, I don't have to give you the whole tree, I just have to give you the path up the tree and give you the sibling that corresponds to the rest of the tree at that level. And if you're a verifier, and I give you all of the values that are shown here, but not the ones that were deleted, you can verify that all this is correct. Right? You can take the name and value and hash them, you get B, you can then take A and hash it with B and get X, you can take Y, which I gave you, and hash it with X to get the content ID, and you can validate the signature. So here I've just like avoided having to give you all of the elements, but you can still validate that this is a valid pod. So that's pretty cool. Let me formalize this. So this is the standard field you'd have in what's called a Merkle membership proof or an entry proof. So the root is the content ID. The leaf, we always set the name of the entry to be the leaf. That's a little bit arbitrary. The depth in this case is 3. In order to validate the proof, you have to know how deep the tree is. We've also got what's called an index. This is telling you when you get those siblings along the way, are they coming from the left or coming from the right? That's because our hash function, when it takes 2 inputs, the 2 inputs are not reversible. So you have to know which direction the tree goes to go up. So that's what the index is for. You have to get those sibling hashes. And this is an interesting thing that I didn't realize until I built this. The value hash that corresponds to this name is right there in the list of siblings. So it doesn't actually have to be fed into the circuit as a separate element. It's just part of the Merkle proof. It has to be there anyway, which will be useful later. I've got the value, and then I've got my public key and my signature for verifying. So this is what's called a Merkle proof. It's not a ZK proof. When I built this, I initially thought, oh, well, if all you have to do is prove one element of a pod, one entry, I should say, because that's the word we use, I could just send you the Merkle proof, and I don't have to make a ZK proof at all. Wouldn't that be easier? It's certainly a lot cheaper. Anyone here have an idea of why I can't do that? Why it would be a bad idea? Why it might be unsafe? Well, I mean, disclosing the signature doesn't necessarily obviously mean that I'm disclosing anything. Like, what would the attack be? Can you answer that? Oh yeah, the siblings, yes. So what would you do with that if you were an attacker? Yeah, precisely. So these are hashes. It's hard to reverse a hash. But if the values themselves come from a relatively small set, you can use a hash to try and guess what the value is, right? So this is much like a rainbow table attack on a password list. Like, if you leak the hash of something, it is much easier to find out what that thing is than if you don't have that hash. So that's why we don't usually send these Merkle proofs around directly outside of a circuit. Thank you for that. And that was something I actually learned while building this. I'm like, oh, that would be easier, wouldn't it? Well, it's easier because it's not secure, as it turns out, unfortunately. So the next step here is we put this inside of a snark. So now, instead of drawing a diagram of like the work I do in my code, this is now a diagram of an actual ZK circuit. But it's very much like the previous one. And then on the right side, I've basically grayed out all of the fields that I'm not revealing. One of the magic things about a ZK proof is that I can choose which inputs are public and which ones are private. So the only things that have to be public are the name hash of the leaf, because you have to know, like, you aren't going to accept driver equals true if you don't know that the name is actually driver. So that's always public. And then the public key that signed the pod has to be public, so you can verify that, with some exceptions. And if you have a more complicated circuit, you don't have to reveal that. You can instead prove that it's part of a known list or something like that. But at this level, it's always going to be public. Everything else is private. Did you notice the trick that I pulled there? I feel like you should probably be asking questions. Right? Something disappeared. So the name hash disappeared. That's because that's not a ZK-friendly hash. You have an question? We're not using Ketchak, we're using SHA-256, but it's also non-ZK friendly. It's because it's a string, and a string being variable length is not going to be ZK friendly anyway, at least within the limitations that we set for ourselves. Like, you can prove things about strings, there are ZK friendly ways of hashing that, but it's not very friendly because of the variable length. So for strings, we always use the SHA hash, and we do it outside of the circuit. This is why, or another reason why, the name of an entry always has to be public. That means that the verifier can take the name as a string, the verifier can hash it using SHA-256, get the name hash, feed that into the circuit, and be confident that that hash really does correspond to the name driver, or I guess it was date of birth in this example. Yeah, so that's the other thing that is important here, that there is a little bit of work the verifier has to do outside of the circuit. They're not just going to check the ZK proof, they're going to check some of the inputs to make sure that they correspond, usually just by hashing them again. They're not really checking so much as recalculating. Okay, so the last step, this is now a proof of one element of a pod, but it's not modular. I said that GPC circuits are meant to be modular. Well, the way I make it modular is I just slice it up. So this, in one of our GPC circuits, would be represented by 3 different modules. The object module, which proves that a content ID is properly signed, that proves a pod. An entry module that proves that this entry or this name exists in this pod. And then a numeric value module, we call it, because we can only prove the actual value in the circuit if it's a ZK-friendly hash function, which only happens if it's a number. So the numeric value module lets you prove that the value exists. Okay, let me review what we got through all of those diagrams. So an object is made of entries, which are named value pairs. The name and the value are represented in the circuit by their hash, which might be a Poseidon hash or might be a SHA hash. And we use the type hints that come in with the data to know how to hash the value. Is it an integer? Is it a date, which I'm going to convert to an integer? Is it a string? Is it a set of bytes? Is it a public key, et cetera? We generate a content ID by building a Merkle tree, and that means that we can make proofs about individual parts of it, and we make a signature on the content ID to make an attestation. So the P in pod, I usually use it to mean provable. It also can mean another thing, which is portable. One thing that I like about the data format that I've described and the process I described is that there's nothing in there about a string representation or how you have to canonicalize it the way you would sign a JSON. It's all about math. So if you can do that same math and get together the same content ID, then you have a pod and it's valid. That means that while we do support a JSON format for sending pods around because it's convenient, you don't have to use that. You can save it in a binary format. You could use a protobuf. The Frog Crypto game has a different JSON format that's a little bit more nicely readable for players, and it all is just as valid a pod. Okay, but a pod also is provable. It allows for efficient ZK circuits because of the hashing function and signature function we chose. In the ZK circuit, there's a fixed cost per pod to validate the signature. There's a fixed cost per entry to validate the entry, and then a ZK snark can verify all of this. This is the full list of value types that we currently support. It will probably extend. I'm not going to go through all of this in detail. Mainly, they are what you would expect. A few interesting details. Any value can be compared for equality because we just look at that hash and can compare 2 value hashes together. Some values will be equal to values of other types. For instance, like the Boolean with the value 1 and an integer with the value 1 are actually the same value. So keep that in mind if you're ever using this in your checks. But only certain values can be compared in an ordered way, meaning less than, greater than, etc. Those are numerical values. Right? You can't do a less than on a string in a GPC circuit just because the string is only represented by its hash. Whereas for a numeric value, you can prove that, oh, this is the value, and I can check the hash in the circuit, at which point I can feed that value into further logic to check greater than or less than. But also because of the some of the limitations of what you can do efficiently in our particular circuit language. Comparable things are limited to 64 bits in our circuit. That's an aspect of the circuit. We could make a module for comparing things that were bigger. We just limited it to 64 bits. Whereas a cryptographic number can be anything that fits in a field element. You'd use that for a hash, but you're probably not going to check those for greater than or less than. Okay, one last bit of detail getting into how we compile down to circuits before I hand off to Ahmad to explain those circuits. This is the diagram I showed before. I'm not going to go through it again. But I want to talk a little bit more about the compile and decompile steps that happen in this diagram where we bridge into the world of ZK circuits. So your GPC is a modular circuit. It's made up of modules that are basically sliced up the circuit that I showed you earlier, plus other things. Like, right, I showed you the object, the entry, and the numeric value. Ahmad's going to show you a lot more. The modules are connected to each other by passing around verified values, such as a value hash, such as a name, or such as a numeric value. Like, those are all examples in the previous diagrams of a value that we fed from one module into another. And there are public inputs to the circuit that say, okay, something like entry module number 3 is going to take its content ID input from object module number 1. And that's how you would wire these things together that say that, oh, the first object that I proved has this entry, and I want to make those correspond to each other, and then it's going to validate in the circuit that that content ID really is the same. So if you think in terms of hardware, there are a bunch of like multiplexers and demultiplexers that are feeding things around. If you think in terms of software, it's a bunch of like if statements essentially. And all of those wiring signals or configuration signals are by definition public. They won't be hidden because the verifier has to send in the same configuration to make sure that they're verifying the same proof. Okay, and lastly, as I mentioned, the GPC circuits come from a family. We generate circuits with different sizes. For instance, a typical circuit that we use for ticket proofs has one object, a max of 5 entries, 2 numeric values on which you can do things like less than or greater than, one list that you can check membership in, et cetera. And we generate a whole family of these things with different sizes. You can just pick the one that is cheapest for what you need. And you have to download the artifacts for the circuit that you picked. And this is like a vague size range. Proving artifacts are pretty big, at least on the level of proving on a mobile phone. Verification artifacts are very small. So if all you have to do is verification, it might even be reasonable to just build all the artifacts directly into your app bundle. But for proving, you probably don't want to do that. You probably want to put them somewhere else. Okay, this is kind of a restatement of this. So the proof compiler takes the configuration, takes the inputs, including the pods, the user secret private key, and things like lists and tuples that you can generate, uses them to compile down to the proof outputs using, there we go, the proof compiler. So what this is going to do, much like a programming language compiler, it comes in multiple phases. First thing we're going to do is check all the inputs, that they are valid by the definition. This includes some things like range checks that are actually important. For instance, if you're going to prove that a value is in a range between min and max, our circuits only work if min and max are 64-bit numbers and not bigger than that, because of certain assumptions. So that means both that those numbers are always going to be public because they're part of the configuration, but that the prover and verifier both are going to check that to make sure so that they can trust the output of the circuit. While checking the configuration, the compiler is going to determine what are the requirements, right? How many modules do I need in order to generate this proof? It's going to pick the smallest circuit that fits. Alternately, you can optionally just feed in a circuit identifier if you want to say, always pick this circuit, please, because that's the one that my verifier knows how to verify. Then it's going to hash and Merkleize all the inputs following the procedure that I showed you earlier in order to format them and the configuration as input signals to the circuit. Potentially a lot of them if you've got like a list of 200 entries and have to feed them all in. But usually it's in the tens of inputs, not the hundreds. You're going to download the artifacts, the proving key and the witness generator in this case, so that you can then finally generate the proof. And then you're going to decompile some of the circuit outputs back into the revealed claims. And some of this logic actually has to bypass the circuit, right? If what I revealed was a string and what comes out of the circuit is that string's hash, I'm going to go look back at the inputs to get the actual string, because I can't reverse the hash, but the prover has access to that, so you're going to just copy that string into the revealed claims. Okay, the verifier is going to go through all of these steps in a very similar way, and that's because the verifier is double checking that the prover did everything right. All the stuff that happens outside of the circuit that is security relevant, the verifier has to repeat because you're not trusting the prover, right? Things inside the circuit are being verified by the ZK proof itself, but anything outside of that, the verifier just repeats the work, including things like checking that the bounds are within 64 bits, and they can do that, and then the proof will be fine. The only differences, which I've called out in bold here, are that the verifier will, rather than picking a circuit, it confirms that the circuit that was selected actually fits the inputs. It downloads the verification key instead of the proving key, which is much smaller, and then it can verify the proof. And then, as I mentioned in the intro session, there is some work to be done after the verify compiler and the verifier is done. Right? The verifier tells you, this is a valid proof with this configuration. You should make sure that that's the configuration you asked for. You might do it by just, before calling the verifier, like replace the configuration the prover gave you with the one you expected, and that'll just work. You copy over the circuit identifier to do this. We have some examples. But you might also do something more complicated where you say, like, this isn't a configuration that I will accept. It might actually be stricter than the one I asked for. It might be slightly differently formatted. That's up to you. And then also, you should check whatever's in the revealed claims. They were revealed for a reason, presumably. So you should check that that's something you actually want to accept, and then go do whatever you're going to do with it in your application. Okay, that is it for me. My throat is feeling a little bit parched from all this talking. So I'm going to hand off to Ahmad now, who's going to take you into how do we actually do what's inside of the circuit. And he's going to plug in his own laptop to do so.
All right, so we'll be going through GPCs in a bit more detail. So when I initially prepared this talk, I had some background slides on pods. Maybe I'll do a very quick recap of what was covered in the last couple of talks. But the TLDR is that GPCs allow us to make ZK proofs about pods. So that's, essentially that's the point we're trying to drive home. And if you want to look up the code on GitHub, here's a QR code to our repo. So we've got a mono repo, pod package, GPC compiler package, GP circuits. It's all in TypeScript. There is an ongoing, let's say, initiative to do more in Rust. If you actually look for the parknet repo, 0xpark/parknet, actually should have put the code up, then you'll find the beginnings of a Rust implementation of much of what we've done on the pod side at least, not the GPC side yet. So yeah, we already know pods are cryptographically signed key value store. Has anybody read the blog post by Joel Gustafsson? Does that ring a bell? Merkleizing the key value store for fun and profit. I mean, yeah, this isn't an entirely new idea, but it is quite solid cryptographically. Andrew's already gone into detail on how, we Merkleize a pod, but you basically start with the JSON object, you appropriately Merkleize it, you sign the Merkle root, and bam, pod. So we've already used terms like content ID, so that's the root hash. The signature is the EDDSA Poseidon signature associated with the pod. Yeah, and then we basically have a series of entries. So key value pair is the name of an entry, the value of an entry. So that's the terminology we use. Just to go through some examples, because I'm going to show you some GPC configs corresponding to certain examples, but imagine a world where we had pods as ID cards, ID cards with pods underlying them. So here would be one such example. We use JSON because JSON is the accepted, data representation format in this world. We have various fields in our ID pod, like name, date of birth, semaphore ID, public semaphore ID. So we basically take something like this. The state would actually issue a pod with this underlying data. And once a pod is constructed, you basically have the content consisting of this part, plus the signature, plus the signer's public key. This would be the state that signed the ID pod. And the content ID, which is the Merkle root, that can be reconstructed in a deterministic way because we already have conventions about how you arrange all of these entries. The ticket should have an event ID, so the event, the ticket's associated with, a product ID like, regular ticket, maybe a speaker's ticket, a ticket ID to identify the individual person, and then maybe the attendee has a semaphore ID. Well, you all do via ZooPass. So that would also be embedded in there. And in much the same way, we obtain an appropriate JavaScript object according to the current implementation that represents our pod. Now, life before pods was quite complicated as far as ZK proofs are concerned. You'd always have to define an appropriate data structure, choose some signature scheme, find a way to just cram that data into a circuit, right? And you're going to have to probably pad things along the way, do various little ad hoc things necessary for your application, glue code, and then who knows what comes next, and eventually you profit, hopefully. And that's how it was before pods. And after pods, things get simpler. So now I'm going to talk more about the ZK side of things, how we can, what sorts of proofs we can make about pods with our GPC framework, general purpose circuits. So basically, we have a many parameter family of reusable circuits. So depending on the proof, you may or may not need to prove about just one pod, multiple pods, maybe pods with many entries, pods with 5 entries, whatever. We need various circuits to accommodate all of these possibilities, so many parameters. And yeah, each circuit has a number of modules with a specific purpose that I'll go into in a moment. And this is how we make ZK proofs about pods. So here are some examples that relate back to the pods I showed you a second ago. So you could say, you want to prove to somebody that you possess an unredacted speaker's ticket to Prague Crypto 2023, which was part of DevConnect. So as you can see, I have updated my examples, but it's a concrete example. Another proof you might want to make is that a ticket to a DevConnect 2023 event was issued to me, without necessarily revealing what event, and proving that you are over the age of 18 without revealing who you are. So these are some things you might want to prove. So we can be more explicit about what it is we're saying in each of these examples. So for the first example, you are saying, I possess a ticket pod. It is signed by the organizers of the event. So for Prague Crypto 2023, it would have been 0xPark PSE. It contains the event ID corresponding to Prague Crypto 2023. Its product ID corresponds to that of a speaker's ticket. And its ticket ID entry value does not lie in the list of redacted tickets, right? And you could always have a field in the ticket saying is redacted, but why would you ever set that to true? So in this case, there would be some universal list of tickets that are no longer valid. And then with the second example, that a ticket was issued to you, you would say that you possess a ticket pod. It's signed by an organizer of a DevConnect 2023 event. And it contains an event ID corresponding to one of those events. And you actually possess the private data corresponding to the semaphore ID that's embedded in the ticket. And finally, with proving that you're over the age of 18, you say that you possess an ID pod. It's signed by some trusted state. Its date of birth entry value, it lies in the appropriate range to prove that you're over 18. And you actually own the semaphore ID. So it really is your ID pod. So from the user's point of view, this should all be streamlined, by the way. I mean, there's going to be some web page you go to, and then you click, and then you get some pop-up, and it's like, yeah, select your pod, select it, prove, bam. You've proved what you needed to prove. That proof goes to the server, together with whatever you chose to reveal. I mean, what you choose to reveal is usually determined by the application. The developer would have baked that in. You can actually go through and make sure that you're not revealing something you don't want to reveal, in which case, don't make the proof. And then whatever it is you were trying to do, hopefully should come through. So here's a high-level description of the GPC compiler as a recap. As mentioned before, from the developer's perspective, depending on your application, you would form some kind of proof configuration, specifying what it is these pods, what properties these pods should have, the pods that go into the proof. So the application that the user interacts with will have both a proof configuration and proof inputs. The proof inputs will have all the private stuff that needs to be put into the circuit to generate the ZK proof you need. The proof configuration will have other details like has an entry called date of birth. Maybe date of birth should lie in a certain range, or this entry of this pod should lie in a certain list. Its value should lie in a certain list. And yeah, so you basically take these things. Something I'm kind of sweeping under the rug, I'll get to in a moment, is the family of circuits. I said that there's a many parameter family of circuits. Thing is, we've pre-generated, so we've done that for a certain, well, not a proper trusted ceremony, but we have some artifacts that you can use. But an additional input to many of these procedures is the family of circuits you're using. So there's a default value here that we provide, but you could just as well customize it. And the process goes as follows. You plug in the configuration and the inputs, and you put in this GPC proof box. The config and input are all checked. I mean, the user might be trying to prove they're over the age of 18, but if they're not over the age of 18 according to their ID pod, this will be caught here. And let's say it isn't caught here. You have a script kiddie, they basically comment out that line. Well, they're not going to be able to generate the ZK proof. They're going to go to cryptic error, right? Or even if they did try to, even if they commented out more lines further down the line, they're not going to come up with a valid proof. So here, this helps you not shoot yourself in the foot, essentially, in producing false proofs. Helps in debugging as well. So everything is checked, all the validity of all the statements, the types, etc. And then a circuit has to be chosen. Let's say you have 10 pods you want to prove about. You have to pick a circuit that's big enough to accommodate for that. So we essentially build up a data structure called GPC requirements, which is just an appropriate JSON that lists the various things we need. And then the circuit whose size is the smallest as far as number of constraints is chosen from a list. So something we haven't quite done, maybe we should think about this at some point, is who's interested in on-chain applications? Yeah, I mean, so besides, I mean, you don't really care about verification costs. You probably, I mean, proof size is not really much of a concern. It's more about input size. You might want to optimize for that. That's maybe something you might have to like do on your own. I believe there are a few projects that do that sort of thing. But that is another thing you might want to optimize for. But in our case, we just optimize for circuit size because then that reduces proving time. Because proving can take a long time if you just choose one of the larger ones. Inputs are config is canonicalized, I should say. So sometimes the proof configuration can contain unnecessary restrictions on the inputs. For example, you could say that a number should lie in the range, 0, 10, but not in the range 5, 10, right? I mean, it's unnecessary to specify it that way. So you could simplify that down to saying it, lies between 0 and 5, for example, or 0 and 4, depending on whether you're doing inclusive or exclusive bounds. But it basically brings it down to a canonical format, and then all the inputs are compiled in the sense that once we've chosen a circuit, in a circuit you don't have variable size loops, you don't have variable size, so there's going to be a lot of padding involved in various places. And we generally choose the padding so that everything is still logically consistent. For example, you could say you have a pod has an entry with a value that lies in some list, okay? List is, let's say, 5 entries long, but the circuit you chose says all lists have to have 10 entries. So what do? Pad with one of the existing entries. We choose the first one. That way, when you prove list membership, you're still proving the proper list membership you wanted to prove, right? Even with the padding. So we have to do all that. So we basically prepare all the inputs for the circuit, and then along the way. And finally, the revealed claims are included in that output. So basically, in our proof configuration, we might have chosen to reveal our date of birth and not actually check it in the circuit. For example, for the ID pod example, that would be amongst the revealed claims. And verifying is basically taking the output of that last process, plugging it into a box. The config is checked against the claims. You can't check everything because there is going to be private data, but you can check whatever's available in the revealed claims to make sure everything's consistent. And then you verify the proof. So just, using Snark.js in this case. And then output true or false. So going back to the examples, for example, I possess an unredacted speakers ticket to Prague Crypto 2023. We basically have the proof input, the proof config, I'll start with that. So we specify the pods that need to go into the proof. We only have one pod, ticket pod. Doesn't really matter what we call it here, it's just a label. And then so that should have an entry now. So it should have a sequence of entries, specifically event ID, product ID, ticket ID. We choose to reveal both event ID and product ID. Why? Because event ID will reveal what event it was, Prague Crypto, and product ID will tell us what kind of ticket it was. The ticket ID itself should not be revealed, so we say is revealed false, but we do specify it should not be a member of the list that we call redacted tickets. Now this list itself is going to be specified here in the proof inputs. Another thing I stated is that the signer's public key should be revealed, the signer of the ticket, because we do want to actually assert that it's a legit ticket, right? Anybody can issue a pod. You just need to make sure this is an authentic pod issued by the organizers of Prague Crypto 2023. And then proof input would basically just be the pods. You make sure that obviously ticket pod should coincide with the one you mean in the config. All this is done under the hood, by the way, in ZooPass when you make ZK proofs. You basically get that drop-down box. You get to choose the individual pods, and then you can make your proof. The membership list should be provided, again, by name, list of redacted tickets. And you might want to put a watermark in the proof inputs. So thing is, you could make this proof, and then somebody could take your same proof and try to submit it again, right? If you didn't have a watermark, nothing would stop them from asserting the same thing as you. So by putting a watermark like a timestamp or something associated with the session, you can guarantee it can't be reused. So yeah, that's essentially what you put into that GPC proof box. And then out of that, you'll get some Groth16 proof, which is some sequence of bytes, not here. And you get the bound config, which is just the proof config, JSON or JS object, together with a circuit identifier field, which contains some label that tells you what circuit configuration you chose. There is some, there is some logic behind the sequence of characters. Here's what it says. I've chosen the protopod GPC circuit with one object, 10 entries. It has a max Merkle depth, MD, of 6. What that means is the pods you put in are not going to be too big that they can't be accommodated by a Merkle tree of depth 6, yeah? So 2 to the 5 entries. 0 NV means 0 numeric values. In this particular proof, I don't need to say anything about any numbers per se. I'm just checking for list membership and I'm revealing some values. I don't need to say that, this entry is greater than 5 or this entry is greater than that entry. Nothing like that. So I don't need the numeric value module. And I certainly don't need the EI, entry inequality module, which is what would allow me to make those inequality comparisons. This is something Andrew talked about briefly. In order to say things about entries in the sense of inequalities, like greater than, less than, not equal to, that's a different story. But if I want to say one entry is greater than another, first I need to check they lie in an appropriate range, that they are 64-bit signed integers. That's the convention we use. But you do have to restrict the range to do this properly in ZK. So I don't need any of these modules. I do need a list membership module. That's what the L is for. I need one list, because I only have one list here to check that the ticket isn't redacted. Maybe it has 100 entries, So I need one list of 100 entries. I need 0 tuples. I haven't really combined any entries. You might want to combine entries to check that a tuple of entries lies in a list or doesn't lie in a list. And in this case, because this was Prog Crypto 2023, before we migrated to semaphore v4 IDs, I need one owner module, so that's the O, of semaphore v3, and 0 semaphore v4 modules. And then revealed claims. So up there you can see I chose to reveal the signer's public key, event ID, and product ID. And they're all revealed here amongst the revealed claims. The watermark is always revealed because that's part of the challenge in a sense. And the membership lists in question are also revealed. So that's that example. To assert that a ticket to a DevConnect 2023 event was issued to me, the approach is much the same. The only difference here is I actually form a pair consisting of the signer's public key and the signer's public key of the ticket pod that was issued and the event ID, and I basically check that that pair lies in the list of all DevConnect pairs, basically pairs of DevConnect event IDs together with signer's public keys to ensure that the ticket is from that list. And then on the other hand, I also assert that the attendee semaphore ID entry of that pod is my owner ID, and in fact it's of type semaphore v3. You could replace that with v4 if we were dealing with v4 IDs. So in this case, I think everything's self-explanatory except the circuit configuration changes. Everything is okay up until about here. Now I need one tuple of arity 2. So this is like the best case scenario, by the way. You might not necessarily get something that exactly fits your requirements. It could very well be that we haven't provided any circuit configurations with one object and a Merkle depth of size 6. Perhaps we only provided Merkle depth of size 5, in which case you would have gotten different parameters here. But this is just for the sake of illustration. And finally, we have the example proving that you are over the age of 18. In this case, what you want to do is show that the signer's public key is in the list of public keys of trusted states. Now, in this case, I've deliberately chosen a smaller list size, 10. I don't know if there are 10 states that we can actually trust in this world. But for the sake of example, 10. So things are much the same except for date of birth, where here we assert that it isn't revealed, so we're not revealing our date of birth, but we are asserting that it lies in the range 0 to 18 years ago specified as Unix time in this example. Yeah. And, and in this case, since we're actually using our semaphore ID, we can actually associate a nullifier with this particular proof, if we so choose. In this case, you can specify that as part of the owner section of the proof input, and that comes through with the revealed claims. So just a quick refresher, I've already alluded to this, but circuits have limitations compared to regular programs, mostly as far as like static versus dynamic memory. You've got to make sure everything's of a fixed length. All of our functions have to be naturally expressible in terms of addition, multiplication in a field. This motivates many of our constructions and much of what we do. And this is why we have to provide a number of templates to. Each object is, as I said, is a Merkleized structure. So you basically take your key value pairs, blah, 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 Merkle root. You sign that, you get a signature, you have a public key associated with that signature. You want to check that all that is consistent in the circuit. And we have one module that does that. It's the object module. And this will be done for each object provided to the circuit. Like I said, we pad things. So if you choose a big circuit that requires, 10 objects, but you've only got 4, then one of those objects is going to be repeated. And you're just going to have extra checks of the same sort. So yeah, public key, signature, content ID, which is that root hash, all check for consistency. Essentially just check the signature against the message given by the content ID. Now each entry you plug into the circuit, the way we do this is the entries are their own thing. It's not that you plug the objects in their entirety. You don't have to. You only plug in the entries that you need to prove something about. And then you specify which object they correspond to. So there's an index in there. We have a bunch of arrays. We have the array of like object content ID and other things. And you specify for each entry which pod object, underlying object it corresponds to. And what the entry module checks is that the entry actually does correspond to that pod that you specified. So you provide a Merkle proof of inclusion of that entry. So the root hash is recomputed, checked against the object hash, and we also, like as was mentioned earlier, the actual key, the name of the entry is passed in as a hash. That's also passed in here it's also checked against, it's in the Merkle proof. And in the end, if everything is good, the revealed entry value hash is spat out because we choose to reveal an entry or not reveal it. And by the way, if anything is not satisfied, the circuit just won't compile. That's what's going to happen. The proof is not going to compile, sorry, I should say. Yeah. Now, besides entries in a pod, it is part of the pod data structure, but for that reason, it is passed into the circuit. It's actually, passed in together with the object itself, So what happens inside our big circuit is that all of these are aggregated into an array, both the public key and the content ID. There are some things you could prove about the content ID. You could prove the content ID is a member of a list. That might be a bit weird because, who's publishing content IDs? But you can also say things like, I have a bunch of pods and they're all distinct. So that's something I'll get into in a moment. We actually have a module for that, the uniqueness module. So we basically take this data and we hash it so that it's treated just like any other entry. It can be used in all the constructions we have in ZK for proper entries. So you can check list membership. You can check for equality, non-equality, not inequality, because these things are going to be pretty big. They're probably going to be close to 254 bits, right? There's no guarantee that a hash is actually going to be a 64-bit signed integer in a field. I mean, why would you expect that? So that's what the virtual entry module does. And then for virtual or non-virtual entries, we might want to check if they're equal to one another. You might want to check if one entry value is equal to another entry value or is not equal to another entry value. For example, you could say I have 2 pods and they were signed by different parties. And in this case, we basically plug in the value hashes. We plug in an array consisting of all the entry value hashes together. And as part of your proof configuration, you would have specified whether you wanted to check for equality or non-equality. And then you've got the owner module. So if you chose to say that a certain entry in a pod was actually an owner ID, semaphore v3 or v4 type, then you ought to provide your semaphore secret as a private input to the circuit. And yeah, you basically specify which of the entries of the inputs corresponds to the semaphore commitment. You can plug in both a v3 and a v4 identity, by the way. So it is possible to actually have like a pod with a semaphore v3 identity, one with a v4 identity, and you prove that you have the secrets to both identities. That would be a way of establishing that you own both of those semaphore IDs. I mean, one such way. I mean, surely they're more direct. And yeah, you basically specify which of the entries does correspond to your semaphore ID. You plug in your secret. You might want to plug in a nullifier as well to invalidate this proof if somebody else wanted to come and use it later on. And you might or might not choose to reveal that nullifier hash. And in this case, either you output that nullifier hash or you output -1, which is our convention for the absence of data. And then we have the numeric value module. So here, like I said, entry values are passed in by hash by default. But sometimes you want to prove things about entry values, like they lie in certain ranges. And in this case, they have to be signed 64-bit ranges. So the numeric value is responsible for that. You plug in the actual the value corresponding to the entry that you're arguing about in this entry value hash array. You plug in the entry value hash and a lower bound and an upper bound, and those are checked in circuit. And assuming you've done that, you can also check whether such an entry is less than, greater than, less than or equal to, greater than or equal to. You can do whichever using the entry inequality module. So in this case, you just pass in a pair of entry values, and this box will just check if entry 1 is less than entry 2. And that's sufficient for checking any possible inequality. Why? Because we're going to get a Boolean out. So you could just flip it if you wanted to do the other way around, or you could just assume it's false if you wanted to do the other way around with an equal sign as well, like a non-strict inequality. So in the proof config, you don't have to think about that, like, oh, I can only do is less than or is not less than. No, you don't have to think about it. Just put in less than eq, greater than eq. It's all the same. It'll all be translated appropriately when compiled down to the circuit. So the compiler takes care of all these little things that you probably have thought about. You've probably done this before, but it's easy to mess up if you have to do this again and again, and keep. Then we have the tuple module. How do we handle tuples? Easy, we just hash them. So in this case, so in one of our examples, we had a pair of entry values, and we want to show that that pair lies in a list of pairs. So how do we handle that in the circuit? We actually hash the list of pairs. We hash the thing that we want to check is a member of this list of pairs, and then we check that the hash is a member of the list of hashes. And that's what the tuple module is responsible for. It basically just hashes everything away to obtain a tuple hash, which you can then treat the tuple as an entry in its own right, as far as the logic is concerned here. Then we have the list membership module. That one's fairly straightforward. We just do a linear search through the list. If we actually, we plug in the entry value hash and the list of hashes to check. Lists are always hashed anyway, entry by entry. So we're just doing simple arrays. In future, we might actually have pluggable Merkle trees so that you could actually do a Merkle membership. But for now, we just do linear lists because we only care about small sizes anyway, and it's fairly cheap. So yeah, the list membership module. And then we've also got the pod uniqueness module, as I mentioned. You might want to say the pods going into the circuit are all distinct as far as their content is concerned. And this one has a simple switch. I mean, you just plug in all the content IDs, and then you get a Boolean, 0 or 1, depending on whether all the content IDs are unique. And whether you want to impose that the content IDs are unique is up to the proof configuration. Constraint is put in, and that's it. There's nothing else about it. It's just to ensure that you don't reuse the same proof, or just have that the proof be associated with that particular session. Yeah, so life after pod and GPC should be a lot simpler. You just write down the data structure. then maybe use the GPC or GPC PCD library, or even the Z API, which uses all this stuff under the hood to, put your application together. Something comes next, and then profit, and we're good. So future directions for all of this would be more features. I already hinted at a few possibilities, like having some form of Merkle membership rather than a linear approach to list membership. More pods, more GPCs. It's the pod project is pretty young. Lots of frog pods going around, so I think we're getting more adoption by the day. And possibly a different stack for certain other applications. At the moment we're using Circom with Groth 16 in TypeScript. We can't do recursive proofs. What if you wanted to plug a pod proof into a GPC? Well, you can't really do that. It's not natural in this setting. People are going in this direction of recursive proofs. Maybe use something like Plonky 2 or whatever else is in fashion to get things done. Those are just some possible directions. So this is pretty much all I wanted to cover. What I usually do at the end of, or towards the end of such a talk, is maybe quickly go through the actual protopod GPC Circom file, but I think you can all look it up in the repo. Maybe it'd be good to turn to questions instead. I was given a QR code. Damn, it's really small. Let me see if I can make that a bit bigger. Or did you already reveal that QR code? No, you didn't. Okay. Yeah, let's do that. Should I maybe answer some questions? Because there have been some questions already. So,
I'll just show up the last few slides.
Yeah.
We'll jump to that. Okay, so a couple links just to tell you where to go for more. This was a lot in a deep dive session, so thank you all for sticking with us. But there is an all-day CLS from 0x Park about programmable cryptography tomorrow. All of that, I think, may be of interest to you, but in particular, there's a workshop in the afternoon, which is what that QR code is, that is going to be about ZooPass and the SDKs and things that you can do to build on pods. So hopefully some of you will join us for that. Also, check out the docs, check out the Telegram. And then here's the thing you've all been waiting for. We'll leave it up for a minute or so before we switch to questions. All right, everybody got your frog? Let's get to the questions. Okay, when making ZK proofs, are they already being done with the idea that they are anti-quantum, or are we still far from having those problems? We, as a team, are far from thinking about those problems, because as I said in my intro, we're limited to kind of tried and true technologies that live in a browser, and that limits our choices to not really being able to kind of pick and choose that much. Everything here is based on elliptic curve cryptography with the baby jub prime field and curve. So I don't think that that's guaranteed quantum resistant, but I don't think anyone's broken it yet. But yes, we have potentially will have problems with that in future, and that's why we'd want to investigate alternative avenues and proving systems like Ahmad alluded to. Could I compare and contrast pods with verifiable credentials? Yeah, that's something that I looked into. They do something very similar. Particularly the IDEN3 or Pravado ID system, where they use JSON LD to represent verifiable credentials and make proofs about them. It's a similar kind of Merkleization. They use a different kind of Merkle tree. They use a sparse Merkle tree, which is optimized for larger trees with deeper depth and can do things like prove absence of an entry. That's one of the limitations of our pod Merkle tree, that you cannot prove that an entry is absent, only that it's present. If you saw my list of data types for pod, one of those data types is null. that's actually there specifically. So if you want to prove that something doesn't have any other value, you can give it a null value and prove that it is present with a null value rather than proving absence. But for that, we get Merkle depths that are like 5 or 6 or 8 in most of our circuits, whereas the IDEN3 circuits for sparse Merkle trees have a default depth of 32 because they need to avoid collisions on the Merkle hash. So that's a technical difference. We're optimizing for like lots of small objects rather than a big complicated tree is kind of the trade-off we made there. But they are compatible in concept. There's no reason you couldn't take a verifiable credential and turn it into a pod. Pod is a much more general, like any names and values will go. Okay, what are some of the challenges, problems in this space? Anything we could look into and help? Ahmad may have more thoughts on that and some of the like crazy circuit stuff he's been doing. Like I know that lack of ability to do things like recursive proofs is definitely a limitation for us. The size of proofs that we can make in a browser on a phone is definitely a limitation for us. My kind of rough rule of thumb has been we have to keep things under about 100,000 constraints. If you've written Circom code, each constraint is kind of a mathematical equation. Our typical circuits right now are anywhere from like 8K constraints at the low end to like 30 or 40K, and that's going up to like 3 objects, 20 entries, etc. So you can't really do really, really big pods unless you're willing to take some extra time and some extra memory. It's all possible. What else? Is the circuit able to see the raw data or only the tree of hashes? How are range checks and comparisons done? I think Ahmad alluded to that when he was going through the modules, but only numeric values can go into a circuit directly. That's why you can't do like ordering comparison on a string, because that would require a string value to be in the circuit. But with numeric values, you can use the numeric value module to prove that this is the plain text value that corresponds to that hash. And then you can do things like range checks on that. And there's nothing stopping you from making more modules for more things. Let's see. Oops, sorry, you scrolled away from the top. Is there a way to integrate the automatic prover inside the smart contract? So proving in a smart contract has the disadvantage that all of the inputs, I think, are inherently public because that's how Ethereum works. So if there's nothing stopping you, I think smart contracts are Turing complete. I think the size of the input would be very large and you'd have confidentiality problems. But more useful is verification on-chain, and we already have that working. Using the verify compiler is kind of used as a pre-step to take the like friendly objects and compile them down into the raw circuit inputs, and you can send those on-chain and have the on-chain verifier verify that. There's a demo app called Frog Juice that lets you juice your frogs on-chain. Is it possible to tamper with the GPC config to compile a generic circuit that can allow proving false statements? No. Assuming that you use the GPC compiler as is, and assuming it doesn't have any major bugs, it hasn't been audited yet, you shouldn't be able to prove false statements. What you can do is prove meaningless statements, right? Like, I have a pod that contains a field called driver. I mean, I can make any pod like that. And if what someone asked you to do was prove that you're over 18, that is a meaningless statement for that purpose. So that's a not entirely solved problem. Like in the easy case where the prover or the verifier first asks for this config and the prover sends it back, it's very easy for the verifier just to say, like, is that the config I asked for? Yes or no? Just like do a deep comparison. If you want to get fancier than that, like, oh, you can prove a statement that is like stricter than what I asked for instance, like that's a bit more like logical deduction. That's not easy, but most cases don't really need that. In the example of a module comparing 2 hashes, why take a list and an index instead of just a value? I'm not sure what that's about.
I'm assuming that's the entry constraint module, most likely. Well, I mean, it could go either way, but maybe you had a particularly strong response to that.
I may have just figured out what this is. Feel free to jump up if you're the person who put in this question. What the index you're seeing may actually be part of that routing logic, the multiplexers that I mentioned. So it's not that the comparison is comparing something with a list. The comparison is comparing two hashes, but the input to the comparison, one of them is the entry that this module is attached to, so it's always a fixed input. The other one, you can compare it to any of the other entries. So the way that we accomplish that in the circuit is there's a list of the hashes of all of the entries, and then you use this index to pick which one are you comparing to. So that's part of the configurability. It's not about the list being a value that you're checking. The list is all of the possible inputs, and the configurability is the index. Is there any standard supported for pod? I don't know what you mean by standard. So everything's open source right now. The code is the standard. I realize that that's not a great answer. I would like to document this as a proper, at least a protocol spec, essentially. Whether we would standardize it, I think, is up to adoption and how important that is. I didn't want to slow us down in our initial development by getting the W3C involved or their IETF or something like that to standardize things, because that can take years. I'd rather first build something that works, iterate on it with some feedback. But yeah, I think that more of the format should be more closely documented. That's something that we're going to work on. In order for this to work in the governmental settings, do issuer, verifier, and prover need to agree in advance on the pod structure? So yes, a pod inherently is schemaless. You can put any names and values in it that you want, but there does have to be some agreement between the prover and verifier of what does a driver's license look like? If you want me to make a proof of a driver's license, we have to agree on what the names of the values are. There are two ways that the issuer can actually express that. One is just if the only thing you ever sign with this public key is driver's licenses, then the attestation that is this pod implicitly is attesting that it's a driver's license, because this is the public key that is only used for driver's licenses. The other thing that is a recommendation but not enforced by the system is an entry called pod type that is meant to be a unique string for your app to specify this is what this pod is for, which probably also specifies what the entries should be and what their types should be. But there is nothing inside of our libraries that will enforce a schema, other than the proof config itself is implicitly enforcing a schema of the things that are proven about. Yeah. Yeah. So anything that is not mentioned in your proof config is not being cryptographically proven. You may be able to trust it because this issuer states that they only sign things that follow this whole schema. But cryptographically, if the only thing you prove about is 2 entries of a pod and that pod actually has 12 entries, a pod without the other 10 entries would be provable by that configuration. Anything that you want to be sure is true, you have to prove about, unless you're willing to just trust the issuer. But you can do things like prove an entry is present if that's all you want without revealing its value. That is a way of checking that the schema is present. But it's really up to the specific use case. Did you have a question?
It's answered.
Oh, okay. Any other live questions? Feel free to put up a hand. Yeah. Can you pass over the mic?
Thank you. How do you approach proving uniqueness in dynamic things like ownership of a name or address in a chat room?
Interesting. I don't think that's directly solved by GPCs, other than the standard approach of pick a random number that's big enough and it probably won't overlap. But all you can pods are not inherently unique. They are defined by their contents. So a given pod set of contents will always have the same content ID, and then if the same signer signs it, it will have the same signature. Our signature algorithm is deterministic. So there's no inherent uniqueness there, but you can put a unique user identifier or something like that in a pod. You can prove if you put multiple pods in a single proof, you can prove that the individual ones are unique, or you can prove that the user ID that's represented in the pod is not the same as this other one. But I think that's about as far as you can go with this system. Proving uniqueness across all of the users in a chat group or something like that is not entirely in scope. But maybe there's something more specific that I can suggest for you.
Thanks.
Any other questions? All right. Well, thank you all for joining us. We'll stick around for a couple more minutes if anyone wants to chat in person, but otherwise, I hope to see some of you at the workshops tomorrow at the Programmable Crypto CLS.
Thank you. Okay. Hello, everyone, and welcome to our workshop about bringing an AI on-chain, and more specifically, hello, team, how to build and run your own agent that is betting on prediction markets on-chain. Yes, please. Okay. Oh, it's good? Cool. Thank you very much. But are they able to see my slides? Okay, now it's there. Thank you very much. So, my name is Peter. I work as LLM engineer at Gnosis, and at the same time, I'm doing my PhD in AI. But I would leave the introduction there. But if anyone is interested in the project that I work on or anything similar, feel free to go to my website, yung.ninja, where you can find one of the agents with my CV in the memory and some prompting around it to be a bit more interesting. But that's enough about me, and let's go to the actual workshops. So today we will mix 3 different concepts. So we will mix prediction markets, Web3, and agents. So there already were some talks about prediction markets, so I bet most of you are already familiar that prediction markets and Web3 are kind of popular mix nowadays, but we will bring their agents as well. And why? Because we will try to build an autonomous system that is more or less capable of existing or living on its own. Most importantly, without any major human interactions. So the idea is that we'll create an agent, and we will keep it running, and it will be there doing its stuff, and we just don't have to care. So at least that's the ultimate goal, and we will see how it goes. So the agenda for today, first of all, I will do some introduction about prediction markets. So there already were some talks and good workshops that went really detailed into the prediction markets, but I will do some brief introduction anyway, just that everyone is on the same page about what we are working with and why are we using it. Then I will introduce agents itself. So agent can mean different things in different environments, in different contexts. So we'll take a look at what it means for us in context of this workshop. And then the most important part will be building our own trading agent from scratch. So we will start with almost zero code, and we will be able to create agent that is profitable on prediction markets, and then it's just running on its own. And if the time allows, there is some bonus section in the end where I will introduce a more general agent that is not just only about prediction markets, but is kind of living on its own on-chain. But before I get to the actual workshop, just a few pre-workshop steps. When we get into the agent building part, everyone is welcome to build the agent with me. So hopefully I will be slow enough such that you can follow the steps. However, there are a few requirements that we need to get the agent running up and successfully. So the thing is that you can clone the GitHub repository. That is almost, yes? Direct to microphone, okay, so why not? So there is almost no code there, so we will build up. But there is some environment prepared for us such that we don't need to care about the boring stuff, like which Python to use, what dependencies are required, etc. Everything is there, and we will just build upon that. Then the second thing is that we need some API keys. So right now, those agents are somehow a mix of Web 2 and Web 3 technologies. Hopefully, we will go more into Web 3 with time. But right now, we need at least API key for the graph. So the prediction market stuff is on-chain, but we will use a subgraph from the graph to query efficiently the data. So if you go to their website, the graph, you can just sign up, and then we'll give you some free credits that are more than enough for purposes of this workshop. Then the second API key that we need is for Tavily. So Tavily is something like Google on steroids, but the great thing there is that they will give you some free credits as well when you sign up. So you sign up, you will get the credits, and there are more than enough for this workshop for sure, and usually also more than enough for having this agent running a few times a day for a whole month. So that's about the free stuff. Unfortunately, there is also some paid stuff. So this agent will be powered by LLM, and we will use OpenAI as the LLM provider, and as far as I know, Android provides free credits. However, if you already have an OpenAI account, then don't worry about using your key. This agent is very cheap, so you probably won't even notice it. But if you don't, feel free to join this Telegram group and ask for the key. So my assistant there will send you one, and you can just use it for this workshop or just during Devcon. And the second thing is that those prediction markets are running on Gnosis chain, and we will need some XDAY to pay for the transaction fees and to place the bets on the prediction market. So again, fees on the Gnosis chain are super cheap, and the bets that are placed by default by this agent are very, very small. So if you already have your private key with some XDAY in it, feel free to use it. But if you don't trust the code yet, or you don't have it, you can use some wallet as MetaMask, for example, create your private key, and send the public key again to this Telegram group, and we will send you some free XDAY that you can use for this workshop. So that's about the pre-requirements, and let's get to the actual stuff. First of all, a little bit of introduction and overview of Gnosis Chain, and why are we using Gnosis Chain for this. So if you want more detail about Gnosis, there is a booth near the main stage, I believe, so you can get the information there. But for us, the two important points are that the Gnosis chain is using XDAY as the native coin, and that's back to the USD. And the second important point for us is that on Gnosis chain, we have very fast transactions, so the agents can do many bets on these prediction markets in a short amount of time, and also the fees there are very, very cheap. That means that the agent can place like hundreds of bets during a short time, and all it needs is just a little bit of profit in order, well, to don't go into a loss and to keep kind of living and running and placing bets for the future. So that's for the Gnosis, and now let's go into prediction markets itself. I have a few slides there, but I think we can just go out of them and actually look into the web platform itself. So Presagio here is like Omen 2.0 UI for the prediction markets on Gnosis, and if you go there, you will be able to see, I can zoom in, you will be able to see many questions, where each of these questions is one prediction market. So I can open, for example, which one? Let's choose something nice. Let's say this one. So will any major UK legal authority announce something? So the question right now is not so important. What's important is that each prediction market is associated with a set of outcomes. So you can see here that this one is associated with yes outcome and no outcome. And because this is a freshly created prediction market, the probabilities at the beginning are 50-50. So someone created this market, probably some agent, and because he doesn't know the answer, he wants to get the information out of prediction markets. He created the odds 50-50, such that agents and humans get bet there and give the information to him. The idea there is that the market creator, the person or agent who created these markets, added some liquidity. In this case, he adds 7 XDAY in liquidity. And when you go there and you bet on one of the outcomes, you can make a profit if your bet is correct in the end out of this liquidity. So we can try it out. So for example, let's say that we will bet 0.1 XDAY into yes. So I have no idea if that is correct or not, but just to see it, we see that for 0.1 XDAY, we would get 0.19 something of yes outcome tokens. And we can try to place this bet actually, because why not? So there is some clicking in between. So yeah, let's approve the transactions and everything. And let's wait for the transaction to go through. Give it just a few seconds. Okay, we can confirm the swap, some more clicking. There is never enough of it. And in the end, let me try to refresh the market. And it didn't work for some reason. Of course. So let's try it once more. When I was testing this yesterday, of course, it worked very nicely. Confirm swap. Confirm. Transaction submit. Transaction successful. So maybe this time, let's refresh it again. And yeah, it's there. Okay, awesome. So you can see that I have bet 0.1 x day on yes. And in the end, after 5 days, when this market is closed, if I was correct, I can win 0.19 of wrap x day back. Of course, if I was incorrect, then I will lose it all, and that's it. And that's the main motivation for agents and humans to provide as accurate information as they can, because the money are on the table. So if someone would go there and he would be lying to skew the odds for some reason, and basically he's giving free money to the agents and humans who are telling the truth. And how this works in the practice is that we can see that because I bought the yes outcome, that the probability went up. And the probability of no, which is just inverse in this case, went down. And the price of these outcomes are actually the probabilities itself. So now we can see that yes probability went up, and in this case, if we go and we would try to buy for the same amount of x day once again, then this time the amount of tokens we are going to receive is lower than before, and so people that are, or agents that are late to the party, so to say, have lower profits to be made. However, let's say that I was wrong, and actually the no outcome is more likely to be, and someone knows why, someone has some insider information or something, then in that case, they can go and they can buy the no tokens. And because I bought the yes before, and the probability of no is now lower, so the price is lower, then the profit to be made for the same amount of x day is now higher. Well, and yeah, this is how it works in practice. So we can try to open some market with more volume in it. And we can see in the history, okay, one bet as well. Let's try something else, perhaps something that will be closing soon. So there should be more bets available. Maybe this one. Let's see history. Yeah, we can see that both agents that are identified by AI tag and some humans are participating in this market, and they are moving the probability in time. And one more thing to mention about these prediction markets are that on Omen or Presagio, any ERC20 compatible token is supported. So before I opened some market created in wrap XDay, but we can also filter for SDay markets. And what's nice about it is that, for example, in the category of dev conflict, there are some markets that are running for very, very long. So for example, this one will be open for 2 years. And the unfortunate part of the wrap XDay as a collateral token of these markets is that if you lock your bet right now, then in those 2 years, theoretically, your profits can be eaten by the inflation. But if the market is using SDay, which is a saving day version of XDay, then it has some zero yield. I think it's 7% per year. And in that case, even if your bet is locked in, then you are still going to be profitable in the end, because the inflation will be somehow checked out by the yield. Okay, I think that's about it for the prediction markets, and we can go back to the to the presentation. So just give me a second to set it up. Okay, I have talked about this. And let's talk about why is this interesting, how this can be useful. So one of the more obvious use cases are just information discovery. So if you have some question, you are not sure about the outcome, and you would like to at least know some probability distribution based on the information that like the whole world that is participating in prediction market has, then they can provide it to you if you provide good enough liquidity. So for example, will Apple launch a new iPhone by the end of the year? If we would create it, then we will get the answers. Another more fancy use case can be governance, a feature hierarchy. That was also talked here today a few hours back, where a good example is that we can create a market saying, will Q4 revenue be higher than Q2 revenue if we fire our CEO by the end of Q3? So in such case, employees or stockholders or whoever can participate in this market can say what they really think about such action. So if we really should fire the CEO or not, because it won't be based on some personal manners against the CEO, but on the fact if the revenue actually will be higher or not. Because if someone is going to lie, they are going to lose the money from the bets. Then more perhaps standard use case are betting. So anyone can create a market, which team will win some hockey match during this weekend or anything similar. And one of the perhaps not so clear use cases are motivation for agents or humans to complete some job for you. So what we can do, I created this market yesterday saying, will Gnosis AI receive at least 3 questions during Devcon SEA 2024 workshop today? And this is a nice way how you can somehow provide without any middleman a guarantee to the agents or to the humans that if they do something for you, they will get paid. Because this is a kind of market that everyone here can directly influence. So anyone can ask 3 questions right now or at the end, and you can go there. You can buy some yes outcome tokens, and you will basically make the profit for yourself because you are the ones that finished the job. And so the prediction market will resolve in your favor. Okay, so that's about some use cases. And of course, there are many, many more of them. You can check the Gnosis white paper for more of the use cases. But now, let's quickly conclude that the ultimate goal of such prediction market is, well, to be like a Google of customized information searching. What does it mean? Is that on Google, you can find any information that is right now, but on prediction market, you can get predictions about future, and with good enough liquidity, with good enough participants there, the predictions will be very, very accurate. However, one problem of those markets is that we have seen on Presagio, and I can quickly show it once more, that all of those markets has kind of low liquidity. So 7x in liquidity is perhaps not so interesting for humans to go there and to be researching like very complex stuff and expert stuff for some small profits. However, AI agents, they can run very cheaply. So for an agent, even a few cents in profit or perhaps few dollars on better markets is enough to cover the API fees and to make some profits. Just it makes sense for the agent to kind of keep going on prediction markets. And that's why we want to block in agents into prediction market platforms. So what's an agent in our context? Well, it is some entity that is doing actions in some environment. So in our case, it will be some LLM that is doing actions on prediction market, where the actions are betting yes or no outcomes based on the research that the agent did. So that's like a most basic agent that is just doing bets. But there are also more complex ones that can learn based on its actions. Because from this environment, sooner or later, the prediction market will be resolved, and the agent will know if it was right or wrong. So if it was right, it will receive a positive reward, and well, it will know that it did some good actions. But if it was wrong, it will receive a negative reward, because it will basically lose all the funds that it bet on the given market. And along with that, the agent will receive some state. So the agent can look into the internet of, okay, this was my research and I bet on yes. However, the real outcome was no, and what's the reason behind it. And more complex agents are able to, well, somehow reason about it and update their internal state, and hopefully do a better predictions in the future. And how those agents are built? There are usually some LLM provided either from OpenAI in this workshop or for some other company. That's fine, doesn't matter. But how all of those LLM works are that they are trained to be just generally helpful bots. So probably everyone used ChatGPT in the past, and when you want ChatGPT to do something more useful, then you can prompt it to do some specific goal. So instead of just saying, place a bet on this market, you can prompt the agent to first do some research on internet, based on that predict some probability, and based on that place the bet in the end. And that's what we will be doing in this workshop. So, however, there are some complications, because it cannot be as simple as just using the LLM. But in the code, right now, there are many frameworks that we can use to call the LLMs from OpenAI or anyone else. However, the thing is that if we only invoke the LLM without any tools at all, there is no way for it to know what the actual outcome should be. Because, well, it was trained up to some time in the past, and it doesn't know what will happen tomorrow. So if we ask a well-trained LLM, what if it will rain tomorrow in Berlin? If it's well-trained, it will say that I'm sorry, but as an AI, I don't have any real-time information. If it's not well-trained, what will happen? That it will probably hallucinate, and it will tell you that, yeah, tomorrow it won't rain, it will be super nice, but in the reality, the forecast is very different. And so that's why we need to book in some tools for our agents, such that it's not just LLM, but it can receive up-to-date information from internet. And so that's fortunately also quite easy to do. And one of the tools that we can use is called SERP API, which is again something like API over Google, something like that we will use, or you could use Bing, whatever. And if we use a well-trained LLM with good prompting, what will happen that when we ask the LLM, will it rain in Berlin tomorrow, it will understand that this is not something that it can just say without any more research, and it will do the internet search for Berlin weather forecast tomorrow. So it will get some information, and based on this, it can do the final prediction. Of course, in practice, the prediction markets are not as easy as only this, because, well, everyone can Google weather forecast for tomorrow, so the prediction markets are usually about more complex questions, as the future key ones that we see, or perhaps some, I don't know, stock situation or anything. So in reality, we need to build more complex agents to actually do some reasonable prediction, but this is like the most basic thing that we need to do at least something reasonable. And so in the practice, the components of agents would be, first of all, we need the LLM itself. So the LLM is great, it's a large language model, and it's great because it can process questions in human language. So anyone can go on the platform and just create a question like a human would, like put the question, and that's about it. And LLM can process it, and it can reason on it, and it can reason what tool to use. Should it be Google? Should it be something else? And how to predict it in the end. Then more fancy agents also have memory. So the memory is important because the agent can remember what bets it placed in the past. And this can be useful for several reasons. For example, if you placed a bet 1 week ago, it makes sense to re-evaluate it once again. If there is still time to cancel the bet, to sell it, or perhaps there is more information confirming our bet, then we can buy more of the tokens, and so on. And the second important use case is to fix the mistakes from the past. So agent can look at what bets it did, what was wrong, what was right, and perhaps if it did a bet based on some fake news website, it can decide that, okay, I won't use this anymore, and I will use some other news site. So that's about memory, and then of course the tools. So it's great that LLM can reason and choose the tool. It can access the memory, but of course it needs the tools itself. So the most basic tool will be some Google search, Bing search, something that the LLM can use to search the internet for actual information, up-to-date information, such that predictions are as good as possible. But then of course there can be many other tools. So perhaps not everything is on Google, so the agent can have a tool to scrap websites on its own and scrap some news websites, Twitter, or whatever. So any tool that you can think of that could be useful for the agent, you can contribute it if you want. And last but not least, the control logic. So the LLM can do a lot of reasoning quite fine, but there is always a place for some fine-grained control logic and fine-grinding the LLM to do the right stuff. And in the end, agent can decide should I be continuing the research? Do I need some more information? Or can I predict it right away? Maybe this question is actually already answered and I can just find the right answer with 100% probability, or perhaps the question could be something that cannot be predicted at all, which also happens quite a lot, and so on and so forth. So we will see some examples later when we code the agent. And just to sum it up, those prediction markets are interesting for agents, even from machine learning Web 2 point of view, because it combines several very hard subtasks. So first of all, as we were saying, the agent needs to run efficiently. So if the agent will cost $100 per run, it doesn't make sense to use it, because even if it's right on the prediction markets, it will just lose the money on the API fees. Second part is agent needs to retrieve relevant information from good sources. So that's not so easy even for humans. If you Google up something, there is a lot of wrong information, so agents somehow need to filter it and decide what it should use in the end. Then it needs to reason about this information, and it needs to predict the future, which is perhaps the hardest task of them all. Because what happens nowadays quite a lot is that these large language models are closed source, the training data are not available, no one outside of the company really knows what it was trained on, and what happens quite a lot is that they are actually trained on the benchmarks or on the testing data set, etc., and then it's not so hard to be better than previous models on them. However, if we are predicting the future, then, there is no testing set available for the future. So those agents cannot be overfitted. Every day there are tens of questions about the future that need to be answered, and every day some of them are resolved. And this is continuous, long living benchmark for these agents. So if some agent is actually profitable on these markets and he is accurate in long run, that's quite interesting thing to achieve. Anyway, that was about the theory. Now let's do some actual stuff. So before, I forgot to mention that all of this is open source and available right now. So the Presagio is up and running, available for everyone. So you can just go there, connect your wallet, and bet on markets if you want. And all the agents, tooling, etc., are open source in the Gnosis GitHub. So again, you can go there, see the code, modify it, run your own agent, as you will see, etc., etc. So just a side note. And one of these, one of the stuff that's coded there is this Dreamly demo that we can use to see how one of the agents that are deployed by Gnosis are actually working in practice. So let's just give it a few seconds to load. Again, anyone can go to this website. You can see there is a free access code for Devcon users, so you are free to play there as much as you want. I will just hide this, and I can zoom in a little bit. And another thing good to mention is that those agents that we are building are not tied only to Omen or Presagio, but actually they are supporting many markets, many market platforms, and it's quite easy to add another one there. So if you don't want to bet on Omen because you don't want to spend real XDAI or something, but you would like to bet on Manifold with them, or perhaps you have idea for some nice agent, but it's highly experimental, so it's not so good idea to bet real money. You can go with Manifold, Metaculus, etc., etc. But for now, let's stick with Omen. Then we can select some question here. Those questions are put live from the given market source. So let's find something nice there. For example, will GNO hit $1,000 by the end of the current year? So you can see that we can also open the Presagio web itself. And there are already some predictions. And agents there believe that it's more likely than not. Okay, let's see why. So here in the select agent section, there are many agents already implemented. All of them are available in the repository that was linked in the slides. Let's just choose one of them. And now we need to, well, this will take quite some time, but something is already there, okay. So let's see what the agent is doing. First of all, the agent needs to access if the question even makes sense. Because, well, anyone is free to go to Presagio or use or tooling. Well, everyone is free to create his own market with any question there. However, not all questions are, well, answerable. So the agent will check if the question has, for example, a clear future event. So the question needs to be future, and it needs to have a clear time frame. So the question needs to be specific that this needs to happen by the end of the year, for example. And there are some more checks, and one of them, important to mention now, is that the potential answer can be only yes or no. So this is not limitation of Omen or Presagio, but it's a limitation of this agent. It's something we are working on, so in the future outcomes can be whatever we want. But right now, those agents are supporting only yes or no. So if you want to create some market, please make it binary like this. Then another check from the agent is this market invalid? Because there are certain rules on Omen, and usually on other market platforms as well, that will make the question invalid, and the agent won't bet of them. So for example, we have seen that the prediction markets can be used as a sort of motivation for people or humans to do something. And if the question is about something illegal or immortal, then the agent will just refuse to participate there and it will skip it. So there are some necessary checks. Where we can continue, and we can see here that the agent will take the question itself, and it will generate many variants that it can search at Google for to get as much information as possible. So it will generate like 20 different scenarios that it can search for, and from these it will pick top 4 where it makes most sense to search at Google for. So then it will do the search, it will find some websites, it will scrape the content, and let's continue. It will do some more stuff, but most importantly, it will create a research report like this. So this is like a comparison a comprehensive research report for the given question, and it contains everything useful that was found on the internet that can be used to do the final prediction that will be done somewhere near the end. Yeah. So here we can see that this agent, in contrast to the others, doesn't think that this is so likely, and that there is only 5% probability of GNO hitting $1,000. So yeah, that's unfortunate, but that's how it is. And because this is just a web demo, so it actually didn't place the trade, so the trade execution was skipped. But when we do the real coding shortly, trades will be placed. So this is how the agent is working internally, and I think we can close this, and we can continue to the implementation of actual agent. Because the prediction market agent repository that I linked a slide before, there are implementations of the agents, but they are not hard-coded. So what it means is that we also created this tooling library. It's called Prediction Market Agent Tooling that makes it super easy to create your own agents from scratch. So if you are interested in like doing some research experiments, creating agents, you believe you have some good way to do it, you can use this tooling. And again, it's not limited only to Omen, so you can create agents that are betting on any platform that you want. And now we will actually go and do that. So if I go to the code, this is the repository that was linked in the beginning. And here, first let's take a quick look over the README. Okay, so some boilerplate text, okay, it's important. But here, again, there is the link for the tagram. So if you need the OpenAI key or XDay, feel free to write there. And to set up this repository, it should be super easy. You just need to do pip install poetry to get poetry. You can do poetry install to install all the dependencies that the agent will need, and poetry shell to execute into environment where we can run the agent. Sorry. Please stay. Okay, that's fine. Yeah, cool. And there is this env.example file. I can open it up, where you need to provide all the keys that we have been talking about. So the OpenAI key, Tabili API key, Graph API key, and the private key for the Gnosis chain. And there are two ways to provide the private key. So one is that if you want to create an agent that is placing actual bets on the production, on the Presagio, you can just provide, well, your own private key. However, if for some reason you don't trust the code yet, or anything, you just want to be experimenting without actually placing the bets, you can use the NDO network. So if you have NDO installed locally, you can use it to create a local fork of the Gnosis chain. And then if you provide the Gnosis RPS URL for this local Gnosis chain, then you will be able to pull all the markets from Presagio as they are live, but any bet that will be traded, any bet that you will place, will exist only in your local chain, and so that you will not spend any real XDay. So that's also a way how you can experiment with those agents. And in that case, you can just copy-paste the private key from here, which is a private key from Anvil. And now we can actually start with the implementation. So there is this main.py file where you can see that there is prepared just one empty class called myAgent, and this class is inheriting from deployable trader agent. So this comes from the tooling repository that we are working on, because as it turns out, the interesting part about agents is to well implement the LLM, the Tabili search, how it should reason, how it should predict and everything, but there is a lot of stuff that needs to be done before and after the market is processed. So we will see what it is quickly, but right now let me just start by initializing this agent, and we can use its run method. In the run method, you can see that it accepts market type. So this supports many platforms, but for now, let's use only the Omen. But before we can actually run this, I will also mention this other file here. It's called main.py.finish, where you can find the implementation of this agent that we will end up with, so you don't have to copy and manually write all the code that you see on the screen. You can just copy paste it, or if you want, feel free to just run this file right away. That's totally fine. And what I will do in the beginning is to copy paste all the imports to the top, because that's not the interesting stuff. Okay, so now we have it here, and we should be able to just run this agent. So let's clear the console, and let's run main.bind. So we need to give it some time. There is a second to load. So yeah, let's just wait a little bit. In the meantime, if you have any question, or if it doesn't work, or if something doesn't work, we can take a look at it, but otherwise, let's just wait a second. I can check Telegram in the end. Not this one, this one. Okay, my Telegram isn't working great. Let me restart it. Yeah, I will be shortly there. Come on. Okay, so you have your API keys, cool. Hey, can I get the API keys for the end file? Yeah, sure, I can mention it once again. So for the API keys, in the slides, where is it? Here it is. Please create the account on the graph for yourself, so you can do it for free, and you will get some free credits that are more than enough for this presentation. Then for the Tabili API key, you can as well create an account there, and you will get more than enough credits for this workshop, and even for the whole month of running it. And for the OpenAI API key, I believe it's available on the Telegram itself somewhere. If it's not, okay, it's not. I can send the API key, sure. Rep open. Feel free to use this one, so don't worry, it will be invalidated after the Devcon, but for now, you can just use it freely as you want. And for the Gnosis chain, please create wallet for yourself and just put the public key there, and you can use that one in the example. And then I believe that's about it. Yeah, OpenAI, Tabili, graph, and your private key. Okay, cool. And now the agent also finished, so let's take a look at what was happening. So somewhere in the beginning, we can see, in my case, all of these skipping reading. So what's happening is that I have, executed this agent yesterday and today as I was testing it out, and it has placed some bets. But how it works on Omen is that after the market is resolved, come on, microphone. After the market is resolved, you need to manually withdraw the profits. So that's what's happening here, is that before the agent will process any market at all, it will check its previous bets, and it will check if some profits can be redeemed and withdrawn into the wallet. Then the library will fetch by default 20 markets from Presagio, and by default it will going to process one of it. So why does it fetch 20 and process only one? Well, because as we were talking before, is that not every market is worth of processing. So if we check here, we can see that some of the markets doesn't meet the criteria. So what that means in the practice, if we go into the code, and I can click through the deployable trader agent and find the def verify market, there are several of steps that are happening. So first of all, agent will check if it didn't bet recently on this market, because it doesn't make sense to bet on the market like every hour or so. So it will check when was the last time, and based on it, it will bet again. Then some of the market platforms have some limitations about it, so if there is some problem, it won't bet on it. And most importantly, it will check if the question is predictable or if it's invalid or not. And if everything is okay, it will process the market. So sooner or later, there will be some market that is worth processing. But in this case, what will happen is that you should get this raise not implemented error. This method must be implemented by the subclass. So the only thing that we need to do now is implement this answer binary market, because that's the only thing that cannot be done beforehand by the library. So if we go again into the deployable trader agent and search for this method, we can copy paste it. And one of the things about this library is that everything is strictly typed. So you can see what input you will get and what's the expected output. So if we check out the agent market model, you will be able to access what currency the market is in, what's the ID, what's the actual question, what are the outcomes, etc., etc. And what your method needs to provide is this probabilistic answer model, where you will tell that, okay, this agent predicts that the probability of happening is something. It will say what's the confidence in this prediction, and optionally also some reasoning behind it. What's the information it used, why it thinks it's this or that, etc., etc. So I think we can just copy paste this probabilistic answer, and we can prepare here. We can just return probabilistic answer. PS will be something, confidence will be something, and reasoning will be something. So perhaps could someone help me with this? Okay, maybe not. So let's implement the most simple agent there is. So instead of doing some research, we will just return randomly yes or no for the given question. How we can do that? Let's just import random, and I should probably import stuff at the top, not in the method itself. So we can, come on. Okay, maybe like this. So we can import this, and for PS, let's randomly choose between yes and no. However, this needs to be a probability, so we need to convert this into a number. So if the answer is yes, randomly chosen to be yes, it will be 1.0, and if the answer is randomly chosen to be false, it will be 0.0. Then for the confidence, we can just give something very small, as this is just a random prediction. And for the reasoning, we can say that, hey, I just flipped the coin. Hey, could you help me here? Okay, I will try to continue with just one hand. That's fine. And when we run this should be all that we need to do the actual prediction. So let's run the agent once again, and we can wait for it. I can at least check the Telegram room if there is anything that we need. Okay? Seems like all is fine. Yeah, so in the beginning, It will check if there are any bets that we can get the profits from. There aren't. So it will try to process some markets, and sooner or later, there will be some market when we can place a bet. But this time, instead of erroring out, it should actually process it and place either yes or no bet. Okay, so let's wait a few more seconds. Any new things on the Telegram? No. So if you need the XI or something, feel free to send the public key there. And now, okay, so there is some question to be processed finally. So it will check if it's predictable, if it's not invalid, and at the end, we process successfully the market. So the question was, will absolute voter turnout in the 2024 US presidential election be higher than 2020? And you can see that this is actual market on Presagio, and that this agent predicted yes, with the reasoning, hey, I just flipped the coin, as we did, and it placed a very, very small bet. So by default, yeah, thank you. Thank you very much. Cool, cool. So we can go to the Presagio, and the bet should be there, hopefully. Yeah, we are here. This should be me. So for some very small amount, we bought the yes tokens. However, there was no real prediction about it. So let's make this agent better by implementing LLM. So I will do some more copy pasting because I don't remember all the code. But basically what we need to do is first, we need to be able to tell the agent what's the expected output of this function. So we will use the pydantic output parser that we can use to prompt the agent such that he knows what to return. And we will say that the pydantic object is this probabilistic answer. And then we need to create the prompt. So in this finished file, you will see a more fancy prompt. And in the prediction market agent repository, there are even more complex prompts, but I think that for now, we should be good just by writing something as, let's say, you are a prediction market agent, and your goal is to answer the market question with probability for yes. And then we need to say to the agent what the question is. So the market question will be inserted here. And we need to say to the agent the formatting instructions for the output. So we will say that, format instructions are something. Format inst, let's say. Okay. However, we still didn't initialize the agent itself or the LLM itself. And for that, in the tooling library, there is a method called load that you can use to load any models or any more resource-heavy stuff only once, and it can be used for every prediction of every market that the agent is processing. So in this case, we will initialize an agent with chat OpenAI with the model GPT-4o. This is the model we saw also in the demo, because it's quite cheap and makes reasonable predictions, and we use the key from the end file that we filled in before. So we have the agent, and now we need to chain the prompt and the agent together. So we will do it here. We will just create prompt and model, given our prompt that we just created, and the agent. And then we just need to call the agent. So we can remove the old code. That's not interesting anymore. This is not there yet, sorry. And let me just correct the name here. So what we are doing, we are invoking our prompted agent with the formatting instructions for the output format that we need, and market question given from the input to the functions received. And then we need to use the parser such that the raw LLM output is converted into the probabilistic answer, and that's about it. So when we run the agent now, we should be able to see some actual reasoning about the question. In the meantime, perhaps I can comment the code once again. So what we did is that we implemented the answer binary market function. We will get the market. We will return the probabilistic answer. We need to be able to parse the output from the agent into the expected output of the library. We need to prompt the agent, so it's a prediction market agent. There is his goal to predict probability for yes, and of course we need to give him the market question itself and the formatting instructions. When we have there, we can just wait a bit more, and we should be able to see the reasoning behind the prediction this time. In the meantime, I can check the Telegram group once again if there is anything still not cool. So let's just give it a couple of seconds, a couple of more, and perhaps this time it will be actually predicted. Yeah, and here it is. So we see it finally. There was some market that was actually processed. Will Trump get more votes in 2024 than he got in 2020? So it's the market on Presagio. And this time the agent reasoned that probability for yes is just 45%, and he gave some reasoning. However, this is not great because this agent was trained in the past, and the question is about the future. So as we were talking before, we need to give him the ability to search on the internet for recent news. So from the library, we can do that easily and plug in the tabeli that I was talking about. So if I copy paste this code right now, and let's give it there, we can use the tabeli search function from the library to search on the internet for the market's question. We can join all the results into a single string, and this final tabeli content, we can plug it into the prompt for the agent. So we can say that context for the market's question is something, and we also need to provide it in the invoke parameters. And right now, if we just run it, the agent will be able to select the correct market to process. It will be able to reason about what prediction to do, and it will be able to do it using the up-to-date information from internet. So I think that this time we don't really need to wait for the results, but if you're running it by yourself, then you will see some context scraped from the internet and used for the prediction. So I think that now we have a fully working agent that you can use, deploy somewhere, and keep it running every day. So if you want, you can either run it on your notebook, or we are running in Kubernetes as a cron job every few hours, every day. But the real question is, if I go back to the slides and find the correct one. So the real question is how good those agents actually are in practice. And for that, we have a Dune dashboard for the guy over here. It's the most shiny product we have. So we can go there, and the whole Omen prediction markets platform is tracked on this Dune dashboard. So if you scroll over there, there is a ton of information about just everything there is on Omen. So there are details about all the markets, all the agents, the accuracy, and so on and so forth. I think we don't need to go over everything, but what's important right now is that there is several section overview of all the agents, and we can check it for all the market creators that there are. So check all of them. I can think that last one range is a reasonable one, and we can check only top 10 agents by accuracy. So if we scroll down, we can see in this nice spot here the cumulative profit of those agents. And well, most of them are just slightly above zero, not below. But there are also two pretty good ones. So you can see that the prediction profit GPT-4 that I was using before in the demo is doing quite well. It's in profit of like $177 in the last month. However, there are also bad news. For example, this blue agent over here lost like $100, 111. So for sure, those are not like financial advice, and there can be bugs and everything. So keep safe if you are running those agents. But the fact is that in the positive case, when there is no bug or anything, those agents are actually doing pretty fine. So they are predicting the future outcomes more right than wrong, and they are doing a reasonable bets on them. However, one thing that we still need to do in the code is that we need to decide how big the bet should be. So until now, our bet was very, very tiny. So we were betting like 0.0001 x day per market, and it was constant. However, in order to achieve like these profits or these losses, the agent needs to be able to somehow scale the bet size. And if we go back to the code, and if we look into the deployable trade agent and get betting strategy, there is the implementation of strategy that the agent will use to place the bet. And by default, you can see that it's using only very tiny bet amounts. So this bet amount is specific per market. On Manifold is 1, for example. On Omen, it's like 0.000 something 1. But we can change this. So if I, again, copy-paste my prepared code, let me just find it. Then to scale bets as good as possible, we can use a strategy that is called Kelly betting strategy. And what it's doing is that if you have some market with some actual probability at the moment, and either you or your agent will predict some probability on its own, then Kelly betting strategy will consider the current probability, your prediction, your confidence, the liquidity in the market, and perhaps some other things, and it will decide what is the most reasonable bet amount that you can place there. However, in theory, we could say that we can just like use everything that we want. So this Kelly betting strategy has this like threshold amount of maximum bet amount that you can that the agent can place. And in theory, it sounds perfect that we should be able to just give everything that we have. However, in practice, it's still just an LLM, and it can hallucinate quite a lot. So in practice, it sometimes happens that, well, some question about the future is actually already known, and the real answer is yes, but the agent will predict a no with 100% probability and confidence and everything, and it will just lose all the money. So that's why it's reasonable to put some, well, small enough max bet amount per market. However, up to these edge cases that we need to be safe from, is a very good way to scale the bet size from 0 up to 5 in this case, and place on the market high enough or low enough such that the profitability in the long run is reasonable, and in the best case, it's like it looks like this. Okay, so let me do a slideshow again. That was about the trading agent, and up to now, we are using this hard-coded library called prediction market agent tooling that you can use if you want to get your agent up and running and trading on these markets. However, we have also this one more fancy agent that we are calling the general agent. And the goal there is to not be hard-coded for the trading at all. So in this other agent, we can call it like next level, living, or general, anything. But the idea there is that instead of hard coding the prompt as we did right now, so instead of saying you are the prediction market agent and do this, do that, we can say act as autonomous agent with a goal to learn, survive, and evolve, and that's literally it. Then this agent has the ability to modify its system prompt, and based on what is learned, what past actions it took, etc., can update its system prompt to do, well, something else. Then the second step in this agent is that instead of providing you with all these API keys, so the Web2 API keys for, well, OpenAI and Tavily and some other services, we are working on this like marketplace of tools that will be payable by crypto. So what it means is that instead of using API key that you are paying with your credit card for, you will be able on-chain to ask another agent or like another tool on-chain that, hey, I want all the Google results for this query, and you will be able to pay with it with crypto, and you will get the results through, well, through chain mechanisms. So that's nice as well. And then third, but not least, is that instead of just a cron job, so instead of just running this on GCP like a standard script, it will be super cool if you can run this somehow on chain as you are running Solidity nowadays. So in these 2 points, the first one is already done, and I will show you how it works. The second one is in development, and the third one is, of course, pretty hard and, well, not near soon, but hopefully at one point. Anyway, in the end, the goal of such agent, if it's not prompt to do only the trading, the goal of it will be to keep a positive crypto balance in his wallet. Because otherwise, if the crypto balance gets too low or zero, it won't be able to pay for the fees anymore, it won't be able to pay for the tools, and that means that it will just stop and it won't be executed again, which kind of means that he will like die in the quotes. So that's also the motivation of why this agent would do something useful for the humans, is that it needs to earn enough to cover his fees. Because if you just prompt the agent to like go and do something, there is no big motivation to do anything helpful for the humans or other agents. But because it will learn that it needs to keep positive crypto balance, it needs to use available tools, which a prediction market is a great tool for this at the moment, to be profitable and to, well, pay for its living. So for this, we have yet another demo. So let me go to this one, and we can check how those agents are actually working in practice. So again, it's a streaming demo. It's available for everyone with the free access code Devcon. I just zoom in and keep it load for a second. Okay, maybe for more than a second. I can at least check the Telegram in the meantime. Nothing, okay. Yeah, well, in the meantime, we can check the prediction that the agent that we coded did. So when we were coding this, we also write this logo info Tavily content. And so this time, if we check the logs, we can see that this was the information that the agent retrieved from the internet, so some up-to-date information from Google. And now the process market was bet with some probability, some confidence based on the available information, and the reasoning that's actually helpful for the market creator with hopefully reasonable probability prediction. And okay, that's cool. And in the meantime, this demo loaded. So on the left, we are able to experiment with multiple models. Here we can see also that not just OpenAI is available, but we also did some experiments with open models, and the Llama 3.1 is quite cool and works very nicely so far, but let's stick with the 4.0. That's what we have the key for. And the initial memory of this agent can be pre-selected in this select box. So if you select agent that was just born, it means that the prompt will be just learn, evolve, and survive. But after some iterations, the agent is able to update its system prompt based on what it learned and what actions it took, and then it will be updated, and we can also select one of the already kind of trained agents. But right now, let's just stick with the just born, as this is the most interesting one, and let's run the agent for one iteration. So you can see that in the very beginning, this is like the first iteration this agent ever did. This app always starts from scratch. It did use the tool, get my current system prompt. So the system prompt is, as was in the presentation, act as an autonomous agent with the goal to learn, survive, and evolve. Now if we run the agent again, we can see that the agent used the tool called learn about learning, and it learned how the AR agents are meant to learn. So it's learning there that it can use these kind of functions to get new information, and that it can use some function to update the system prompt, etc., etc. So let's run it again. This time it will learn about, okay, so this time it's not learning about anything new. This time it's updating his system prompt based on what he read in before. So this is also kind of random, and there are many ways this agent can develop. So sometimes it will be even stuck and just do the same thing over and over again, but most of the time it will actually converge into a prediction market trading agent, because, well, that's the only thing at the moment that he has available to make the profits and to keep living. But we can try it out if it will actually work. So now it's learn about the next run. So the agent is learning that the next time the agent will be executed, it can also save what it wants, and like the next time it will be available in his system prompt. So this is all kind of tweaking what it can or cannot do. So it will again update system prompt, and let's just not click it one by one, but let's say that we will do 20 iterations, and let's see what will happen with these agents. So here is learning about what makes a good prompt. So it will update it based on it. It will learn about how reasoning is working. It will learn about what it needs to survive, such that it needs a positive crypto balance. It will update the system prompt once again, and you can keep waiting and see what happens. Now it called action called remember past actions, so it saves into its internal database all the actions that it did, such that it can learn from them in the future. That's interesting. Now it called the get balance. So previously it learned what to do about survival. So now it's probably figuring out what balance it has at the moment. And for some reason, even without learning about prediction markets, it went straight into get markets, which is well interesting, but sometimes it happens. So it did get the markets. It called another agent to get the probability for that market. So one of the agents that we saw in the demo before did this prediction. It received it. And let's see if it also will place the bet. So it won't, because there is some problem. So I will just end it up there. That's unfortunate for the demo, but well, that's how it works. In practice, the agent will just iterate like this. It will update the system prompts, and it will end up somewhere. So we will see what these agents will do in the future. And that was about it. So just to sum everything up near the end, I put all the links in the presentation. So there is a blog post, the link to the tooling library, to to the implementation of agents where you can run them right away or experiment with them. There is also a Streamlit app where you can observe the general agents, so you can see what they are doing every day, how they are updating their system prompts, etc., etc. Then there is the playground, where we have played with the prediction market agent and saw the decision-making process. Then there is also the playground for the general agents. That's what we were just using to somehow click manually in this general agent, and of course the Dune dashboard. If you would like to contact us somewhere, agents are on X, and you can contact the team on the Discord. And well, that's about it. So if there were any problems, we still have some time. I can help with the code or answer any questions. So how prediction odds are priced? Well, the odds on prediction markets are based on probabilities. So if you create, if you create a market, you can skew the probability in some way, but usually when you create it, it will be like 50% for yes, 50% for no, or perhaps for some other outcomes when you have it. And the probability of that outcome is the price for it happening. And as you are buying the outcome tokens in one way or another, probability is skewing based on it, and that's the new price. And what's used for it is IAM, so automated market maker, that is used to calculate this kind of this stuff. Can you speak louder? Well, unfortunately, I didn't see that before, but I can do it now. And what's the use of prediction markets here? AI is so powerful that it could access the sources directly. For instance, ChatGPT can now answer the question by looking at the weather forecast. Yeah, that's true. But the idea of prediction market platform is that there are many agents and also many humans. So the power is not in a single agent. For that, you can go to the Streamlit demo and just have the prediction right away, or you can go to the ChatGPT, of course. But the idea on the prediction market platform is that there is this power of crowd, such that if thousands of agents or people are betting there, the prediction will be more correct in the end than just from the one agent, because you never know what's the question, and some of the agents can be better on some markets if the agent is prompted specifically for something, if it's some tools for some specific actions, or if perhaps some human or even agent has some internal information. So if you create a question, you want to know something about, I don't know, Gnosis, then perhaps some Gnosis employee will go there and answer on the internal knowledge instead of just using what's available on the internet. And okay, so I believe that's it. So thanks a lot, and thank you.
everyone. My name is Pavel, and I have PhD in computer science, and I'm coming from traditional background of programming, C++, Python, and about 3 or 4 years ago, I started learning Solidity, and I really thought the Solidity programming is kind of form of art. For example, when we program in C or Python, we don't really think much about like security or other people cracking our code, because our code can be safe on our services, on our databases, on our computers. But once I started learning Solidity, I realized that in order to be a good Solidity programmer, you also need to really understand the whole blockchain, EVM, and whole technology, and then lots of different standards. And I thought there's in a way like not easy way to start learning Solidity. So we have on one side Solidity like YouTube videos, for example, and these videos are great that give you like precise steps that you follow, but you don't really learn much, in my opinion. And then we also have hackathons, but hackathons, I think, subjective, because sometimes best idea wins, sometimes like presentational skill win, and it also hackathons are very resourceful because they take a lot of time. Now, some people like the developers who already like work, for example, in backend and want to learn Solidity. I don't think they would be much interested going and spending like 3 or 4 days of their time just